if we could all take our seats. We're going to get started in just a minute. If you could take your seats, please. We promise there'll be plenty of time to network during our breaks and our lunch, but we're going to get started in just a minute. Thank you. All right. All right, well, thank you. Well, greetings and thank you for all being here. My name is Chris Menzel. I'm the Executive Director of Stanford Data Science, and I'm excited to welcome you to this inaugural conference. We have a full day lined up, so let's get right into the program. It is with great pleasure that I introduce Marc Tessier-Lavigne. Pioneering neuroscientist Marc Tessier-Lavigne became Stanford University's 11th president in September 2016. He returned to Stanford after serving as president of the Rockefeller University, a graduate biomedical research university in New York City. From 2001 to 2005, he was a professor of biological sciences at Stanford, where he held the Susan B. Ford Professorship in the Humanities and Sciences. He's also held faculty positions at the University of California, San Francisco, and executive positions at the biotechnology company Genentech. Please welcome Marc Tessier-Lavigne.
Well, thank you, Chris, for that kind introduction, and good morning to all of you. I want to thank you for joining us for Stanford Data Science's inaugural conference. It's so great that this conference is occurring in person, that we're all together. It brings me so much joy to be reunited with colleagues and friends and students, see so many familiar faces in the audience and some new ones as well. So this is just such an exciting time. Today's conference is going to bring together Stanford faculty, scholars, students, and friends to think through the future of data science and to learn from one another about new developments in the field. Our speakers are going to explore important questions about data science methodology, the application of data science in varied fields from health to environmental studies to the social sciences and more, and also ethical questions related to those applications. The day is going to kick off with an exciting keynote by Emery Brown, a world-renowned neuroscientist who's also a good friend. Emery, it's so wonderful to have you here. He's going to explore some of these themes in relation to our understanding of the brain and consciousness. So we have an exciting day ahead, and I'm delighted that so many of you are here to share your ideas, to ask crucial questions, and also to advance our work in this area. I'm also pleased that these important questions have found a home at Stanford Data Science. Stanford Data Science was created in 2019 to weave data science research and methods into the fabric of the university. This central university resource aims to advance discovery in data science itself through basic research and the creation of new methodologies. At the same time, data science holds the key to advancing discoveries across many disciplines at Stanford, both in fields that traditionally work with data, from astrophysics to economics, but also fields where the use of data is relatively newer, like the humanities. The application of data science, we know, can provide great insight. In fact, it's essential to providing insight in so many disciplines, and even more so today as the amount of data that's available to probe questions has increased exponentially. And in so doing, it's also helping us find solutions to many of the challenges our world faces. So both advancing understanding and discovering solutions. In this way, Stanford Data Science is at the heart of our mission to both catalyze discovery and also apply knowledge to creating solutions. I'd like to underscore two important features of Stanford Data Science that I've already alluded to. First, structuring Stanford Data Science as a central university resource ensures that this work is done in an interdisciplinary way, and that faculty and researchers in all corners of the university have access to cutting-edge methodologies that can expand the horizons of their research. I think the collective experience of the people who are assembled here today is a testament to the ability of Stanford Data Science to bring together data scientists and scholars from many fields who rely on accurate and dependable data and data science techniques to do their work at the highest levels. Second, and crucially, Stanford Data Science is focused not only on discovery and application, but also on ethical principles around the use of data. The application of data has incredible potential to transform our understanding of humanity, our society, and our planet. But as we improve our ability to use data, it's become increasingly urgent that we consider factors like privacy, like bias, and the societal implications of and impacts of this work. As we create methodologies and approaches that have the potential to shape practices across fields and in the wider world, it's critical that we ensure that human values remain at the forefront of our work. I'm so grateful that Stanford Data Science is attentive to these issues, many of which will be discussed during today's 3:30 panel on how to increase trust in data science. Now, before I close, I want to thank Emmanuel Candès, who has really been the leader in developing Stanford Data Science into the important central resource it is today. Emmanuel is a powerful advocate for the importance of discovery, for training the next generation to be rigorous in their research, and also for applying ethical principles to the use of powerful new tools. Emmanuel's been instrumental in our efforts to advance data science across the university, and I can think of no one better to lead us in this work. I also want to thank the members of the Stanford Data Science Advisory Group for joining us today and for all your work to guide the creation of this unit at Stanford. I also want to thank the organizers for arranging this inaugural meeting and for pulling together such an exciting and thoughtful program to explore the pressing issues within the field. And thank you to all of you again for your contributions to this work and for being here for this important series of conversations. And with that, I'd like to hand it over to Emmanuel. Emmanuel, thank you.
Thank you, Marc, for this enlightening comment and also very generous comments. I want to thank you, but not only you, also the entire leadership of the university for believing in data science, for believing that data science is an important field, and actually supporting us and standing by our side during this long pandemic. And your unwavering support has been really appreciated by all of us here today. We're very happy to be back with you in person. I want to thank Percy Drell, who has been very supportive of data science from the get-go, Marc, of course, and all the deans. Jennifer Widom, Dean of Engineering, cannot be here with us today. We'll hear from Deborah Satz later on ethical issues around data science, and also the Dean of Research, Cam Moller, and Tim Stearns have been all extremely supportive. So thank you all for your support. Sorry, I had some notes that I need to get back. Even though this is our inaugural conference, a lot of work has been done already, perhaps during the conference by a team of us ever since we started data science about 3-4 years ago. And you'll hear about some of the activities we've tried to develop to make data science a good place on campus. You'll hear about our research centers. You'll hear about our educational efforts. You'll hear about how we're trying to increase multidisciplinary aspects of research through graduate fellowships and postdoc fellowships. You'll hear about outreach activities. But I think the past is not what's most important. What's most important is the future. And we're very excited to have you all here because we just want to learn from you. We want to know how we want your help in making Stanford Data Science better. We want your help in energy and enthusiasm in telling us about the work that we need to do. And Stanford Data Science cannot happen without you. And so we're very happy to have this interdisciplinary conversation today so that we can learn together how we can fulfill your expectations and be a positive place on campus, a place that values people doing data science. So I'm expecting a lot of things from today. We've organized this day as a conversation about data science. We want to increase our sense of community and shared intellectual goals. Now, we'll hear a lot about many different topics, and we'll start with neuroscience. And it's my great pleasure to welcome Emory Brown to Stanford. Emory is many things at once. He's an anesthesiologist, he's a statistician, and he's a neuroscientist. And he's a Zappel Professor of Anesthesia at Harvard University and Massachusetts General Hospital. He's a Professor of Computational Neuroscience at MIT. And he has something very unusual on his resume. He's a member of all three academies. And I don't know of how many people I can say this. He's a member of the National Academy of Sciences. He's a member of the National Academy of Engineering. And he's a member of the National Academy of Medicine. I think when we thought about this conference, we could not think about a more exciting speaker because Emory's work is about consciousness. And what is consciousness? It has to be, in my view, one of life's greatest mysteries. And what does it mean to be aware or to sleep or to be in a state of deep coma? And so this is broadly speaking, Emory's field of research. And I think Emory has sort of brought the issue of consciousness out of science fiction or even poetry to the realm of science. And so he's been interested in the brain and all states of consciousness. As you'll see perhaps from these lectures, is a continuum of states in consciousness. You can be unconscious and not perspective. You can be unconscious but perspective. And in his research, he has used data in this particular case, EEG, that is electroencephalograms, to infer the level of unconsciousness in an individual, for example, under general anesthesia. And so he has shown after a remarkable study in 2013, how anesthesia hijacks the brain waves and makes it difficult for different parts of the brain to communicate, and that's what leads to unconsciousness. So his work on anesthesia brings us a window on the brain, and we can learn about the brain, again, perhaps one of the biggest mysteries, how the brain is working by understanding and monitoring data as we put people and patients through induced unconsciousness. Emory, it's a pleasure to have you here. You're a great friend to Stanford, and we look forward to your lecture.
Great. Well, thank you so much. Let me just get this. So, thanks so much for having me. It's a real pleasure to be here, and I hope I don't make you unconscious during my talk from what I'm about to say. So, I'm going to focus. I will get to some issues of consciousness towards the end of the lecture. But what I want to talk about is this sort of general theme of keeping science and data science. And to do that, I'm going to talk about three topics. A little closer.
Here's your notes. I need that full screen. Thank you. Just run like that.
Oh, okay. All right. That was an audible. All right. So I'm going to talk about measuring the period of the human biological clock. I'll say a little bit about what it's like to decode information from the rat hippocampus, and then I'll talk about monitoring depth of anesthesia. We'll discuss some issues of consciousness. All right. So measuring the period of the human biological clock. So I was a graduate student. I did my PhD in statistics at Harvard, and one of my PhD advisors was Peter Huber. And as many of you know, Peter was and still is an expert in robust statistics. So I went to Professor Huber when he got there, and I said, Professor Huber, I'm interested in doing a PhD in robust statistics. He goes, I'm tired of robust statistics. I said, I'm tired of robust statistics too. And he said, well, he said, multiple time series analysis. He said, that's an area where there's a lot of things to be done. And I said, oh, wow. So I said, if I find a problem, multiple time series analysis, will you work with me? He goes, well, if you find an interesting problem, I may work with you. If it was not so interesting, I may not work with you. So I said, okay, fine. So I was very lucky because Chuck Seisler had just come from Stanford, actually, and set up his laboratory, his sleep research laboratory, at the Brigham and Women's Hospital. And Chuck was studying the human circadian system. And he had these ideas for these really, really cool experiments. So I'll just show you some of the data. He was going to be doing 3 types of protocols. So one was the constant routine, where people were sort of in a room in a same position, sort of no meals or that sort of thing, or at a very sort of stable condition, kept awake for about 30 hours or so. Because what he wanted to do was track their circadian rhythm, following their body temperature, and then really trying to estimate where the minimum occurred, because that was the main phase. That was the phase in the cycle which was most robust, let me just say it that way. Then he was thinking about sort of some of the more standard longer protocols like free run, where you isolate someone in an environment, they have no light cues or this, in other words, they have no cues from the outside world. Their intrinsic clock runs its intrinsic period, and you do some analysis to measure the period. And then he was thinking about a forced desynchrony protocol. With forced desynchrony, you put someone on a daylight cycle where they can entrain, so put them on a 28-hour day, all right? So on a 28-hour day, your internal clock can't entrain to 28 hours, so you'll actually get to see the actual intrinsic period. And you can actually, and so these are these sorts of protocols he's going to be doing. And he's recording many things, but the main thing is human core temperature, measured from, just to be frank, from a rectal probe every minute. So these were very interesting experiments. All right. So this was the first paper that I wrote of that work. So you can see, because of the data, that everything's harmonic, so no surprise I'm working on harmonic regression, all right? Not really sort of straightforward, obvious model. And you see the waveforms are asymmetric, so working on harmonic regression models that have more than one harmonic, at least 2 harmonics, let's say, all right? So just to make the point clear, go back to what I call Statistics 101. So I've got some data, I know the mean, I know the variance, I take the sample mean as the estimate of the true mean, and the variance goes down as 1 over n. Okay, so why is he telling me this? This is Statistics 101. Okay, all right. Because of this. So it turns out that if you have a harmonic regression model like the one I'm showing here now, and so it's a harmonic regression, we have at least, we have p harmonics, and we have, let's say, just a simple correlated noise model, all right? Then if you calculate the variance of the period estimate, it goes down as 1 over t cubed and not 1 over n, or 1 over t, all right? And this was known at the time, this was, been known for years. Peter Bloomfield, in his book on time series analysis, talks about this and gives some intuition about why it's the case. And the quick back-of-the-envelope intuition is that if you compute the Fisher information for this problem, right, and you look at the sum, you get a sum of t squared. And the sum of t squared is proportional to big T cubed, so that's where it comes. It's really just that simple. It's not deep at all right? But what it means is if you do have a model where this model works, you can get very precise estimates of the period. That's the key thing, all right? So, and if you look right here, you see this, you have this thing which is like a signal-to-noise ratio. Here's the energy at the harmonics, and here's the spectrum at that same location, all right? Well, so this is the first paper I wrote. It was a note to Biometrica, and I sent it off in September. It was accepted in December. I said, man, this academic thing's going to be a piece of cake. Yeah, I got this, all right? And so I just checked, literally just before I started here, and as of this morning, it has a whole 21 citations. All right? So it's rocking the world, as you can see. All right. So that was in the early 90s and late 80s. And Chuck decided around the mid-90s that what he wanted to do was measure the period of human biological clock. He had a really cool biological intuition. He realized that the period was being improperly estimated. And so here's the logic of what he thought. All other species had periods that were closer to 24 hours rather than 25, all right? And he just couldn't understand why this would be, that humans would have one closer to 25. And then he realized something important. We'd published a paper back in like 1989 looking at the effects of light on the human pacemaker. And he basically showed that light was one of the most important factors for shifting the internal clock, all right? It could be artificial light, it could be natural light. And so during these free-run studies where you have someone in isolation, you select your own light-dark cycle. So what that means is that you're giving yourself light as an input to your circadian oscillator, and there's an asymmetry in the way light affects the oscillator. And the way it happens is it tends to delay the oscillator a little bit as opposed to advancing it. So what happens is that when you do these studies like this, you get an incorrect estimate of the period. It's a little bit longer than it should be. So that was Chuck's insight, a really, really cool insight that he had with Richard Cronauer. All right. And so these are those microphase shifts. And so I told him that, well, you know, if you do this, you're going to have some way to actually measure the error, because you're saying it's this, but it's plus or minus something, all right? So these are some of the so he did this in forced desynchrony. So here's what the forced desynchrony protocol looks like. So the person is on a 28-hour day, all right? Now they're 14 hours of 10 lux of light, and then 14 hours of total darkness. And if you ever, 10 lux of light is basically practically darkness in and of itself. And the other thing is, but we probably have more light in our room now just from having our cell phones on, our radios, our televisions on, or whatever. But this is really, really, really dark. All right, so he's really kind of taking out the effect of light on the pacemaker. And you can entrain to, or a human can entrain to a period of 28 hours. So you're going to see the intrinsic period of the oscillator. And you can actually see that in the data. So these are 5 subjects here from that study. And if you look here, you can see the constructive and destructive interference. There are 2 big components, a 28-hour component and something around 24-hour component in this data, in each of the subjects. You can see it there. It's like, for example, like right here.
We cannot see your cursor.
That's why I switched the other mode. Okay. That's why I switched the other display mode. All right. But so look at subject A, between 15 and 20 hours. You can see that it adds up destructively there. Whereas if you look at the same subject around 15, they're enhanced. So it's getting bigger in one place and small in the other. So that's the constructive and destructive interference of these 2 oscillations. There are 2 oscillations there. That's the bottom line. All right? So here's the model. Now we just add a 28-hour component to the model. There's the mean. That's the circadian piece. We have at least 2 harmonics for the circadian piece and about 4 harmonics for the 28-hour day oscillator. And we used correlated noise because it's very real. For example, your body temperature is highly correlated from time to time. And taking that correlation into account makes the estimate of the period much more accurate because you don't have, like 36,000 independent data points. They're highly correlated. You have to take that into account. All right? All right. So here's what the decomposition looks like. This is for one subject. You can see the circadian piece. And the magnitude of the 28-hour component is as big as the circadian piece. And when you add them together, now you can see the constructive and destructive interference really clearly as they're cleaned up there a bit. And then the residuals together with the AR processes in the bottom panel. And I can tell you we were able to convert each one of these subjects' data into white noise with the model. In other words, the model fit very well for all the subjects. So we published this paper in Science back in 1999. And so I was able to dust off my error formula. It's been cited 21 times. And we had a very precise estimate for the period. That was kind of the take-home message. And it had this really, like I said, this really cool feature, the signal-to-noise ratio piece in there. And so here's the data from the subjects that we looked at. And actually, Chuck studied about 12 sort of normal, healthy, sort of young people between the age of 18 and 64. And he studied, believe it or not, he studied 12 elderly patients. We had 12 patients, 12 subjects who were over the age of 65 that underwent this protocol, believe it or not. because we thought that the question was, were the periods of older people different from those of younger people? That was the issue. And you can see that those are the period estimates for each of the subjects, and the standard errors are they're not in hours, they're in minutes. And it's because of the protocol. The model worked and gave you a very accurate description of the data. All right? And then Chuck had one subject who did both protocols. The subject did a forced desynchrony protocol, okay, and he did the free run protocol. And so I told him that if you had the light times from the free run protocol, you could actually estimate the period from that data as well. And so that's what I did. So here's the model that I worked out. It's a van der Pol oscillator with light inputs. So this is the light input going into the van der Pol oscillator. So you have a signal-to-noise model here where the signal is the solution of this van der Pol differential equation, basically. Just like the other situation before, except now the signal is represented by the van der Pol, and it can take light as an input. All right, so when you do that, so so let's look at this one over here. Here's the harmonic regression. When you ignore the light effects, you get these huge oscillations. It looks like circadian oscillation is really big. There's the noise. But when you take into account the light, here are the light effects right there. And then here's the circadian oscillator, has a much smaller amplitude. And look at the period. The period is 24.25 hours. So you could actually extract it from these data with a proper model, essentially. And over here, if you did it the naive way, you get the mistaken estimate that it's 25 hours instead of 24. That's the bottom line, all right? So I was feeling good about this until last year, all right? And this paper came out in Scientific Reports. And it said they had a data-driven, unsupervised time series modeling approach so you could estimate circadian rhythms and their properties from skin surface temperature in free living conditions. Promises everything. And not only that, they said they could divide people into 3 distinct clusters. All right, and so this provides, as they said, a novel basis for modeling and understanding the human circadian function in free living conditions. Now, just what were the limitations of their study? So the first one I put up there, they only used a single harmonic. And you saw that in the data that I showed you, you had to have at least 2 harmonics to describe the circadian pacemaker, and you had to have another piece there to actually, if you had the 28-hour day component. These other 3 points, they're their own. This is what they said in their paper about their limitations, not me. Look at the first one. It lacks measurements of light exposure, which would be a very valuable variable to include. I think so, right? The crucial question on how these various factors that they listed just above that, interact in circadian biology cannot be evaluated from the study design. And so I like the last one, though. It says, the concept of circadian period thus refers here to a broader concept of periodicity than that assessed in the controlled laboratory study. Broader concept? I mean, I think about how hard we worked to, Chuck doing those studies, recruiting all the subjects, curating the data, making sure the data were properly collected, and just obsessing about everything to get the results that I just showed you. But now, we can do it with just skin temperature, don't have to use any of the complicated models like we used, and it's a novel approach, and I'm sure it's going to have huge impact. And I actually looked through the article to see if Chuck's name appeared in there at all, Seisler, and it appeared once in a paper where he was like the 15th author or something like that. So none of his major work was actually looked at. And I just ask you the question, is this data science? All right? So let's move on to another topic, decoding the information. I guess the answer was no, right? Okay, all right. So decoding information from the information stored in a rat's short-term memory. So I'd worked on circadian rhythms for a number of years, and I decided to make a career shift. I decided to find another area to become involved in, and I thought about it fairly carefully about what areas I wanted to attack. I thought about genetics, I thought about the environment, women's health. I thought a little bit about maybe endocrinology in particular. And then I thought about brain science, and I thought I would get involved in neuroscience. And so through I had to retrain. I didn't know much about neuroscience at all. Even I've been to medical school and that sort of thing. So I took the summer course at Woods Hole in the marine biological laboratory. The Methods in Computational Neuroscience course was run by David Tank, who was at Bell Labs at the time, and David Kleinfeld, who was there then as well. And I mean, I just had to learn enough. I had to learn more. I didn't know enough to really enter this field. And then David Kleinfeld, we had to do a summer project. He said, why don't you work on the problem of decoding information in the rat hippocampus? I didn't even know what he was talking about, but I thought, okay, I'll study that. And it just so happens that one of the young experts in the field at the time had just moved to Boston, and that was Matt Wilson, right? He's now at MIT. And so the cool thing about the hippocampus, so the hippocampus, that's not where the hippopotamus go to school, all right? It's actually, it's a seahorse. It stands for seahorse or sea monster, because if you look at it, you can see where they've taken off the part of the rat brain there, and it looks kind of like a seahorse or a sea monster, all right? And so these neurons, actually, before I tell you that, there's another actor in this story who is Lauren Frank. And again, this speaks to data science. So at the time, Matt was on my list of people to talk to in Boston. And I didn't know enough to really talk to him yet. So I was teaching this course with Art Dempster at Harvard on statistics and physiology. And we devoted the second semester specifically to neuroscience as a way to learn neuroscience, for me anyway. And so I was learning things one lecture ahead of teaching it to the students. And so one day, we get this call from MIT, and it said, some folks from MIT want to come to your class. And I said, sure, that's perfect, that's fine, that'd be great. And it was Lauren Frank and Ken Blum, who were in Matt Wilson's lab at the time. And the reason they were coming was because MIT had no statistics department. And so they were looking for help with their hippocampal data. It's like, wow, this is perfect. So that's actually how I got involved with working with them on the hippocampus. And one of the things about the rat hippocampus is and the hippocampus in general, it's the area of short-term memory. So, and the rat hippocampal neurons have this really cool property called place cells. That is, as a rat runs around an environment, yeah, that might be a good idea. Thank you. Well, I'll just work out here. But now the mic's here. I'll just stay put. All right. So the rat hippocampus has this really cool property. That is, as an animal runs around an environment, neurons start to fire in very specific places in the environment. And they're called place cells or place receptive fields. And I can just show you that here. Let me play this little video here. So you can see there's a red area forming. You're going to see a white area forming. And the red area forming is where one neuron, every time the animal is in that part of the environment, the neuron is spiking. And then there's another neuron, the green neuron, which every time it's in the lower part of the environment there, it's spiking. And there's a white area. So you can actually see there are three areas defined. These are place fields. So the red neuron says, I'm kind of up here somewhere. The white neuron says, well, I'm kind of down here. The green neuron says, I'm over here. So it's a very simple question you could ask. If you had enough of these neurons, could you actually read where the animal was in its environment just from the spiking activity? Could you basically decode the information that it's showing you, all right? And so does the animal maintain a dynamic representation of its position in the ensemble spiking activity in the hippocampus? So here's what the experiment looks like. So what you do in the first part of the experiment, the encoding analysis, let the animal run around, just like it was doing. Runs around, runs around, runs around. And you record the spiking activity, all right? And then from that, you do that, let's say, for about 15 minutes. And then from that part of the data, you estimate the place fields, where are they located, all right? Then you take the last part of the data, the last 10 minutes, and now using the place field estimates, as the animal runs around, you estimate where it is in the environment just from the spiking activity. All right, so that's what we did. So we had about 30 neurons, and this was a big deal at the time, having simultaneous recording from 30 neurons. That was really huge. And so these are some of the results, just the pictures of the results that Matt had published in 1993 in Science, showing that this was feasible. So that's an animal running around. The black line is where the animal actually is, and the red line is the estimate, all right? So we did some work on developing a slightly better model. And again, this goes to, like, I was learning this stuff. I mean, I hadn't worked on point processes when I was a PhD student. It was something I learned just for this particular problem. So representing the ones and zeros, the spikes, as point processes is what we took on. And we needed some sort of state space model. So we just went back to the Chapman-Kolmogorov setup and Bayes' theorem for basically what we now call state space modeling. And using Bayes' rule, I want to get the best estimate of the animal's position given all the spiking activity. That sort of makes sense. And then what I'll have to do is I need some sort of one-step prediction. So I guess where he's going to be in the next time period. And then that becomes my prior, and here's my likelihood. And so initially we used an inhomogeneous Poisson likelihood, where we model the shapes of the fields either as Gaussian shapes or we use what are called Zernike polynomials. Zernike polynomials are orthogonal polynomials on the disk. And they're just like Fourier series on the line. These are orthogonal polynomials, not so much just because we're trying to get the shape of the field right, all right? So you work through that, and you end up with something that looks like a Kalman filter algorithm for point processes, basically. It takes as its inputs the spiking activity. It measures the difference between the spiking activity that's predicted and the spiking activity that you actually see. That's an innovation. You add that to the previous estimate, and then you get an update. And now while this looks linear, it's not linear because xk is also in lambda c on the right-hand side of the equation. So it's a little nonlinear equation to solve, but it's basically this. I wrote it this way. You can see that it has the same formula like a Kalman filter, essentially. All right? So here's the estimates. Here's the analysis of the fields. So there are two animals, animal 1 and animal 2. Animal 1 is column 1. Animal 2 is column 2. And then the Zernike polynomial fits. So there are 34 cells for animal 1, 32 cells for animal 2. And you see the Gaussian fit and the corresponding Zernike fit. They're similar. And the places like for the Gaussian fits where you see sort of two ovals, what we did there is we just fit two Gaussians because you could see there were two clumps of data, all right, that you had to account for. All right, so now these tell me for that neuron the probability of spiking given the animal's position. So now I've got this over an ensemble of 30 neurons. Can I now invert this with Bayes' rule and just estimate where the animal is? All right, so let's see. All right, so here we are. All right, so I'm going to show you the rat running around first. That's about the size of his head. The environment is 60 centimeters across, right? And actually, let me just do it this way. Sorry. I just want to show you the rat first. Okay. Here we go. He looks like he's on cocaine, basically, because these newer machines, this is nothing for them to run through this. But the green activity on the right is the spiking activity. That's where they threw little food pellets to make him run around like that, so you can. Cocoa Puffs actually works best, it turns out. All right. So, but that's the experiment, all right, and that's basically 10 minutes of data, all right. So let's start it back. So now let's look at the Gaussian estimate. So when I say Gaussian estimate, I mean I built the fields based on assuming a Gaussian shape for every field, all right? So here's that. And down below here, what you're going to see is the coverage probably. See, the animal's running away from the estimator, or there's lag, right? All right, but you can see that it's right in the area where he is, but it's not sort of right up on him, okay? And below, you see the red line down at the bottom where it says 39. That's the instantaneous coverage probability. If it's working perfectly, it would be 95%, all right? So it's not quite 95%. In fact, it's a good distance away from it, but it's not doing too bad, all right? So let's go back here. And now let's look at the Zernike polynomial one. So just the different shapes of the fields. And the coverage probability will be up top again. So that you can see both of them now. So the Zernike intersects much more frequently with the animal itself than the Gaussian one does. And the coverage probability, while it's not 95%, it's 70%. So he's doing better, certainly doing better. But what's interesting about it, this is only from 30 neurons. And this is a very naive kind of, no-frill statistical model. It shows you there's a tremendous amount of information in these neurons there. so that if you really take the modeling of it seriously, you can probably extract even a lot more. All right, so I'll stop there. So here's a summary. So the error for that time period for the two animals was around 7 or about almost 8 centimeters for the Gaussian model, about 6 and 5.5 for the Zernike model. The reverse correlation technique, which is just basically, it's an ad hoc procedure. I'll skip on telling you how that's actually done. But that's what Matt used in his analyses. He got an error of about 30 centimeters. And even in his paper that he showed, in the ones in Science, the error was about 30 centimeters for a very similar environment. So this was a tremendous improvement just by doing a little bit of statistical modeling, just to get the shapes of the fields right and something about the spiking activity, better described. And so we feel pretty comfortable to say that yes, the animal does maintain this dynamic representation. And then I felt like, there's one thing I forgot to tell you. So one thing Peter Huber told me, he said, find an interesting problem and try to squeeze all the methodology out of it you possibly can, all right? And I felt like that's what happened a little bit here with this research. We were able to develop this point process sort of state-space model framework and then use it not only here but on a lot of other problems. I just listed a few of them here. So I felt that this is the sort of thing that we as, in this case, statisticians and data scientists, should be doing. What I found is if I take real problems seriously, then first it tells me what the assumptions I need to make are. They're much more interesting than the ones I make mathematically. And then also, as a consequence, I usually find broad applicability, all right? So let's swing to monitoring depth of anesthesia, all right? So, and I put this up here like this on purpose, because this is how people talk. When they say things like depth of anesthesia, all right? So what is depth of anesthesia, all right? Okay, so and this is me trying to describe the way people talk about, and people, I mean anesthesiologists, right? Talk about depth of anesthesia. It's an inference being made by an anesthesia caregiver regarding how well a patient is likely to tolerate surgery. It's based on physiological measurements, heart rate, blood pressure, oxygen saturation, movement, the anesthesia drugs the patient has received, the anesthesia caregiver's practice, habits, and experience. That's depth of anesthesia, okay? There's another answer. A number between 0 and 100, computed from an electroencephalogram using the bispectral index, BIS. 100 means you're wide awake, 0 means you're in a profound coma, 40 to 60 is where you have to keep them. Isn't anesthesia easy? All right? So this is developed by the company Aspect Medical back in the early 90s. And that's how it's marketed. Even today, that's what you do. You keep someone between 40 and 60, they're well anesthetized. That's all you need to know, all right? So I thought it might be worthwhile kind of dig back into how they could have figured this out. So how does BIS work? No one knows. Because the algorithm is proprietary. It's a black box, all right? And in fact, one of the things that a lot of literature has been wasted on over the last 30 years or so since this came out is trying to guess what's in BIS, all right? So I went to the BIS, the current manual. The company now is owned by Medtronic. And here's what they said. So they have the EEG, which they take. They compute a power spectrum. They compute a bispectrum. And they compute two things, what's called new suppression, and they compute suppression measurement, also just a suppression measurement. They put that together somehow, and they give you a number like 40 that they're showing there, all right? So now, the spectrum makes sense because there's some frequency content. There's very strong frequency content in the oscillations, all right? Bispectrum may or may not make sense, but if it does, it's because you're measuring, are the frequencies coupled, right? Is there coupling between them? And you might think, well, as the system starts to organize because, you have these oscillations at very fixed frequencies, that things start to couple and move together, all right? Reasonable. The suppression piece is an empirical thing. You'd have to know what EEG data looks like. But when you go into a very profound state of coma, this is one of the signatures that you see, a burst and a suppression, a burst and a suppression. It's a very profound state of coma. It can happen with hypothermia, head injury, anesthesia. And so you're saying, well, if you're in that state, you're really deep. So that would be good to know. And then if you're completely flat, completely suppressed. So that's what the manual right now tells you is in there, okay? So one of the things that it puts emphasis on is the high frequency content in the spectrum, right? It looks at that it puts a lot of weight on that. And so these guys in New Zealand back in 2004 took data from patients who are under anesthesia and measured their bispectra, and they basically found that there was really nothing beyond what was in the power spectrum that was in the signal, essentially. If you had the spectrum, you pretty much had the whole thing, all right? All right. But BIS is predicated on using the bispectrum. They put a lot of emphasis on the fact there's coupling between the frequencies, during this. That's how they market their device. And they modified the upper frequency range, at least in the most recent issue of the manual, to say they look at frequencies between 14 to 30 hertz as the highest frequency, and they also look at the amount of low frequency synchronization. All right. I'm showing you, actually, I have to tell you one other thing. Hold on one second. All right. How is BIS validated? And that's interesting to, if this thing can produce this information, which is so important, how is it validated? This is one of 4 studies, all right? They had 38 patients, and they're randomized to getting 1 of 3 different doses of propofol. Propofol is one of our most used anesthetics. Rendered you profoundly unconscious. It's the anesthetic is unfortunately, responsible for Michael Jackson's demise, all right? And so now what they do is they have 6 leads of EEG, and now here's the stimulus. These are people who are coming for surgery. Nobody would volunteer for this, okay? They get a 2-centimeter skin incision, all right, to start the surgery. And it's at a very precise time. And they measure movement, all right? So the stimulus is getting a skin incision. Did the patient move? Then they look to see what did the EEG do around that time. So that kind of straightforward, nothing deep, all right? And then they looked at BIS. Oh, and that's the thing. They don't tell you how they calculate the outcome. They said they just measured the BIS. They looked at the delta power, so the power between 1 to 4 hertz. The power above, the frequency that divided the spectrum into the 95th percentile, and then the median frequency. So they had these 4 measures that they were computing. And I just wanted to put this little detail in there. So what they did was, so you have 2 groups. You have the people who moved and the people who didn't move, all right? Now you make some EEG measures, and your EEG measure in their case is the BIS. So they put that in a linear discriminant analysis, okay? A linear discriminant analysis. Then, after calculating the linear discriminant analysis, they plugged that into this formula. They did a logistic transform on it. They didn't do a logistic GLM. They did a regression and then plugged this in there. So that's why the numbers scale between 0 and 100, all right? I see you're believing a lot in this right now, all right? There was no separate validation set, and there's no separate test set. In fact, what they did was they had 195 patients that they had studied before. They added these 38 into them. They redid the analysis. So the predictions, the people that the model was fit to are the same people the model was being predicted on, all right? And here's their key slide. Look at the one up top. So this is their key result. See how the bispectral folks, the movers had basically higher BIS, right? They're more awake. And then the patients who didn't move had lower BIS. And then their area under the curve, their AUC, if you look down in the lower panel, is 0.81. Okay, so those are the results. So they had about 4 studies that were very much like this. This is the validation, all right? I'll just be frank with you. I think this research has set our field back 30 years. All right? And one of the big reasons is the first point here. It's a black box. No one knows what's being computed. So you either use it blindly or you ignore it or you're skeptical about using it. All right? And it's been shown that it can be misled by high-frequency noise. So for example, and this is why we have human studies committees, but there's a certain country, I won't name it, where they had medical students take muscle relaxants while being awake. And the muscle relaxants, when their muscles relaxed and they put the BIS on, the BIS went down. They're conscious but paralyzed, all right? obviously this is totally unethical. But this was to illustrate the fact that this machine actually reads change in muscle artifact and has nothing to do with EEG associated with someone's level of consciousness, all right? And then, this is interesting. So in a 2004 paper in Lancet, BIS was considered to be very effective against preventing awareness. In a 2008 paper, it was shown that it wasn't. All right, so it's not clear what it supposedly does. And then for two drugs, ketamine and dexmedetomidine, it doesn't work. It doesn't work in kids. And the other thing is it has a delay. Okay, so the person's waking up now, right now. So I just waited about 12 or 15 seconds, right? The delay here is sometimes 30 up to 2 minutes before the effect actually shows up on the monitor, all right? And then we estimated like what the use of, so the other thing is anything associated with the EEG, even the work that I do, people say, oh, in fact, I was in a meeting the other day with one of my colleagues, one of my neurosurgical colleagues. He says, you know, that BIS monitor you guys use. I'm like, dude, we're not using the BIS monitor. We have an EEG monitor. All EEG monitors aren't BIS. So anything associated with the EEG in the operating room is called BIS now, all right? So you can imagine what their opinion of it is. And we've estimated that even at our hospital where we have proper instruction on using the EEG, we have somewhere between 23 to 30% of the anesthesiologists actually use some form of EEG, at least the way that we're trying to teach it, all right? And all this starts because of two things. And I've presented this to you without any diagrams because that's how this is presented. Nobody's looking at data, all right? If you look at data here, just do some simple plots like I'm going to show you. These questions clean up pretty quickly. But I want to show you this conceptual issue. So what is general anesthesia? First of all, depth of anesthesia doesn't make sense. Anesthesia has like 4 components. You need to be unconscious. You need not to feel pain. You have to have amnesia. You shouldn't move around. And it has to be reversible, and you have physiologic stability. So if you think about what they're doing in these studies, they are putting in a painful stimulus and using a painful stimulus to infer whether or not you're conscious. And your cognitive neuroscience colleagues will tell you if you want to check consciousness, you have to do a cognitive task. Are you consciously processing something or aren't you? So the task, in other words, the definition is totally screwed up. So, and the other thing is, what they're really measuring is some measure of pain, what we call antinocioception. It's called antinocioception when you're unconscious and pain is still being processed through the body. That's called antinocioception as opposed to analgesia. It's a technical difference, but essentially it's a test of pain, right? They're sticking you with a probe, all right? Looking at some data cleans this up in 2 seconds, all right? Here's the deal. This is someone getting propofol, going through different stages of anesthesia. Without even going into details here, when you're awake, you have high frequency, low amplitude oscillations, all right? As you get down to these states here, which are states of coma, and you're unconscious, you have very large amplitude, low frequency oscillations. So anything with any kind of measure which would just track that is going to probably get you 60 or 70% of the way there to saying someone's unconscious. Not deep, all right? And you can see the bottom plots down here. These are the two that the BIS includes explicitly. They say they include explicitly, and you can see why, because if these are present, it says you're profoundly unconscious. All right, now, this is my favorite, ketamine. Ketamine really, really messes with the BIS. Really, this is totally cool, all right? So high frequency oscillation, you're awake, all right? All right, so ketamine says, I'm going to mess with you. I'm going to be profoundly unconscious. I have a high frequency oscillation and then a slow oscillation. A high frequency oscillation and a slow oscillation. It goes back and forth between that. Actually, it's really beautiful. If you look here, see the high frequency oscillation? There's actually a downward chirp. It goes down, goes to low frequency, then jumps back up, and does that. So if you give someone ketamine so that they're profoundly unconscious so you can operate on them, this is what the EEG does. So the BIS can't track this. It gets confused. In fact, it usually reads high. It usually says the person's awake, all right, when you know they're profoundly unconscious. And here's the other drug that it fools too. It's called dexmedetomidine. So the key part is right down here. At high doses of dexmedetomidine, you get the large slow oscillations, right? But if you shake this person like this, they'll wake up. So they're just sedated, all right? So every anesthetic, but remember, they said it doesn't matter what drug you use. If you get a number between 40 and 60, you're unconscious. And what they never thought about, they never looked at the data really, and never thought about the neurophysiology of the drugs. And this is the final one with kids. It doesn't work in kids. So it makes sense. If you build a model or an algorithm using like the 30-year-old and the 50-year-old and the 80-year-old, the patterns are completely different from what you see for the kids. But the thing is, you can just see this. I mean, this should never have happened to begin with, all right? It's the same spectral structure. There's a lower band, there's an upper band, but the region over which where they lie changes the function of it. It changes very, very systematically. It's not random at all. So this is all knowable, but what you can see is they never plotted any data. All right. So what's my summary here? So each of these anesthetic classes has a different EEG signature. They change systematically with dose, patient age, and physiological condition. So we recommend that everybody use the EEG to take care of patients, but guided by not this sort of rule of thumb, but using the neuroscience behind how the oscillations are generated and what their effects of the drugs are in the brain. And you can see these oscillations very regularly in humans as well as in animals. And if you take a problem, look, there are at least 3 axes. Let me just say it this way. You have to know the drug class, how much did you give, and then the age of the patient. There are at least 3 axes. So depth of anesthesia folds them arbitrarily into one axis and just assumes that all the drugs work, everything works the same as long as you get the same number. That's what's happening here, all right? And I think that it's very easy to see once you look, just plotting the data. I didn't go over any mechanisms at all. We could have a long discussion about that. Just plotting the data just shows you that. And you know who's losing out? The patients are losing out, because anesthesiologists don't track their brains very well. So what are you going to do? If you want to make sure that someone's anesthetized, you're just going to overdose them. Right? You're gonna, because nobody wants to hear this, oh, I was awake while they were operating on me. So you can just infer right off the bat the patient's getting overdosed, and they certainly are. But yet this is, and again, to put it into further context, this is the strongest EEG signal there is. It's stronger than what you see in sleep. It's stronger than what you see in, let's say, cognitive studies and looking at patients with epilepsy or these sorts of things, because there's no noise once the person becomes anesthetized. You're seeing dynamics coming directly from the brain. We have the strongest EEG signal around, and we don't use it as anesthesiologists. And as I said, the patients are losing out. So, again, I needed a counter story for this. So last Friday, I clicked my heels 3 times, and this email came, all right? It was from a CEO of an AI startup, and here's what he said to me. It says, using real-time data, we aim to develop an AI-based system able to predict real-time hemodynamic risks and present explanatory explanations of factors, contributions to that risk during general anesthesia. The informed risk prediction enables anesthesiologists to plan an appropriate course of action to avoid such risks and take best possible decisions for their patients. Right? And he says, to do this, we need some big anesthesia data. All right, so I folded all our data up and I sent it to him right then. Yeah, right, exactly. This happens a lot, and this isn't the first such email that I've received, and I'm sure there are those of you who received similar emails. I mean, what we see is data is not information, all right? And so as I was thinking about what to extract out of this and sort of keeping the science in data science, so don't let the ease of large-scale data collection and analyses change or overly simplify scientific questions to be addressed, all right? I think for those of us who are statisticians, it's incumbent upon us to help make sure that inference paradigms remain in place and don't get thrown aside just because we can compute things automatically. And I like to talk about the Box-Tukey paradigm. This is the way I learned to think about sort of scientific inference. The whole idea of exploratory and confirmatory analysis coming from John Tukey, and then Box's idea of iterative model building. And the same thing applies, I think, in where we are now with our, our data sciences, and I think this is something which is really can't be emphasized enough. Training and education are going to be key. I'm thinking about like experimental design for observational studies, because if you're thinking about it, a lot of putting together a data set or data sets is really, you're saying you have observational studies. Cross-training is really, really important as well, because the areas of expertise, training in some area of expertise along with, some area of data science. And then retraining like I did. I mean, I retrained. I had to learn. There was stuff out there I needed to learn that I didn't learn in graduate school, and I think that's going to be a continuing issue sort of going forward. And cross-disciplinary collaborations are essential, because we have to think about who is really intellectually responsible for the findings that we report in studies. So I'll stop there. Thank you.
Thanks a lot, Emery. Maybe we can keep your last slide, because I'll say amen to this.
Okay, all right.
We can invite questions from the audience. Or maybe while the audience is thinking, maybe I have a question.
Sure.
Do you know of cases where misuse of this has led to dramatic consequences?
I mean, I have to scratch my head to think of like dramatic consequences, but I think the fact that, so just to put it into perspective, we have 60,000 anesthetics a day, 60,000 surgeries in the United States. So there are like 60,000 surgeries per day in the United States. And at best, let's say 25% of those, there's some sort of EEG being used. And a high fraction is probably with BIS, because they have the largest market share, right? So we don't have to have like sort of these very like sort of egregious faults. There's just a huge fault built into the system that happens probably to at least 80% of the patients, or if not more, who are having surgery, and that just shouldn't be. So I think it's still quite an issue. A question here.
So trying to get at the big anesthesia data.
I think we're online, so I think if you can use a microphone.
Trying to get the big anesthesia data that the company is looking for. So you say that there's so many surgeries done a day and under anesthesia, of course, and some of them use EKG. Can we collect that data? Can we, it's clearly not an experimental setup, but can be used in some ways?
Right. No. So two things. It's easy to collect. We have electronic medical records now. But it should be done prospectively, right? Don't come to me and ask me for my data, without some, and I don't know if you've ever talked to an anesthesiologist before you've written me. I have no idea what the person understands scientifically. And I see a lot of this where the people write and say, oh, I've got a new classifier. Can I try it on your anesthesia data? I mean, that's what I'm talking about. In other words, the science is not there. And I think that's what we have to put the emphasis on going forward.
Thank you.
Brian.
Can I just speak loud? No. Thanks. That was really very interesting. Thank you, Emery.
Thank you.
I wanted to ask you, there are two things that came to mind. One is, first off, I don't understand Medtronics in this story, right? You'd think that they would want to make their algorithms better. So I find that the situation there a little bit puzzling. And in fact, to simply predict the BIS, given that you have a lot of data, one could imagine that you might be able to build a lookup table form to go and sort of deconstruct it.
Probably could.
Okay. And then the other question is, in thinking about mechanism, these measurements are kind of brain-wide measurements.
Right.
And I'm wondering if there's any spatial localization to the EEG contrast measurements that are also insightful.
Right. So just to respond sort of seriously to the first question, yeah, and in the spirit of full disclosure, we're working on better algorithms which could be used commercially right now, just to be frank. And as far as the second one is concerned, yes, my colleague Patrick Purdon has done a lot of work on source localization for like the oscillations. And he has a couple papers came out a couple years ago, and also one which will be coming out in a few months or so, basically giving us some idea of where the oscillations are coming from. And taking advantage of this data like we talked about last night, where you have patients that have electrodes implanted in their brains for epilepsy surgery, and you can get them to do a controlled anesthesia study on them to sort of learn about where the drugs are acting. So we actually know a lot, and we've also done the same thing like in non-human primates. So this is, to have an algorithm like this sort of dominate the market, and then people going, I'm not going to use it. I mean, it's just a travesty. I can't say it any other way. And I do believe, I honestly believe it set our field back. Because the things that I'm showing, just those plots, they should be in the head of every anesthesiologist essentially in the country and thinking about taking care of their patients, particularly the ones for kids. I mean, that's inexcusable.
Thank you for your talk. In the middle, you made a comment that when you have had a successful data-driven study, you've tried to squeeze out most of the methods from it in different studies. Do you have any practical tips of how we can achieve that?
No, that's a very good question. And what I found was, so I'll explain what happened in this particular case, maybe we can extrapolate from that. So what I noticed in the neuroscientists doing was they would spend all this time to get spikes, so ones and zeros. And then the first thing they do is they would smooth it, right? I'm like, dude, what, you spent all that time collecting it, why you just threw it away, right? And so I said, how can I just continue to keep the ones and zeros and do a regression? Or how can I keep the ones and zeros and run a filter? So that was point processes. And then just basically the GLM with a essentially logistic model to first order. And this had been known. I mean, if you go back and look at this paper in 1988 by, I'm forgetting his name, at Berkeley. I'll think of it in just a second. Brillinger, right, exactly, Brillinger, thanks. Brillinger had said do this. He said, he actually wrote this out in one line, and nobody else paid any attention to it. So, and then what I realized was there are a lot of other situations where we have zeros and ones in neuroscience. So behavioral studies, did the animal get it right or wrong? That sort of thing. So that's what I'm talking about. So essentially we had a paradigm, and then state space was very important because there's continuity in a lot of these things which is not taken into account. So that's what I'm referring to. And so there's a whole series of things that we did after that took advantage of that sort of, because the problems had the same model structure, essentially.
So can I ask you again about your last slide? You had this plug to education, and what does it mean to educate people in data science? Is something that we are struggling with. Is it statistics? It's computer science. It's everything. So could you expand? What are your thoughts about education in data science?
I think that's a good. So again, let me explain it by example. So I was on the NIH panel for the Brain Initiative. And one of the things we talked about was educating the next generation. In other words, the people who were doing quantitative work had to learn the neurophys techniques, understand how they worked, what the properties of the data coming out of that were. And it wasn't sufficient enough for just the neurophysiologists just to be there and just start using methods and not understanding them. So we have to create courses. That's why I gave the Woods Hole example. That was I was in that class. I was junior faculty. Everybody else was either a graduate student or a postdoc. It was just like, the 10-year-old in first grade, essentially, But we need to have, and with web possibilities now, these sorts of things are much easier to set up. But we can't produce these very complex algorithms, complex from a statistical standpoint, complex from a computational standpoint, but they're easy to use because all you have to do is feed your data in, and nobody understands what's going on. Because that's going to kill us. That's what I had in mind.
Steve.
I want to let's see if this works. Does that work? Yeah, whoa. Sorry. So I wanted to expand on that. The experimental design for observational studies is music to my ears because I'm an epidemiologist. The whole field is based on that.
Right.
And all of our graduate students take data science courses. Almost no data science students take our courses. And the question is, how does this not, and there are other courses given in statistics in this,
Right.
but it doesn't seem to be absorbed into the culture of data science, particularly coming from the computer science realm, that this is necessary. And so how does this, aside from just offering courses, the courses are there. And when I've discussed this, I'm often told, well, there isn't room in the curriculum. They have to learn these higher level techniques.
No,
so how does this become part of the culture of data science training to make what you have as number one on your list, in fact, a number one priority that might be taken in the first year?
I think we have to, in other words, we have to make it part of the required curriculum. I just don't see any way around it. And I see you have, I think Guido Ibbons is speaking later on today. I'm sure he'll have some comments on this also. But it just seems like to me, these people, when someone calls and asks me for my data set, right, they want to do an observational study. I mean, basically. I mean, that's what they're telling me. And I would say, do you have your observational study certification? I mean, that's what I'd like to ask. I mean, are you certified to do this, you know? And it's interesting because we set up a statistics institute at MIT about 6 years ago. And we started pulling together all the courses. We had a lot of probability courses, statistical inference, data analysis courses, all. I said, is there an experimental design class? And we finally found one in AeroAstro, right? Because, I mean, they have to do very well-designed, you know, experiments. It makes total sense. But I think we have to bring this out to the fore. And that's why I wrote it as number one. Because when people call me up and ask me for my data, they want to do an observational study. And I want to know, are they certified to do it? Russ?
So this has been a really fun discussion, and thanks for these comments. So you've lived through at least a couple of hype cycles around particular, you know, types of methods, and I'm curious how you think about, like, you know, for people in the audience who are thinking about, like, what do I, you know, how do I think about the latest, greatest method, and what should I take from it versus being kind of skeptical about, you know, the hype? I'm wondering how you think about that.
Well, I think you have to always have a healthy degree of skepticism. I think there's no way around it. But where I'm able to really get my head around it, at least conceptually, maybe not technically, but at least conceptually, is when they tell me what they want to do with my data. And, like, you know, they say, well, I want to study hemodynamics, and hemodynamics where, in the operating room, or hemodynamics in the ICU? And do you realize the hemodynamics are tightly linked to whatever anesthetics I give, right? And so that's the sort of thing that where with just a few questions you can usually debunk, you know, whether or not someone truly understands what they're doing, or do they have like a plan for a well-designed study, which is what I think. I just can't see how we can teach data science without the experimental design course being like a fundamental part of the program, because essentially they're observational studies most of the time. That's what we're saying.
Other questions?
One more here. One there.
Thank you for this talk. And I found it particularly interesting because I woke up in the middle of a sinus surgery about 8 years ago. And I actually found it to be not an unpleasant experience, surprisingly. I guess my question is, how do you set the so you have a decision problem here in terms of whether you want to give me more or less.
Mm-hmm.
And you know, how should we think about setting this problem up? What is the goal of a better BIS in terms of what outcome are you trying to maximize?
That's a good question. So let me just say the effects of the drugs, like the drugs we're talking about, like propofol or the ethers, right? They do look pretty much like this, okay? And I find it hard to believe that you woke up and your EEG wouldn't have shown some sort of indication of it. It's now next to impossible. And so what I would do is, you see the first large set of, see where it says alpha, slow alpha oscillations? I would dial you down to just that stage, because that's the stage where you're sufficiently unconscious that, you know, I don't have to worry about you waking up, but you're not overdosed, basically. So that's what I would shoot for. Now I can see that. I can see that in the panel there, and you see how the oscillation has high frequency oscillations and then it has low frequency oscillations. As we get older, we lose the high frequency oscillation. We'll have just the low frequency oscillations. So I'd put that in the context of how old you are and what I'd expect to see. And we've looked at enough patients to have a really very, very good sense of that. I want to teach the anesthesiologist how to read this and not rely on, I mean, to think that you could simplify this problem down to something which is just a number between 0 and 100 is an embarrassment, quite frankly. But however, understanding these patterns, in other words, I don't want you to just recognize the pattern. I want you to understand why that pattern comes about. How is it being generated by the neural circuits? Then when an anesthesiologist is taking care of you, he or she is really using neuroscience to take care of you as opposed to pharmacology. That's what I would recommend.
Earlier you said that this pattern may depend on your age also.
Mm-hmm.
So the anesthesiologist will have like a wide array of things that they need to recognize depending on your age.
But they're very stereotypical, that's the thing. It's not a large set. In other words, it's not one dimension. It's 3, maybe 4 dimensions. But it's very, very tractable.
One last question.
Yeah, thank you very much for the talk. It's a refreshing perspective that you're bringing. I'm curious on what types of arguments do you bring to the fore when you've got like your Vanderpool example, you're getting 75% of the prediction value out, but the deep learning model comes along and gets 98% out. Presumably the Vanderpool model gives a better explanatory example that you can use to infer the underlying processes.
No, that's a very, very good question. And, I would go with the Vanderpool because I understand how I construct it. I understand, what it means. And then, as sort of simplistic as this sounds, I would look in the residuals. What did I not explain? What did I miss? In other words, and then I think it is a fair question to say, is there something that the neural network model is telling me about the physiology that I missed? Because that's what I'm interested in. I'm not just interested in their fitting just for fitting's sake. I really want to make a scientific inference about the properties of the system that I'm looking at. So if they came out and sort of beat me, that's fine. That's great. But nevertheless, then you have to tell me what new science you figured out at the same time. Was there some sort of new pathway that you detected that we weren't aware of that we should now go and study? I need to know what the additional inference is, basically.
All right, we want to thank you, Emory, for a wonderful talk. Chris.
Look at the computer later. Thank you, Dr. Brown. So as we head into our first break, please take a moment and notice the name tags of the people around you. We encourage you to find folks that you don't already know and explore your shared interests. So if you've not had a chance yet, you can visit the registration desk to add your interests with little stickers or pens. There's a lot of different domains of scholarship represented here today. And what brings us together is that we're all building and using data science to learn something new. So enjoy the quick break, and we'll return in 15 minutes for our first set of lightning talks.
Okay, hello everyone. Thanks for coming back on time. My name is David Lobel. I'm a professor in Earth System Science here at Stanford, part of the Stanford Data Science, and I'm going to moderate this exciting session that we have. We have 4 lightning talks. By lightning, what we mean partially is that there's not going to be Q&A after each talk. We're going to save that for the end when all the speakers will come up, and we'll have about 15 minutes for Q&A at the end. So without further ado, we're going to get started with our first speaker, Sandrine Dudois, who is a professor and chair of the statistics department at UC Berkeley, as well as in the School of Public Health and Epidemiology. And she'll be talking about learning from data in single-cell transcriptomics. Sandrine.
Thanks very much for the introduction, David. And I'd first like to thank also Chiara and the organizers for inviting me to speak today. It's my first in-person conference. It feels a little odd, but it's really nice as well, so I'm very happy to be here. So yes, I will talk about learning from data in single-cell transcriptomics and present a little data science vignette in a biological context. So my group's work in this area was motivated by a long-time collaboration with the NILab at Berkeley, now at the NIH. And it's on the study of stem cell differentiation in the mouse olfactory epithelium. So one of the goals of this study in the NILab was to elucidate the molecular and cellular mechanisms that underlie stem cell-mediated development and regeneration in the olfactory epithelium. And this work has important implications in medicine, in particular to the prevention and treatment of neural tissue damage and degeneration. So think, for example, Alzheimer's disease. So our collaborators in the NILab focus on the differentiation of a particular type of adult tissue stem cell, the horizontal basal cell. And they use the p63 protein as a molecular switch. So under normal conditions, the HBCs will self-renew, but when p63 is downregulated, they will start differentiating into a range of different cell types. And we use single-cell transcriptome sequencing, or in short, Rna-Seq, to measure the expression levels of, on a genome scale and at the resolution of single cells in mice that were normal, wild type, and also mice that had the p63 gene knocked out. So this is an illustration of the different types of cells in the olfactory epithelium. We have the horizontal basal cells here in green. So normally they will self-renew, but when the p63 gene is downregulated, they will differentiate into a range of different types of cells, globospacial cells, and different types of neurons, as well as subsyntaccular cells. So here's, in a nutshell, what single-cell RNA-seq does. So you first isolate individual cells, then you extract their RNA, you chop off the RNA, and you sequence the little fragments of RNA. So you find all the different bases, A, C, G, U, and then you map the small fragments back to the genome, and the idea underlying RNA-seq is that the number of reads that fall in a particular gene region gives you a measure of the expression level of that gene. So our entry point here comes after much pre-processing. There's image processing, there's base calling, and sequence alignment. And after these steps, we can summarize the data from Rna-Seq in a matrix whose rows correspond to genes and whose columns correspond to cells. And the entries of the matrix are the read counts. That gives you the expression measure of, say, gene 1 here in cell 1. So single-cell RNA-seq studies gives you a great illustration of the range of questions that you see in data science, where you have complex data, where there are multiple steps of analysis, and where it's really important to have sound and statistical principles and methods to derive reliable and interpretable biological insight. So the data are complex in a variety of ways. Dimensionality, of course, we typically have large P, and either small n or large n. There's various levels of processing depending on where you enter on that analysis pipeline. You have various types of data in addition to the familiar matrix, X and by P. You have image data, you have character string data, you have graph data. We have data on data. For example, annotation data on the genes and on the cells. There are large technical biases, for example, due to batch effect from the sequencing run. Also sequence composition effect, like GC content effect. There's often low signal to noise and sparsity. In single-cell RNA-seq, a particular cell typically has up to 80% of its genes that have 0 counts. So our approach to this single-cell RNA-seq study follows a general data science workflow where we first try to understand the domain context and question. Then we frame and translate the domain question into a data-enabled question about statistics. We translate the question into statistics. So this is a step that's often overlooked, but it's essential, and actually it's far from trivial. And in this context, I like to think about this quote from Tukey: far better an approximate answer to the right question, which is often vague, than an exact answer to the wrong question, which can always be made precise. So in our case, the main questions that we're dealing with are: what are the groups of cells that we see in the olfactory epithelium? What genes are differentially expressed between these different cell types? What are the lineages and where they branch? And also what genes are involved in the differentiation process. So then, of course, there's the important aspect of designing the study to make sure that the question of interest can actually be answered with the data that we collect. It's so common to see obvious confounding problems in these studies. We also want to answer the question as accurately as possible given available resources, so dollars, biological sample, reagents, time. EDA is really important in this context to understand our data, its main features, as well as detect obvious problems with the data, so for quality control, quality assessment purposes. So it's really crucial to look at data to avoid garbage in, garbage out. So no matter how good your machine learning method, if you feed it garbage, you're going to get garbage. Data cleaning and pre-processing are also really important, and they often have a larger impact on the results than the choice of downstream machine learning method. So we spend an awful lot of time at that step. This is the typical entry point and comfort zone for statisticians and computer scientists. This is where we spend most of our time. Why? Well, because the rest is actually really hard and somewhat unsatisfactory for us that have math backgrounds. There's no cut and dry mathematical answers to these questions typically. And there's somewhat of an art actually in applied statistics and data science. And we really need to be immersed in the scientific context and have also sustained communication with our collaborators to make sense of everything that's going on here. And it's really important, I think, as statisticians to be involved in these other aspects of the data science workflow, because this is where the domain meets statistics, and we need to make sure that there's no disconnect between the work we do here and what's happening in the science. So in the context of the actual machine learning or statistical inference, we want to make sure that the method actually answers the question and that the output of the method are consistent with how the results will be used. In particular, it's good to think about the meaning of probabilities in all these methods. Where does the randomness come from? What are these sampling units? So there's a few caveats here. So it's very often to see hammers looking for nails, unrealistic modeling assumption, and I like this. I always say it in French because that's my background. But why make things simple when they can be complicated? So often the simplest approaches do quite well in these contexts. So this is a highly iterative and collaborative process, and of course something that's crucial throughout the process is software, good and reliable software. So here are a little bit more specifics about the workflow we've developed to address the question from our collaborators, so to study the differentiation of stem cells in the olfactory epithelium. This is more like an advertisement of the work that we've done, because I won't have much time to spend on any of these topics. Also, I've indicated here in gray font, gray characters, the name of the R software package that we've developed for each of these steps, and they're released through the Bioconductor project. So before we do anything, we look at data for quality assessment purposes. We also spend a lot of time on normalization. The goal of normalization is to adjust read counts to make sure that when we see a difference in expression measure, either between genes or samples, that this difference reflects the biological effects of interest and not some unwanted technical effects due to batch or to sequence composition, for example. So we've developed a range of normalization methods, ranging from very simple methods that just do global scaling within a cell to more sophisticated method like regression on unknown factors of unwanted variation, which we obtain through factor analysis. So this is unsupervised normalization. And we've also developed a framework for applying and assessing the performance of these different normalization methods to have a data-driven way of selecting an appropriate normalization method for a particular data set. So a very common task in these genomic studies is to cluster either the genes or the samples. Well, as you know, clustering is a very difficult problem, and it's a frustrating problem because no matter what, the data or the clustering algorithm that we use will get clustered, whether they're real or meaningful, whether they're replicable or how we validate them is another story. So you might ask yourself, why yet another clustering method? So actually what we're doing is not to propose a new clustering method, but a framework for applying and comparing a variety of different clustering algorithms, and then aggregating the multiple candidate clustering into a stable consensus clustering. So it's essentially an ensemble approach for leveraging the strengths of different clustering approaches and formalizing what people often do in practice, which is try a bunch of different algorithms and sort of try to compare the results and combine them. So this is a more formal way of doing this. We've also developed a method for merging clusters in order to navigate the trade-off between the resolutions of the cluster and also their replicability across data set. So the rest of the methods that I'll mention are more specific to the trajectory inference questions. So we've developed a method called Slingshot for inferring the cell lineages and their pseudotimes. So the first step relies on a cluster-based minimum spanning tree to infer the global lineage structure. So the number of lineages, whether you have 2, 3, 4, 5 lineages, and also where they branch. So we work on the clusters and then fit a minimal spanning tree to these clusters. And then the second step is at the level of the cells. And then we identify pseudotimes for the cells along each of the lineages using simultaneous principal curves. So the pseudotimes are essentially the locations of the cells on the lineages. They correspond to their to transcriptional time, so not necessarily chronological time. So this method allows us to identify any number of lineages, and also we can supervise the inference of the lineages by telling it which are the terminal states. So in our case, we know that we have neurons and sustentacular cells as terminal states, so we can feed that information to the way we build the minimum spanning tree. And then the next step in the process, of course, is to try to understand which genes influence the differentiation process. So we've developed a framework for differential expression that relies on the continuous nature of the differentiation process. So for this, we rely on negative binomial, generalized additive model. We can, by looking at the coefficients of the GAM, and contrast based on these coefficients, we can identify different types of differential expression patterns. I'm sorry, 2 minutes, okay, between or within trajectories. So I'll show you very quickly a few of the results. So we applied Slingshot to the clusters that we get from Rna-Seq, our ensemble method. And so this is a 3-dimensional principal component analysis plot of the cells colored by cluster. We fit a minimal spanning tree. We find 3 branches, 3 lineages, and then the simultaneous principal curves. And then we apply this NB-GAM approach to identify genes that are differentially expressed within lineage and also between lineage. This is very quickly just the GAM. So Ys are the gene expression measures, Gs are genes, I are cells, Ts are the pseudotime, and we use cubic splines to parameterize the mean of the NB-GAM. And we look at contrasts of the GAM coefficients to fit different types of differential expression patterns. So this is the types of, depending on what contrast we look at, we can look at differential expression within a lineage, like these blue lineages, which gene expression increases with pseudotime, or differences between the blue and the orange lineage. So just a combination of linear, just different types of contrast between the betas. And we've applied this to our olfactory epithelium data set. And these is an example of the top 200 differentially expressed genes within the neuronal lineage. You can see different clusters of genes that have different regions of activity early or later on in the lineage. And this is an example of applying a test for finding genes that are differentially expressed between lineages. And here we've identified 4 transcription factors that correspond to epithelial cell differentiation. So I'll just jump very quickly to the results. I won't have time to show all of the results, but basically by using this GAM-based approach, we can uncover the transcriptional programs that are active in each of the 3 lineages and find both known and unknown and previously unknown marker genes. So overall, we can also use the GAM and look at derivatives of the GAM to look at which genes increase now in expression. So it gives us the ability to address a broader range of biological questions. So it's really a flexible approach to uncover the transcriptional programs associated with stem cell differentiation. So overall, we found that Slingshot and this trait-seq GAM approach revealed that olfactory stem cells use divergent strategies to generate the major cell types in the epithelium. On the neuronal lineage, we have numerous step-like transition, but fewer gradual changes in the sustentacular and the microvillus lineage. So I'm out of time, and I'll stop here. Thanks very much for your attention.
Thanks, Adrien. So our next speaker this morning is Yuri Leskovitz. He's, as you know, a professor of computer science here at Stanford. He's also been a very active leader in the Stanford Data Science, so we all have him to thank in part for this Stanford Data Science existing. He's going to talk today about mobility networks for modeling the spread of COVID-19.
Super. I'm really excited to be here, and I'm amazed what has grown from what we started with Emmanuel a few years ago. So great, super excited. So what I'm going to talk to you today about, if it's going to show up, is actually a project that we started exactly 2 years ago. And it was my COVID lockdown paternity leave type project. So my daughter was born actually yesterday, 2 years ago. So this is what we've been working on, and I want to show this to you because it's a nice story. It will, the pandemic is now kind of over, so it will be kind of a good way to remind us what we went through, and I'll show you some results that we were the first to establish about how the pandemic spreads, how to reopen the economy, and so on. So that's the idea. So March 2020, right, exactly 2 years ago, the outbreak hit, and there were these drastic and severe measures, right? We went into the lockdown, social distancing, masks, we were disinfecting every piece of material everywhere, and so on and so forth, right? And then there was a huge number of unknowns, a lot of misinformation, disinformation. Here are some news articles. And of course, there was also quite a lot of protests later on, kind of people asking, do we really need this? This is worse than the virus itself, and so on and so forth. So when the pandemic started, in my group we actually did a brainstorming session and said, okay, how could we help? Can we stop what we are doing and help? So here's one example of a project that we did during the pandemic that actually had quite a bit of impact. And I would say that this is probably, in terms of number of human lives touched, I think this rivals, me building a recommender system for Pinterest with around 500 million people touching every month. This, I think, touched also a similar order of magnitude of people. So coronavirus, right, how do viruses spread? They spread through human contact, right? So the way you can think of this is that there is some underlying contact network that modulates the spread of the virus. And then, right, this virus starts somewhere, and through contact between individuals, it moves from one person to another, and this way how it spreads through the population. But the important thing here is that if you want to model the spread of the virus, you need to know what the contact network is, who is in contact with whom. And the problem is that this human-human contact network is basically unknown. So what epidemiologists or standard epidemiology tries to do, it says, oh, let's just assume the graph is fully connected, right? Everyone can infect everyone. That's kind of the most basic assumption. And that's one fact that makes this modeling hard. Another fact that makes the modeling hard is that the world is super dynamic and super non-stationary. So it's kind of changing all the time. And especially if you think about March and April of 2020, each day was brand new day in the history of the Earth in terms of how humans behaved, right? So it's very hard to build a model and then let it run because the world is non-stationary. So what we asked was, or what our premise was the following, was we said, if we can estimate the dynamic human contact network, then virus modeling will kind of be easy and will be accurate. And if we are able to do this, then we'll be able to ask and answer some fundamental questions like, is social distancing really needed, right? And for example, how should we reopen the economy as we ease back to normality? So the question was, how could we estimate hour by hour kind of real-time contact network of a population of, let's say, 100 million plus. And what we decided to use to do this was an innovative data source, which is basically the geolocation pings of different cell phones. So the way you can think of it, that basically for different cell phones, we know their locations. Right? And we had this data for 10 of the largest US metropolitan areas with combined population of around 100 million, and we had this data for every hour of the day. The data actually came from a company called SafeGraph that basically partners with application developers and then users of those application developers to give back the anonymized pings. And we also, not only that we know the locations of these cell phones, but also we would know, for example, where these cell phones are. And then we can look in other databases and know what is the square footage of that area, how long were they in that space, and so on and so forth. So what this allowed us to do was to build an epidemiological model that has two types of locations. It has census block groups. These are geographical areas between 500 and 3,000 people live, and points of interest, which are grocery stores, pharmacies, schools, churches, anything you kind of go to. And based on this, we built a very simple kind of SEIR type model where the graph of this, how people move, changed hour by hour. So basically for every hour of the day, we would infer how many people from a given neighborhood go to a given specific drugstore, to a given specific grocery store, to a given specific hotel. And we have about 500,000 of these points of interest and about 60,000 CBGs. And we use data from SafeGraph, US Census, from epidemiological literature, as well as from the New York Times. And just to show you an example how the model works, the first panel is mobility. The middle panel is number of infected people, and on the right-hand side is kind of how many people are infected in the Chicago metropolitan area. And you can see how, in the downtown you get a lot of infections, and then as people move around, it kind of bubbles up everywhere. So this is, and what is important here is that the model predicts who will get infected, right? What home neighborhoods people are from, and where will they be infected, at what point of interest. And right, we spent a few months basically working on this infrastructure and pipeline and the model, and the students were very worried. Is this going to work? Are we going to be kind of scooped and overtaken? What's interesting is that we our model only has 3 static parameters, which is probability of infection at home, probability of infection in a point of interest, and the initial fraction of infected population. And you can see that with these 3 static parameters, you can model very different trajectories in different cities in United States. This was the first wave of epidemic, and the X's, the dots, those are the measurements. That's the ground truth data. So you see the variance in those measurements or uncertainty is huge. Okay? So that's what we did, and now I want to give you some results of what was interesting. So the first question is, did stay at home really matter? I wanted to know this. Actually, it turns out, right, given how much we decreased our mobility, if we were not to decrease it, 32% of people would get infected in a single month. So here are different trajectories. Yellow is if we were moving around as if it was, end of February, and then the black is the actual mobility. Okay, so that's the first interesting observation. Another interesting observation is that you can now ask in what different points of interest do these infections happen. And here's the ranked list according to the risk, and it makes sense, right? It's places where people congregate close together for a long time, like restaurants, fitness centers, and so on. So these are all things that at that point were unknown, and we were the first to quantitatively demonstrate them. Another interesting thing you can ask is, how should I reopen the economy? So we were able to simulate what happens if you reopen restaurants at 20% of the maximum occupancy. What happens if you reopen drugstores at this other level of maximum occupancy? And this means you can very nicely trade off between the amount of business these places are going to get or they are going to lose versus the number of infections and the stress on the health system. And for example, if you would cap at 20% maximum occupancy, you would be able still to get about 80% of all the visitors, but you would only you would curb 80% of infections and you would lose only about 40% of the business. So these trade-offs our model allows us to do. And then another interesting thing was that we can also look at social disparities. In particular, poor were hit much more by this virus. Here I'm showing relative risk of infection between rich and poor neighborhoods in different cities. And the question is, why is that? And the explanation or the hypothesis at that point in time was that poor have so many coexisting conditions that then they get hit by the virus much more. Actually, what we were able to show through this data is that poor were able to decrease their mobility less than the rich, or people from poor CBGs decrease their mobility less than people from rich CBGs. So that's one part of explanation. But there's another interesting part is that poor went to places that were more crowded and they stayed there longer. So a single trip to a grocery store, the risk of a poor person getting infected there was twice as much as for the let's say, rich person, in a sense that they went to places where there was more people per square foot and they stayed there twice as long. Okay, so these are some of the interesting things we were able to build, and basically build a tool that allowed the decision makers to make, the public health officials to make decisions. We published this, we started the work in March, we finished in August, and then we worked very hard with Nature, and I think it was published in October. It was really work with 3 amazing Stanford students, Serena, Emma, and Pangwei. It was amazing in terms of the reception of these papers. We gave over 400 interviews and appeared on various TV channels at weird hours of the day. But what was more interesting, as I said earlier, is these results were really used by governments all over the world. There's an example of a screenshot from a Polish, I think, TV. Basically, that's the graph I showed you from our paper, but translated to Polish. In Japan, I heard that basically they showed our paper on TV and said, this is what we have to do. US state governors were referring to what we were doing, and even US Supreme Court briefings are citing our papers. We also worked with New York Times on a couple of visualizations that appeared through subsequent months for people to try to understand these risks. And we also built a decision support tool and worked with various counties and states to implement this for them to help them make decisions, especially with reopening the economy. So this is what I wanted to say and share a story about the research I was doing during the lockdown. So thank you so much.
Great, thank you, Yuri. Our next speaker this morning is Fio McKelly. Fio is a colleague in the Woods Institute of the Environment. She directs a center on ocean solutions, and she, among other things, collects data in addition to analyzing data, and the way she collects data is often to go scuba diving. So if you're wondering who the smartest person in the room is, you can consider that. So her talk today will be on harnessing the data revolution for ocean health and sustainability. Fio.
Thank you. Thank you so much. And good morning, everyone. Today I will present very briefly on the huge potential of data science to contribute to addressing some of the great challenges in ocean science and sustainability, and hopefully, conversely, by addressing those questions, also sparking advances and innovation in data science itself. And Drs. Cohen and Nakayama are here in the room as well today. So I want to start by asking the question, why ocean? Why the focus on ocean? So there's at least three major reasons. First of all, oceans are really important. They are a huge part of the life support system on this planet. They provide food, nutrition, regulate climate, support coastal and maritime economies. The second reason is that all of these key functions and services are threatened by warming, ocean acidification, over-extraction of resources, pollution. And then, so we're losing them, and the impacts result in loss of biodiversity, impacts on human health, livelihood, and lives. And then the third reason is that oceans are arguably the last frontiers for discovery. We know actually still very little about oceans. Dave was saying, I'm a scuba diver. I actually had the privilege of doing ocean exploration on deep sea submersible. I've done many dives in Alvin, which is the submersible that went down on the Titanic. And no, it's a life-changing experience, and every time we find new things. So it's super exciting. But it's also very costly and very slow. And so there's a lot to be learned in ocean. It's really the last frontier. And what has happened in the last 2 decades, it's a true explosion of data from buoys, from animal-borne tags attached to tunas and sharks and seabirds, from autonomous vehicles. And in fact, it's estimated that more data have been collected in the last 2 decades than in the previous 100 years. So this is sort of the beginning of sort of the examples that I want to show, because we are really seeing a huge potential that has no precedent. And what I showed in that chart is just a fraction of what's available, because new developments in genomics, in satellite technologies, drones, citizen science, social media are providing stream of data that open this huge potential for ocean discovery and contributing also to ocean sustainability. So I'll talk about a couple of examples of the kind of insights that this data revolution is providing for ocean health and sustainability. And one of the prime examples come from automatic information system. These are vessel tracking, satellite-based systems that are based on transponders that vessels larger than 15 meters are mandated to carry all over the world. And this is an anti-collision system. It's for safety, but at the same time, it's now providing information on the identities and positions of vessels in a majority of the world ocean every few minutes. And this is the map that you see here. So these data streams combined with machine learning also now allow discriminating different kinds of activities. For example, deep sea mining and fishing, and even different kinds of fishing, as you see here. So the result is a picture, a snapshot and an ability to track to time changes in what happens in ocean ecosystems, far from shore in places where direct observation can possibly provide this kind of information. For example, this is an image of the fishing effort globally in 1 year, 2016, that was provided through AIS data. So this is really important because for the first time, just in the last few years, now this was unimaginable before, we can do surveillance of large offshore protected areas. This data can inform fisheries management. For example, parallel advances in animal tracking. These are satellite tags that Barbara Bloch's lab at Hopkins Marine Station has developed, integrated with AIS data, have enabled the identification of hotspots of overlap of fishing activity with the essential habitat of endangered and threatened shark species. So here you see the overlap of different kinds of fishing gears that catch tuna, and then in plot B, they catch 7 different species of sharks, including threatened ones. And this overlap now can guide management interventions that can reduce the bycatch of sharks in a targeted way, for example, through temporary closures or gear modification. There's also vast room for advances, for new frontiers. And as an example, this is a project that's supported through the Stanford Data Science Initiative that was developed because of the Data Science Initiative, that is aimed at expanding the capacity of the current vessel tracking system by utilizing planet satellite imagery, high-resolution coastal imagery, to enable tracking of vessels that are too small to carry the transponder or that are dark, meaning that they illegally turn the transponders off. So this is a collaboration that spans ocean science, computer vision, statistics, data science. Very exciting potential. And then also the other frontier is taking this information all the way to promoting change in the water, improvement in the water. And one of the grand challenges that we're still facing in ocean is illegal and unregulated fishing. Illegal activities rob nations of an estimated 26 to 50 billion US dollars every year. They are pretty much the obstacle to sustainable management. No, without addressing, curbing this plague, there will be no sustainable management. They affect lives. They're connected to labor abuse, human rights violation. So it's a big problem. So in a paper that just came out today in Nature Communication, the team from Center for Ocean Solutions with other collaborators essentially combined AIS data of fishing effort that you see here on the left. This is 8 million fishing trips with information gleaned from expert opinion survey about the risk of illegal activity and labor abuse in ports around the world. Basically where these fishing vessels are going to after their trips, as a way of then tracking back the hotspot of illegal activity at sea, where fishing it has a high risk of being associated with illegal activity, which you see there in the map on the right, identifying 3 levels of risk, high, medium, and low. And you see hotspots of risk, for example, of West Africa in the Western Indian Ocean off Peru. So then the team is working with what have been called the key actors, the largest seafood companies in the world, the 10 major seafood companies, because their commitment to curbing illegal fishing can leverage this data to identify risk and work to eliminate these activities or at least decrease them through their supply chains. And then, I don't know how much time I have, but I want to transition to another couple of examples that focus on another problem, which is the open question of what's the contribution of blue foods, the fish, shellfish, seaweeds that are produced or harvested in aquatic systems to addressing food insecurity and malnutrition. So answering this question is very difficult. Data were scarce. And as part of an initiative that is called the Blue Food Assessment, that was co-led by the Center for Food Security and Environment and Center for Ocean Solutions here at Stanford, as well as Stockholm Resilience Center, the team had compiled information on nutritional profiles of blue foods from over 3,700 different species of fish, shellfish, and seaweeds. And so this resulting database of the nutrient content now has allowed analysis and comparison of the nutritional value of different aquatic species, for example, in comparison with terrestrial species. So in blue, you see the blue foods, the aquatic species, and then in green, terrestrial counterparts. And so this analysis for the first time are showing that there are several species of aquatic animals and seaweeds that are major contributors, have really high value in terms of nutrition, particularly in terms of calcium, omega-3 fatty acids, and calcium. And then, so the second question is, where are blue foods consumed? Where there's greatest reliance on blue food, and conversely, what areas might be targeted through policy interventions to action to bring the superfoods that have been identified to address malnutrition hotspots. And so these analyses, again, were enabled by big data that weren't available, accessible, at least in this case, up to a few years ago, and consist in the results of yearly surveys of fish and shellfish consumption in households every year across 50 different countries. So here, these data are often reported and visualized at the national scale, and you can see patterns of and hotspots of seafood consumption. But now access to this data at the household scale enables a much richer picture and shows, for example, that in some countries, high national level consumption corresponds to a relatively homogeneous consumption across the country. But there are instances, for example, India and Peru, where that low national level consumption actually masks very high heterogeneity with hotspots of high consumption and reliance of blue foods in these countries. And so now governments and development organizations can target specific areas with this more nuanced information, for example, with programs like school feeding programs or trade networks that can bring blue foods when, where they're needed. So I want to conclude by highlighting three key components of the challenge of bringing this data revolution, this new capacity, to ocean health and to ocean challenges. And these include continuing to support the collection and access of data in real time and at scale. The second pillar is supporting the analytical advances that transform this data in information, in understanding. And then the third and really important component is to connect the research and education to the need and use through partnerships, for example, between academia, government, industry, and civil society. And so I want to conclude with the optimism that Stanford Data Science and the new school focused on climate and sustainability bring as the perfect environment for what is really the essential ingredient of all of this, which is collaboration across disciplines, across groups, with external partners. And this is really echoing what other colleagues have said before me today. This is the key ingredient to make these major advances that we want and need to make for discovery and sustainability. Thank you very much.
Great. Thank you, Theo, and thanks to all the speakers for being so punctual, even a little ahead of time. So our next speaker is Guido Embens, and Guido is, among other things, a professor in the Graduate School of Business here, but he's also a director of one of the centers. We haven't talked much about the centers within Stanford Data Science, but at lunchtime there will be tables set up where you can be introduced to them. Guido is the director of the Causal Science Center, the Stanford Causal Science Center, SC², which began this year, and I'm told it is definitely the most exciting thing that's happened to him this year. So with that, I will pass it on to Guido.
Thanks. Thanks very much. So where's the clicker? Oh, it's right here. Thanks very much. It's great to be here. It was very nice to see the different talks so far and see all the exciting work people are doing. It's also a little humbling to see that the standards for slides are much higher in some of the other disciplines than compared to economics. So I'm sorry about that. So what I want to talk about is three things. So I just want to briefly talk about what I mean by causality, kind of what in economics and social sciences people typically focus on. And then I want to give two examples of research I've been involved in recently, looking at causal effects in settings where there are some challenges with that. So the first thing about what do we mean by causality? In the end, what I'm interested in is looking at what the effect is of some intervention, of some manipulation, where something is changed in the environment for particular units. And these units can be individuals, they can be geographic areas, they can be firms. But some units are exposed to some intervention, and they could not have been exposed to that intervention. And what we're interested in is the difference between what is in that literature sometimes called potential outcomes. So a very simple example is I may have a headache, I may think about taking an aspirin, and what I'm interested in is what the state of my headache would have been had I taken the aspirin relative to what the state of my headache would have been had I not taken the aspirin. Because the challenge is that I can't do both at the same time. And I can't ever directly measure these causal effects. And so we're going to need to have multiple units, multiple individuals, some taking the aspirin, some not taking the aspirin. And so that then creates challenges because the people who took the aspirin may be different from the people who didn't take the aspirin. They may have taken it by choice, and their headaches may have been worse. And so we need to worry about why some individuals, some units got exposed to the treatment and others didn't. And if we have a randomized experiment, we know exactly how that happened, and we're going to get a lot of leverage out of that because there we know it was purely by chance and it didn't have anything to do with systematic differences between these units. But in social sciences, traditionally, in many settings, we can't do experiments, and we face much more severe challenges in trying to come up with credible ways of estimating causal effects. So some of the things I want to talk about are about the challenges in those settings where we can't do experiments either because they're too expensive, because they wouldn't be ethical, but for whatever reason, we have to make do with observational data. And then the second thing I want to talk about is some of the challenges in experiments in settings that go beyond the simple type of experiments that Fisher and Neyman worked on in the 1920s and 30s, where you can simply divide a population of units into two groups, a treatment sample and a control sample, and you can compare average outcomes. In many settings where people are doing experiments currently, there's a lot of interactions, there's a lot of spillovers between different units, and that creates lots of challenges. So the first example I want to look at is a setting where we do actually have experimental data, but they don't answer the question we're interested in, or at least they don't answer directly the question we're interested in. And so we want to combine that with observational study data, and want to think about systematically combining the experimental and observational data so that we can get answers to the questions we're interested in, where the experimental data are not going to be sufficient for doing that. And so the hope is to both make the experiments more valuable by allowing them to weigh in on questions that they don't directly answer, as well as making the analysis from observational data more credible. And so the specific example here is one from a paper with Susan Athey and Raj Chetty, where we're interested in the effect of a childhood intervention, of having small classes for children on tests on educational outcomes. And so here specifically, we're looking at the effect
on test scores in 8th grade. So these small classes were early on in the children's educational careers, and want to see if there's some long-term effects of those. It would have been nice to do an experiment that measured these long-term outcomes, but that would have taken a long time because these are class sizes early on for these children, and we're interested in the long-term effects, but we don't want to have an experiment that takes 10 years to do. So we have two data sets. One experimental data set where children are randomly assigned to small or regular class sizes for which we measure outcomes in 3rd grade. So we have these 3rd grade test scores, and we get credible, precise estimates of the effect of small classes on 3rd grade test scores. Then in addition, we have observational data from a different location from New York, where we also know whether the children were in small or big classes, but now we have outcomes both for 3rd and 8th grade tests. And so what we see is that the results in New York are very different for the 3rd grade, where in the Project STAR experiment, we see an effect of the small classes that improves test scores by 0.2, and that's very precisely estimated. In New York, it looks like the small class sizes actually made test scores worse. And we think that that's probably not true, the true causal effect. We think that's because the children in the small classes were different from the children in the big classes. And so as a result, we don't really trust the results for the 8th grade either. There again, we see this negative effect, but based on these data, I would not think that the effect of small classes on test scores is actually negative. And so what we're looking for is a systematic way of combining these data from this experiment to figure out what the effect is on 8th grade test scores. And so what we do is essentially build a model. So here's a graphical version of that, kind of in the line of, in the spirit of the work by Pearl, where we think the reason we can't simply compare 8th grade test scores in the observational data is that there's some unobserved differences between the kids in the small and regular class sizes that affect 8th grade, that are also correlated with 8th grade test scores. Now, what the key assumption we're going to make, and this is not completely clear just from the graph, but the key assumption we're going to make really is that whatever that unobserved confounder is, whatever these unobserved characteristics are that make that invalidate the comparison in 8th grade test scores for in the observational study, that unobserved confounder is the same for the 3rd grade test scores. And so we're going to leverage the fact that we can actually extract the true effect for the 3rd grade test scores from the experimental data to figure out how to adjust the 8th grade test score results for the observational data, where we don't see them in the experimental data. And so at some level, the starting point is that we think the minus 0.118 is not a credible estimate for the 8th grade, the effect on 8th grade test scores, because we see that for 3rd grade test scores, the observational data don't give us the right answer. We think that the observational data have low internal validity, and we want to use the experimental data to improve that. So to kind of summarize the results there, what we do, the data we have are these 3rd and 8th grade test scores for the observational data and the 3rd grade test scores for the experimental data. The simple raw differences are not very credible, but we're going to adjust them using the experimental data. And what that's going to lead to is estimates for the 3rd grade test score that are now the same as for the experimental data. So you see that the adjusted estimates are the 0.201. And now applying the same adjustment methods, and I'll give a little bit more, though not a lot of more detail on kind of how I get to this adjustment. But we adjust the 8th grade test scores in the same way, and that gives us an estimate that is now positive of 0.057. Now, do we know that that actually works? Well, we do. And so partly it's because I actually lied earlier. We do have data for the 8th grade test scores in the experiment. We do know what the effect is there based on the experimental data, namely 0.085. We had not used that data. We put it aside in this analysis, and adjusted the data purely based on extracting the unobserved confounders using the third grade data, and then use it to analyze the 8th grade data, adjusting for that estimated unobserved confounder, that gives us an estimate of 0.057 that is actually very close to the 0.085. And so kind of the intuitive version of what we're doing there is we're taking the 3rd grade test scores, we're extracting from that what is driving the bias between the experimental and the observational data. We interpret that as the reason for the difference between New York and Project STAR, just the fact that there's this unobserved confounder that selected the students into the 8th grade and into the small and regular class sizes. Once we've estimated that, we use that as something to adjust for in the 8th grade data, and that gives us this adjusted estimate that is actually very close to the truth. And so let me, because I'm going to run out of time, let me skip the details there, sort of how we actually do that, but it's essentially what I said. We're extracting from the 3rd grade data what is driving this bias, and then we're using that to adjust the 8th grade scores. Second thing I want to talk about is sort of a project, and there's an area where there's a lot of interesting work going on about experimental design in settings where we're worried about interference between units. So traditionally, experimental design was in settings where the units are all separate. Whether I take aspirin or not doesn't affect somebody else's outcome. And so I can analyze units separately. I can divide things into a treatment and a control group. But in many settings where people are doing experiments now, in particular in online settings, there's a lot of reasons to expect that there's interference. Many of the companies that are doing experiments are marketplaces, are platforms that bring together different sets of units, and they structure the interaction between these units, but fundamentally they're exploiting the fact that they're trying to leverage the fact that these units interact. And so, for example, if the company like Airbnb offers some discounts on some rental properties, that's going to affect outcomes for other rental properties, because people are going to switch between some renting one property versus another. Or if a rideshare company makes it more attractive for drivers to work at a particular time, that's going to affect drivers who are not in the treatment group, because they're going to face more competition during those times. So in all those cases, we need to address the fact that there are spillovers, and these spillovers are often of first order importance. Now, so here's one way, and I actually put some references there from other people here at Stanford. We also have developed new experimental designs to deal with some of these issues. But so here's one particular way of dealing with that in a setting where instead of having a single population, we actually have multiple populations. So suppose we're looking at a setting where we have customers and products. And we could do an experiment, and we're interested in the effect of giving customers more information about the products when they search for these products online. And so one thing we could do is simply do a product experiment where we randomize products to the treatment group or the control group. The complication is that people may switch between treated and control products, and so simply comparing treated and control products wouldn't tell us what the average effect would be if we expose all the products to the treatment versus none. We could also do a customer experiment where we randomize the customers to the treatment group or the control group. Again, there could be spillovers there. And so one way of trying to deal with that, to address that, is to think of the assignment not as a factor, not as something where you randomize the population of customers or you randomize the population of products, but as a matrix where you think of the assignment as something you can apply to the product-customer pair. And of course, that's not possible in many in sort of brick-and-mortar stores where you can't give two people the same experience when they visit the store at the same time. But in online settings, we can give different information to a particular individual for a particular product relative to the information we give to a different customer for the same product. And so we can choose the treatment at the level of the customer-product pair. And so from that perspective, you can think of customer and product experiments as special cases where a customer experiment also has this assignment matrix, but every column in that matrix is the same. And a product experiment is an experiment where every row in that matrix is the same. But kind of once you set it up that way, it's sort of clear you can go beyond that, and you can actually decide to systematically create sets of product and customer pairs that you expose to the treatment. And that's going to give you the ability to compare different sets of control groups and get a handle both on the direct effects of the exposure to the treatment, as well as the spillover effects, as well as the effects coming from the interference between units. And so here's a very simple version where you can compare this green control group with the red control group and learn about spillovers within customers. But you can do much more complicated things. And so here, for example, a setting where we first split the products into two groups, and we do a customer experiment for one set of products and a product experiment for a second set of products. And that's going to give us a lot of leverage to figure out what the spillovers look like and how we would actually predict what would happen if every pair was exposed to the treatment versus no pair. So let me stop here and not get into trouble for going over time here. But thanks very much for inviting me to talk here.
Great. Thank you, Guido. So we now have about 12 minutes or so until the lunch break. And so I'm going to ask the four speakers to please come up and sit in front of a mic here. We have 3 mics. I'll put one back in a second. And invite questions. Is Yuri still here? No. Okay, then we only need 3 mics, I guess. So I guess I have a question, as you guys think of questions. I don't see any hands up, which I guess is for all of you in some ways. And going back to what Sandrine put up, kind of jokingly about why do something simple when you can do something complicated. But there is, I think, a general trend, which is that as these fields get more and more sophisticated, in terms of the methods fields like statistics, machine learning, and there's a lot of students in the crowd that are those types of students. They're needing to innovate on the methods, right? They're needing to find something unique about the data that will be, interesting for their communities. At the same time, as that frontier gets further and further, it becomes harder and harder for this, students like Theo students or my students to be able to implement, what was new 2 or 3 years ago in that field. So I'm just wondering, in all of your experiences, how have you advised students to find that sort of happy medium between doing something that's useful to the application area and doing something that is innovative? And I guess, it would be a different question from your different perspectives because you're all in different fields.
So, I'm happy to make some comments there. So in economics, there was a time sort of in the 60s to the 80s where suddenly there was concern that people started using more and more complex statistical models for analyzing data, to the point that people became very concerned that the results from those data analysis were not very credible. There's a very famous paper in economics with the title, "Let's Take the Con Out of Econometrics," that was all about the fact that people presented these results of these analyses kind of with great confidence and with very small standard errors, where really they were not very believable. The specific example was one where people looked at the deterrence effects of the death penalty, and people came up with these estimates that every execution would save 17 lives, plus or minus 1. And so it was clear that those results were very unreliable. And so in economics, part of the trend since then has been to rely on simpler methods and more credible methods, and be a little bit more modest and try to actually get better data and get more credibility that way, and away from some of the very sophisticated, complicated modeling.
Well, I think that's a really interesting question, an important question, David. When it goes back to the students, I think it really depends on what their interests are. I think there's room for all of these endeavors, but if you are a student who is genuinely interested in working in applied statistics or data science or whatever you call it, I think you should start from the question and not, not think I have this method, I want to fit it to a particular problem. It's the coolest theoretical method, all these bells and whistles. So it really depends on what the context is, what they're trying to do. So there's room for students who want to do theoretical research and try to work on sophisticated methods and prove optimality properties and whatever on it. But I think you need to really think about what question you're trying to address, what your goals are.
And just to follow up on that, so your communities, I mean, I think we'd already said this for econ, but your communities have become more receptive over time to students who are focused more on applied work.
Oh, that's a really good question. I was on a panel at the ASA, sorry to jump in. Oh, the ASA, the Joint Statistical Meetings last year, just about that, about, applied statistics in academia. I think it's taking time. Yeah. Gradually, we're more open to having junior faculty who are working on applied problem. It's harder, I think, to assess students and young faculty working in applied statistics, just because of the breadth of the discipline. We don't have the framework necessary for thinking about that. I think the same goes also for research in statistical computing. I think it's still somewhat misunderstood how to handle that. I think we're more open about it, but we have a long way to go about it. I've seen this when we hire, in faculty hires, it's very easy to find a star probabilist. Everybody agrees on that, and it's like, yes, let's hire that person. When we try to hire an applied person, it's much harder to come to a consensus about the standards we want, the expectations. So some room to go, some improvement.
Well, my field is marine ecology. Marine ecology, my training went through a phase of huge enthusiasm for experimental manipulations. Experimental design courses, everyone had to do experiments, and experiments became more and more complex and more elaborate and more rigorous, but also addressing questions like, what is the movement of that limpet over now? Because by necessity, then you focus on systems that are amenable to that kind of work. Those are not necessarily most important questions. So I think that I agree that question is key. Often the interesting questions come from cross-pollination from another field. For example, again, in my field, in ecology, meta-analytical techniques and then advances in meta-analysis that came primarily from medical and social fields have really revolutionized the kind of questions that are asked in ecology. Synthesis of experiments, then these in turn have really informed what experiments need to be done, what design. So that, I think that aspect. And then the last thing is that I think that there is a great need for specialists as well, those that really dive in deep and decide that that's their field, and then really make discoveries that have value in itself, or as part of teams bring that. So in part is deciding what is most interesting, I think, to students. But those are the things in my experience that I've learned through time.
Okay, great. We got a question here.
So I want to follow up on Sandrine's comments about exploratory data analysis and the importance of it. One of the things that we've seen in psychology, through this kind of decade of reproducibility crisis, is that students have become incredibly afraid to explore their data at all. Exploratory data analysis has become like a bad word, to the degree that it's very easy to get garbage in and garbage out. But at the same time, you do have to worry about exploration and the degree to which it can become circular in your inferences. So I wonder how you think about kind of threading that needle.
Between exploratory analysis or just...
Between exploratory analysis and p-hacking or other questionable research practices.
P-hacking, you said.
Yeah, p-hacking or circular data analysis. Like how do you ensure that you do correct exploratory analysis, but make sure that it doesn't sort of negatively influence the quality of the inferences in the end?
Oh, I see. You mean just data snooping and...
Exactly.
Right. Yeah. I think you have to keep in mind the goal of the study. I mean, in our case, the exploratory analysis just is basically to understand what's going on with our data. And oftentimes we find problems with the data. In the genomic context, that's what it is. So it's not so much for dictate what conclusions we're going to make for the data, but it's finding mislabeled samples. That happens all the time, or finding technical biases and so on. So it's not really to dictate what hypotheses we're going to test or what conclusion we're trying to. It's just more, what's going on. Understand what are the features of your data. There's a distinction. I can see that. Yeah. And just quickly, I was really happy to hear your comment about having experts. Because I think that's a danger we have in data science. And I go back to my experience in computational biology from 20 or so years ago. People would apply the same label of computational biologist to me, where my expertise is in statistics and my colleagues whose expertise is in genomics. And we contribute very, very different things to a problem. I think you need teams of experts in different disciplines to solve these problems, not one person that can do it all. So I think depth in whatever discipline you're interested in, depth in the domain, depth in computing and statistics. I think that's the key, be able to work together on these projects and find a common language, work at the internet. So thanks for mentioning that.
That's true in all disciplines, and that's where data science can just be very helpful in fostering these collaborations and bringing these specialists into the picture.
We have time for maybe one or two more questions. One more.
So I had a very quick question. First of all, thank you all for the very nice talks. I'm curious to hear your thoughts about the role of open science in all three of your fields. In particular here, I'm thinking about how the research you do is directly tied to behavioral choices or medical or policy choices being done, and how open science can actually be somewhat of a disadvantage. So for example, if you're trying to create models that can track illegal fishing, the more open you are about how those models work, the easier it is to circumnavigate them. Or this recent Nature publication talking about how models used to find drugs that are non-toxic can be reversed to recreate like famous neurotoxins. So how do you balance your obligation as a scientist to create open, reproducible research with some of the moral obligations that can come from the impact that open research can have on the world around you?
A nice simple question to finish us off.
No, that is a great question, and I'm very excited about the panel on ethics that we have today, because I think that those are the questions in illegal fishing or anything that involves human rights and human lives and health and all that is becoming increasingly important in marine science. No? A decade ago, someone like me would have not even thought about this, but now it's what we do daily. And so on one hand, the access to data enables this kind of analysis, but then it brings all sorts of problems and risks. For example, highlighting the risk of illegal fishing on certain vessels can put a huge risks the laborers that are on those vessels. So those ethical issues are at the very center of discussion in this field right now.
I think they would all agree it's a hard balance, and you have to really be thinking about that balance, because they're definitely, you don't want to just say blindly that you want to always be completely open. At least that's my experience. So that is also a good segue to the need for collaboration and the need to think about these questions of causal inference, open science. It's a good segue to the lunch, because we will have the 4 centers all represented, and you can go and find more about them, and that maybe is what Chris is coming to encourage you to do. I don't actually know where lunch is, so I'm going to hand it off to him. But let's thank again the great speakers.
Yeah, and a lot of thanks to you, David, for moderating that. So So welcome to lunch. We're going to head to the break and some quick logistics. So as David said, lunch is downstairs. It's on the second floor terrace. So if you go down in any way, go away from the library, take a right outside. During lunch, we're going to have tables set up for the different centers and also for our summer program in Data Science for Social Good. Give you a chance to meet some of the people involved, have a chat. So grab your lunch, meet some people. There's also space out on the balcony here if you want to come back up here and eat. So we'll see you back here in 1 hour, 1:15. Have a good break.
Test 1, 2. Lavalier check. 1, 2. Testing 1, 2.
All right, we're going to get started in a moment. I'm going to ask my Stanford Data Science leadership faculty to please join me on stage. We're going to have a panel discussion. So yeah, if you can just round of applause to motivate them to come on stage. We're going to... And Hito, that includes you too. So we're going to have the center directors and the faculty directors for Stanford Data Science join us. All right, thank you. There's even enough seats. So as I mentioned this morning, my name is Chris Menzel, and I'm the executive director for Stanford Data Science. For the next session, we're going to hear from faculty leadership for SDS and the center directors, and have a quick discussion around data science at Stanford and right now and where it's going. So to start, I think we're going to begin with our Stanford Data Science faculty director, Professor Emmanuel Candès. Emmanuel, take it away.
Well, thanks a lot for being here. I think what I've seen, I'm old enough to have seen a few emerging themes in my lifetime. I think data science is the first one that cuts across an entire university. That's the first time I see something like this, from humanities to medicine, from medicine to law, from law to sustainability. And I think it's well represented today, so I'm very happy to have such a broad participation. I think I don't want to say too much about Stanford Data Science because we want to hear from you mostly. No matter what we do here, people will do data science. And so I think the question we ask with the leadership of the university and among all of ours is, how can we make your life a little bit better? How can we do better work by being a bit purposeful about data science? And that's a plan for Stanford Data Science, which is, can we create a purposeful institute that does purposeful research and that helps everyone on campus do better work by creating a community of like-minded scholars who shared interests. And what we would like to hear from you is how we can achieve these goals. If there is time, I'm happy to talk about what we want to do that might improve your work at Stanford. For example, we are planning for a big, I don't know exactly how I want to call this. I'm going to call this a research instrument that is a large compute infrastructure for researchers at Stanford, on top of all the research centers that we started and the graduate programs and postdoctoral programs that were started. But I don't want to say too much. We want to hear from you. I think people will do data science no matter what. And how can we make your lives a bit better, the lives of being at Stanford a bit better, and how can we make our collective work a bit better? And what we've heard this morning is that collaboration is key, and that's what we believe in, and that's what we want to enable.
So maybe what we'll do is go down the line and have folks introduce themselves, who you are, but also what you do for Stanford Data Science. And then I'll have a first question after that, and then we'll open it up to questions from the participants. So, Hito.
I thought we were going to start on the other side.
So I'm Guido Immens. I'm the faculty director of the Causal Science Center. And so what we're trying to do there is bring together all the different communities at Stanford that are interested in causal questions. And so the principle causality is very important for lots of different disciplines, but traditionally people have done that kind of separately in their own disciplines. Some disciplines have been very focused on doing randomized experiments. Some disciplines have been very focused on doing observational studies. But there's a huge amount to gain from having these communities interact and see what they're doing. That's been incredibly helpful for me personally when I was a junior faculty. I started working with people in statistics who had a very different perspective on similar questions than I did. And so what we were trying to do here is make sure that these interactions happen regularly. And so we have the conference every year where we have graduate students present papers looking at causal inference either theoretically or empirically.
so that people in the different parts of the university can get some exposure to what all the different disciplines are looking at, what they're worried about, what they're interested in, and we can foster more collaboration between these different disciplines.
Okay. Margot?
Yeah, hi. So very nice to see all of you. I'm Margot Gerritsen. I'm one of the associate directors of SDS. I've been around Stanford for a while and worked on data science programs for some time as well. First as director of the Institute for Computational Mathematical Engineering, where we set up a master's program in data science too with statistics. And during that time, I also co-founded the Women in Data Science organization, which is a global organization now where we're reaching over 100,000 people, mostly women, around the world in nearly 100 countries who are really interested in joining data science, who are interested in staying and thriving in the area of data science and making a positive impact. And we support them and hope to inspire them by normalizing the presence of women in this very important field. You probably know that the percentage of women in data science in the United States, and it's the same in Europe and many other countries in the world, is very, very low. It's about 10 to 15%. And our hope is that through all the activities that we have, that we increase that significantly until we get to more of a critical mass. So when SDS started, I joined as associate director mostly to run WIDS, Women in Data Science at Stanford. We provide the central contents for this movement in the world, and it's been just wonderful to be part of a larger SDS community now on campus. So I invite you all to look at widsconference.org, which is our website, WIDSconference, one word.org, and join us.
Next, okay. Hey everyone, I'm David Lobel. So I'm the faculty director of the Sustainability Data Science Center in SDS, which we're calling SUDS. And the idea is sustainability issues are front and center on a lot of people's minds. We have a new school that you probably have heard focusing on sustainability and climate change. And there's a large community of people, working on these directly, but then there's an even larger community of people around campus that I think are interested and would like to have, some utility in that area. And we've seen this over the years and tried to engage in many ways with, in particular, the data science community on campus. And, as Emmanuel said, even without this center, that's happened and it would continue to happen. But what we want to do is really try to supercharge that and really try to understand, collaboration is an easy thing to talk about, but how do we actually help scale up collaboration so that we really are tackling the big issues and tackling them at a pace that will really solve things. And so we are just starting. We have a group of faculty, both from the sustainability side and from the data science side, thinking about how to get people to understand. There just takes a lot of time for people on the data science side to understand what actually are the questions that are interesting and useful. And conversely, it takes people on the sustainability side, quite a while to just even understand what is exciting, what is new in the data science world. And so we're going to try to facilitate those interactions, maybe fund some initial work and host events and people. So there is a little flyer out there if any of you are interested in the kinds of things we're talking about. In about a month, we're going to have a small event out on the Stanford farm, so it's a good excuse to see the farm if you haven't yet. But it's kind of a mixer to get started in terms of this center. Thanks.
Thanks. So I'm Russ Poldrack. I'm a professor in psychology and I'm one of the associate directors of SDS and head of the Center for Open and Reproducible Science, or CORS, at CORS.stanford.edu. So the goal of our center is really to sort of help science across campus become open by design. So basically to give people both the tools, mostly technical tools, and the incentives that they need to be able to do open science. And the idea is that there's really a broad landscape of both practices and incentives behind sort of why people either do or don't do open science. And so the first thing we want to do is build community by bringing people together, and also incentivize people to do it by offering awards. So we just had our second annual meeting a couple weeks ago, gave out awards to both faculty level individuals who've championed open science and to trainee levels, grad students and postdocs who have been, sort of pushing the envelope on open science. We're also doing a lot of training events. So we've had a couple of talk series. We have a talk series starting in a few weeks. We'll be sending out information about that in the next few days about sort of foundational skills for open science. And we have an affiliate program. If anybody's interested in joining us, feel free to reach out to me, and we're happy to involve you.
Hello, my name is Chiara Sabatti, and I am a faculty in biomedical data science and in statistics, and I am one of the associate directors. I am mainly involved in education and thinking about how we do data science education and how we communicate data science findings or not. So I have been involved with the summer program that we have run for the past 3 years, Data Science for Social Good. This is an 8-week summer internship where we have small groups of students tackling one real-life problems. In fact, we have partners often outside the university that come with data and questions. We also run an outreach initiative that is called Inclusive Mentoring in Data Science. Any of you who is a graduate student is welcome to participate. We have offered it once a year, and we match you up with an undergraduate from another institution that is serving preferentially a larger number of underrepresented minorities in data science. And one of our goals is to make data science more accessible, more visible to this part of the population that is not necessarily thinking about a career in data science, but could have a successful and productive one. And otherwise, I'm the cheerleader here.
Thanks, Kira. Hi, everyone. I'm James So. I'm an assistant professor here at Stanford. And I'm super excited to be helping to launch our newest center, which is on data science for health. We're launching in the spring, and we'll be having more activities also starting in the summer and fall. So I guess there are 3 goals for the center. The first goal is to really provide an umbrella and to enable collaborations foster collaborations among health data science researchers from all the different schools here at Stanford. What's really great here is that you have great data science for health research both in the School of Medicine and also in other schools like in the business school, in the sciences, even in the law school. Right? Oftentimes we don't hear about all this great work that other people are doing, so it's great to have this. One of our goals is to have these more activities and mixers and social activities to foster collaborations across different schools. And our second big goal is to also create more data assets and infrastructure that make it easier for data science researchers across Stanford to work on health data and to translate their insights. Right? One of the biggest pain points when working with health data, which could be genomics data or EHR data or imaging data or wearables, is often that it's actually hard to access the data. The data can be very noisy. It's hard to even just take 6 months to actually just jump through the hoops to get access to data. So we're trying to simplify that process and also create more common resources to make it easier for people to access the work with the data. And then our third goal, which we're very excited about, is also to work with these other great initiatives that complement existing efforts on campus to do outreach and education efforts, especially around data science for health, and also provide more mentorship efforts.
And I'm going to complete my description here because I forgot. First of all, in terms of education, there's 2 gentlemen sitting in the audience, John Chambers and Naras, who have been playing a fundamental role. And then they are mainly running the program that I want to mention, which is the data science scholars and data science fellows. The institute here is supporting partly these graduate students and postdoc, and they are from across the university. They all have a data-intensive component of their science. Some of them focus on method development. Many of them have really instead scientific questions in mind to address which they use a lot of data and a lot of different data technologies, and you will be able to see their amazing work during the reception at the end of the day. And we've put that at the end of the day as the highlight, so the whole day is working up to that. So hold on, your expectation gets better and better, and you'll enjoy.
That's wonderful. Thank you all. Oh, go ahead.
Not to take anything away from our keynote, who was a great.
So thank you all. Yeah, maybe just a round of applause for the. And you all really stole my first question for me in your introductions, which I appreciate. I was going to ask you what you're most excited about that you're doing in data science. You basically all answered that. And then I didn't hear the scholars mentioned, so I was going to mention them, and then Chiara did. So thanks for making my job easier. As everyone is thinking of their question for the panel, I'm just going to add on to Chiara's comments about the scholars. First of all, you'll see them here with little red badges under them. They might also be wearing Stanford Data Science shirts, so please bug them at the breaks. And please visit us at the reception to bug them even further. But the scholars and the fellows are really at the heart of a lot of the early career work that we're doing. We're trying to bring people together across disciplines. You all represent that intention, really. You know, we have people here from all corners of campus, and that is really the goal for Stanford Data Science, is as we talk about weave data science into the fabric of the university, it's to bring people who are doing data science together. So hopefully we all vamped and sparked some interest, and we're going to open it up to questions. What questions do you have for any of the speakers or for the panel if it's an open question? And we have microphones in the back.
Questions or
Yes.
suggestions?
We have one in the middle right here.
I'll just ask, just to be fundamental, how is SDS defining data science? Is it just analytics? Oh. I was just ask, how is SDS defining data science? And for the critics who say it's just analytics with a new name, what is your response?
Well, I mean, it's a process of creating data sets, of extracting knowledge from data sets, and of being able to communicate the results of the analysis to the public, to decision makers, or even your colleagues in an intelligible way. That's
the whole data life cycle.
It's a whole data life cycle, and it starts with data collection.
Yeah, hi. Thanks for this talk. Everything is wonderful. So one thing I was wondering is about data ownership and in the future of science. So like, for example, in economics, data sets from companies like Uber or Lyft or Airbnb are having a big impact on the field. And the main fuel for data science, obviously, is data. And that's shaped by what companies collect. And in a world where you have giant language models that require millions of dollars of compute costs to train, and companies have the biggest data sets, what is the role of the university in 10, 20, 30 years in creating data and balancing access to data for startups or individuals or the government, or so that companies don't get access to all of this amazing data alone?
I mean, I can speak to it from, as somebody who thinks about open science and thinks that transparency and the ability to reproduce, other people's science is really important. And it actually goes beyond data, right? It goes to compute, right? There's, nobody can afford to do, very few people can afford to do the kind of compute that it would take to train, a GPT-3 or whatever the newest one of this week is called. And so I think there are real challenges, and for the university and sort of knowing, what our place is. I think you're exactly right. I guess I'd be interested to hear the others' thoughts, but I think part of what the university has is the ability to provide people freedom to ask and answer questions that don't necessarily have to have a payoff next week, right? And obviously not everything that happens in, certainly companies like Google have research arms that allow people to do that to some degree, though you always have to worry about the degree to which they're going to decide next week that this isn't their strategic priority. Whereas, part of academic freedom is allowing people the ability to to spend their lives asking a question that, somebody, when they were hired, people thought it was interesting, but nobody else has to find it interesting or profitable, right? And so I think that's a really important reason why people would decide to come do an academic career rather than just going to work for Google.
And maybe I'll just add on top of what Russ mentioned is that, I think there are some really interesting and fundamentally new open challenges and questions that arise exactly because of the phenomenon that you mentioned of all of this data being used by large companies. Right? For example, questions like, how do you even quantify the value of the data, right, collected from different individuals? Right? Or how do you give individuals more control or governance on how their data is used? Right? So these are very fundamental, both ethical, social, technical, but also mathematical questions that we want to address here, right? And I think it's the place of researchers like Stanford to address some of these fundamental questions.
Yeah, just another thought. I think we have talked a lot, and I know that there's been some activity around strengthening the relationship with industry in a way that makes sense for the university. So getting more access to data, having researchers from them spend time in the university. I think going forward, that's going to be, more and more critical. And as you were asking the question, I was listening to the responses. I'm just thinking through all the different projects we have that are increasingly reliant on relationships with the private sector. And often what brings them to us is, some measure of our objectivity and our ability to influence, the community overall. Some of it is just their desire to do good things in the world and have something to point to. But a lot of it is, to be honest, is trying to have us get used to working with their data, have the students get used to working with their data, and then they can sort of benefit from that sort of knowledge. But, I think that it's just a very important thing that's going to get more important, but it's not going to ever be obvious exactly how to do it. I think you're going to have to be careful to be very clear about what the university is getting out of it and what we're bringing to it.
Yes, let me just add one more thing to that. I think these are big problems. As I'm editing one of the main economics journals, and there we insist in principle on data being available after we publish papers, but a lot of papers get published using confidential data from companies, and they can't be made available. And so we do publish some of these things, but it creates challenges, because in the end we cannot replicate these things, and we would like things to be replicable. And so we haven't really solved those problems yet.
I was wondering, in terms of education and training, the program you described, what has been most effective and what is needed next in data science?
I don't know what has been most effective. I think it's also early days. It's not that we have been thinking about training data scientists for a long time. And as Marc alluded, we don't even know what is data scientist. In many ways, the term data scientist has been defined as a job description. You can say that you apply for a position of a data scientist, or you try to recruit a data scientist. What I think we have tried to play with, it's a paradigm similar to what came up at the end of the previous panels, that we need experts in multiple fields to be able to work together. So there is, often we use the image of a pie researcher, somebody who is both broad but deep in multiple directions, so can understand the scientific question and can understand the methodology well. And that's maybe something that we aspire to, but maybe it's a little bit of a illusion that we can achieve that in the space of a master program or a PhD program. I think what we have tried to do is really to encourage people to be deep and very well competent in one area, but at least have the upper part of the pie, that is the ability of listening and communicating with others. So we have tried to cultivate setup where students from multiple different fields talk to each other. And
exchange information, and they will not all become super competent in everybody's field. They'll keep their identities as a marine biologist or a statistician, but they'll be able to communicate and cross-pollinate.
I'll just give one example rather than being abstract. I have a graduate student in statistics, and she's very, very smart. And on her own, she decided to start to participate to data science activities, and I saw her being transformed. I saw her blossom. Last summer, she led a team of undergraduates on the part of the Data Science for Social Good program, understand how the city of San Francisco, the San Francisco School District, should implement tiebreakers when they assign students to school so that there's equity in access to education, and she presented the finding to the San Francisco Unified. And I saw the enormous transformation in this young woman, and it was quite something to see.
Okay, I think we have time for one more question.
I have a question. So you guys are all in very broad disciplines. What's something you think your discipline does well that other places around Stanford could benefit from? Like, what do you guys do best that the rest of Stanford needs to get on with?
We love data.
Well, I'll start, I guess, and it's partly answering the last question and maybe partly answering your question, which is I think something that has worked well is, for example, ICME, which Margot, as she said, founded and helped run, and is one of the many successes that she's had. That created sort of this environment where you had students, and statistics has been very similar, where you have students that go out and look across campus for interesting questions. And there is this culture now of people like me who are in the sciences kind of welcoming those students, listening to them, talking with them for a long time. And I guess what I would say is empirically what we've shown is that our part of campus has really good questions, like really motivating questions. How do you feed the world? How do you solve climate change? That fundamentally is, I think, what our little parts brought to the table. And also, there is a lot of, as Fio mentioned in her talk, if you were here, like there's just a lot of data coming in fields that really historically were very data poor. So we have kind of those two elements that I think, our small part of the university brings to the table.
I want to make a plug. So I straddle psychology and neuroscience. I want to make a plug for psychology. And I think the thing that we do really well is to actually think about the nature of measurement, which I think comes from the fact that we're trying to measure stuff that we can't see, thoughts and ideas. And I should put a plug in for my colleague Neil Imram's course on measurement that he's teaching this quarter. And I think that, we often think of data science as being about the end where you have the data and you want to apply models to it. But I think thinking about measurement up front, because the nature of the measurement often places direct constraints on what you can ever even hope to do with the data. And I think that there's a lot of knowledge that's come from measurement theory, a lot of it out of psychology, that actually can be really helpful for thinking about the quality of measurements.
So coming from economics, economists tend to think a lot about incentives and how people are going to change their behavior when we change their environment. And so when I work with other disciplines, sometimes in consulting relationships, kind of, you can see that that's a perspective that's not always natural in other disciplines, but it can help understand what are going to be the consequences of different decisions. But there's just a huge amount of value kind of to having these different perspectives come to bear on important problems.
From an ICME point of view, so computational mathematics or data science, I would say that one of the things we do well is value the critical expertise of the domain expert. And we do not believe that we can just look at data without that domain expertise and really contribute well to a problem. And that is one of the interesting things of interdisciplinary research. I was going to actually say for earth sciences, I also have a lag in neurosciences, but that we have the best questions. But you already said this, so. So I think it's really important, in many applications to put the question central. You know, the question comes first, not the data. And so that's another thing that I would say.
Did you want to say? So I say from our perspective, we spend a lot of time thinking about how to translate the insights that we learn from the data actually back into practice, right? So that's also where it's different from just analytics. You know, one thing is about getting the insights from the data, but especially for our work in the healthcare setting, it's actually really important to think about how do we take those insights back and deploy them in practice, right? So we have an opportunity here to work with not just Stanford hospitals and medical school, but also with like so many industries, both larger pharma companies or smaller startups in this broader healthcare biomedicine space.
It's a good question.
It's a great question, provocative, and I noticed none of the statisticians said anything. I'm just going to say, if you're interested in not reinventing the wheel, I highly recommend talking to a statistician. So we're gonna break. I know there's more questions, but we're going to move on to lightning talk. So please thank all the faculty. So I'm going to invite them to enjoy the rest of the day and to invite down to the front the next set of lightning speakers. So there's room in the front if you'd like to sit there. And I'm going to introduce Kate in a moment. But just before I do, as everyone's kind of shifting around, who here builds data science tools or uses them to make new discoveries, new scholarship? Anyone? I'm surprised that you're not all raising your hands, but let's just say. And of those people that are raising their hands, who here has everything they need and knows everything they need to know? So now all the hands are down. So we'd like to hear more about what's missing, either for you or for your field. You can sign up for our mailing list to receive information from us, but you can also communicate to us through Data Science at Stanford. And we also, for the Stanford folks, have a Slack channel, Data Science. So look us up, communicate, and as we do this every year, we'll have maybe more to say. So with that, I'm going to introduce the PM Lightning Talk. So our session chair is Kate Mayer. I'm going to have her, just get started. Sorry, Kate, thanks.
Good afternoon, everyone. It's my pleasure to be here. I'm Kate Maher. I'm also from the School with Good Questions, apparently. I'm a professor in Earth System Science and part of the Sustainability Data Science Working Group. So it's my pleasure to introduce our first speaker, and this is Professor Brad Afron. He is a professor in statistics in the School of Humanities and Sciences, as well as a professor of biomedical data science in the School of Medicine. And I'm very intrigued by the title of his talk, which is Not Quite Reproducible Research. So welcome.
So, I get a little view this way too. So thank you for the introduction, and thanks to people for putting together this very nice day. It says not quite reproducible research. It goes back to a paper, very well-noted paper by John Ioannidis from our medical school, from our biomedical BDS department. And the title of Why Most Discovered True Associations Are Inflated, a very provocative title, and he gives good reasons to believe that, in fact, reported effect sizes, when you check them later, seem to retreat towards zero. And I wanted to give this talk because I read a very fun paper in statistical science and then looked it up by Eric Van Zwet and a bunch of co-authors, including our own Steve Goodman, it's called The Statistical Properties of RCTs, Randomized Clinical Trials, and it gives an intriguing explanation as to why this might be the case, and so that's pretty much what I'm going to tell you. And Eric's analysis followed from the good idea of going to the Cochrane database of systematic reviews. And the Cochrane Institute is people who do incredible good. They collect, in this case, some 8,821 z-values from randomized clinical trials. That is, the model is that they're seeing zi, and it came from a normal distribution with true effect size mu i and variance 1. So you'd like to know mu I, but you get to see zi. And what Ioannidis said really is you better guess that mu I is less than zi, closer to 0. And so the question is, if say we observe, say, zi equals 3.5, what should we believe about mu I? And here's the blue histogram is the histogram of the 8,821 z-values. And it looks pretty normal, but in fact it isn't really. It's got long eccentric tails. I've cut them off at about plus or minus 9. And the tails are heavy and rather irregularly formed. The black curve is a fitted smooth curve to the histogram, and I'll tell you where it came from soon. So so there we have, there's the histogram. We wish it was a histogram of the mu i's, but of course it's a histogram of the z i's. And then the idea is, well, let's deconvolute it to get at the mu i's. What does that mean? Well, we'll take the Bayesian model where we have some hidden prior density g of mu that's actually given the mu's. And for any one mu I, it comes from g, but we don't get to see it. We get to see zi normal mu I 1. And that is, it's centered at mu I, but it's got noise on it, plus or minus noise. And if we knew Bayes' rule, if we knew g, we could just use Bayes' rule to get the density of the posterior density g of mu I given zi, and there couldn't be any more argument about what that means, right? That's the answer. But we don't know g. We can't see it. And the idea is to deconvolve the Cochrane database and try and get out what g is hiding there underneath the z's. And that's where Neris and I come in. This is our wheelhouse now, so that we've written a paper on and have an CRAN package called Deconvolver, which does exactly what this is supposed to do. It deconvolves the z's to give the mu's, and presumably does a good job of that. And the paper is fun to read, and it isn't hard to use the package. So what does it mean to, here specifically, this is the only specific thing in this talk. The model used here is that the log of g of mu is a polynomial in mu, and it's a 9th degree polynomial in mu. It goes up C0 plus C1 mu plus C2 mu squared, dot, 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 plus C9 mu 9 to the 9th power. Why to the 9th power? Because the 8th power didn't work. Neither did any of the lower ones. You'll notice if I stopped at 2, I would be saying that the prior was in the normal family. So you need all those extra ones in trying to model the long tails of the z-values. And now, if I tell you in the second line there, it says C, that's a bold-faced C, that's 10 numbers, C0 through C9. If I tell you those 10 numbers, that specifies G sub C of mu, the prior, and that gives the marginal density F sub C of Z, which is the prior, which is G sub C convoluted with normal 0, 1. Just exactly what we think the model is. And now all we have to do is get the likelihood, that's in the 4th line there as a function of C, try all the C's and see which one maximizes the likelihood. And there's a little more to it because you have to do some regularization to avoid getting stuck, but that's pretty much what was done. And here it is. Here's the estimated Cochrane prior. And it's pretty normal looking itself, except it has long tails sticking out there. It's got a variance a little less than 1. That's the heavy red curve. And then the dashed light curve is the corresponding F. Of course, it's not, because each Z is a noisy version of mu, the dash curve is wider and lower than the red curve. And so it says there F of Z, and that's the curve, that's the black curve that was fit there. And do we think it's pretty good? Yeah, you can do a goodness of fit test, and it doesn't really pass, but it comes close, and with 8,800 things, that's usually good enough. Okay, so what? Well, now we have the prior, and now we can pretend that's the true G, and we can use Bayes' rule. And I will use Bayes' rule. And here's the red curve. The horizontal axis here is the observed Z value. At the far right, Z equals 4. At the far left, Z equals -4. The vertical axis is what we believe mu is. And the red curve is the median of the posterior distribution, 50% more or 50% less. And you can see what it looks like. The light straight line, light dash straight line, is the 45-degree line. If the red curve fell along that line, then Ioannidis would have been wrong, and there wouldn't be any regression to the mean. That would be the case. If you saw Zi equals 4, you should guess 4 for mu I. But that isn't the case. In fact, you can see that there is some regression to the mean. If you see Z equals 4, the red curve is about 3. If you see Z equals -4, the red curve is about -3. And the black and the two black curves are the 5th percentile and the 95th percentile of the posterior distribution. And you can see it's sort of like a translation family. Things seem to move up a parallel. So here's a rule of thumb. So you can interpret the Ioannidis hypothesis. If you see a Zi, the median of mu I is about 1 unit moved toward 0. So if you see Z equals 3.5, you ought to guess 2.5. If you see Z equals -3.5, you ought to guess -2.5. And that's a pretty good rule, I think. And so now let me go back a second. It says there, a hypothetical, suppose a startup pharmaceutical firm observes, they're just getting going, they've invested all their money, they have a new drug, they think it's great, they've run a phase 2 trial, and they maybe have 100 people total in it, and they get their Z value versus the previous standard of care, and it's 3.5. And they're pretty excited about that. And so what should they believe? And at that point, you have a choice. Well, of course you have a choice. And here's 2 choices. The red dash curve, the pharma company very rationally might believe that they don't care about the Cochrane database. They just have their own experience, which isn't very much. And they think that they're going to use a flat prior distribution across the whole all possibilities. And if that's the case, the posterior density is that red curve, which is normal. They've seen 3.5. The red curve is normal 3.5 with variance 1, which is just say it's the usual frequentist answer that would be given. And I think that's a perfectly rational thing for them. However, you might be a venture capital firm thinking about investing in them, and you might care pretty much about the Cochrane database as past experience, in which case you might use the formulas that we had before, the prior that we got for the Cochrane, and that's the black curve there, and it's a good deal less optimistic than the red curve. Its high point is about 2.68, I guess. My rule of thumb was a little strong there, but it's not symmetric. There's more downside than upside there. And I think both answers are perfectly reasonable in their context. It's not just pharmaceutical, not just venture capitalists who might feel this way. There's also the question of the, say you're the FDA. What do you think you're going to think about that? Or suppose you're just a reader of the New York Times, a regular. They always have, every Tuesday, they have tons of cases like this and people reporting things. What do you believe about that 3.5? The Cochrane database might be a better guess. So that's what I have to say, except to thank the organizers once again for a very pleasant afternoon so far, and particularly thank Chiara for all the work she did here. So thank you.
And I probably should have mentioned this. I think everyone knows we will have a question and answer period for our 4 speakers at the end of the session. So if you can hold those questions in your head until the end, we'll have a chance for discussion. So it's my pleasure to introduce our next speaker, Heidi Williams. Heidi is the Charles R. Schwab Professor of Economics in the School of Humanities and Sciences and a professor by courtesy of law. And Heidi's title is What Inventions Are We Missing?
Easy to be patient. All right. Thank you. I'll avoid getting in a fist fight about which field has the most important questions, but if you would like to talk to Hito and I about economics during the Q&A, we would love to answer questions. So I'm an economist by training, but my research is very interdisciplinary, basically focusing at the intersection of science and medicine and law and economics. And when I try to describe to people the question that I'm interested in, I usually phrase it as, what inventions are we missing? Which is, of course, an impossible question to answer, but that's, as academics, what we get to have a chance to try to answer. So, as an example, why don't we have a cure for Alzheimer's disease? Lots of people in the economy have answers to that question if you ask them. You can ask doctors, you can ask people that do basic science research, you can ask people that work at private pharmaceutical firms or people that have been investing in Alzheimer's research at the National Institutes of Health for decades. Many of those people will give you an answer that's roughly of the form, the science is just really hard. And so economics often gets kind of dinged as being the dismal science, but this is a case where what Hito said before about incentives actually gives a lot more reason to be optimistic. So from an economic perspective, I think we might think that the set of scientific problems that are hard today might be hard because we haven't invested enough in trying to solve them. And so as soon as you kind of allow for the fact that the state of the science today reflects past investments, it immediately opens the box of how can we use policies to try to change incentives and change investments that can make hard problems easier and make progress in areas where it's been stalled. And so that's kind of roughly how I frame my work, is in trying to use data to measure what I think of as missing innovations. So innovations that are scientifically feasible, but that for some reason the incentives just aren't there for them to be brought out to the real world to benefit society. And so given that it's a conference focused on talking about collaboration and why Stanford is a really special place, it seemed like a great time to go through an example where I can use Stanford as an example to talk about collaboration to illustrate one example of how I use data to try to get at these questions. And this is joint work with Josh Lerner, who's at Harvard Business School, and Carolyn Stein, who's currently a postdoc at CBER on her way to Berkeley. This particular project is trying to understand what affects the diffusion of academic discoveries out into the economy. So what makes a difference for whether you're a professor and you publish a paper that maybe some people read and maybe they don't, or whether that paper actually goes out in the world and makes an impact. So people have long tried to argue that universities are a really central source of both commercial innovation and economic growth. But when they've tried to make that argument, they've made it pretty indirectly. And in fact, there's been a lot of focus on why that doesn't happen as often as we would like to in practice. So from a policy perspective, this was a lot of the debate around what's called the Bayh-Dole Act, which basically tried to streamline patent and titling rights to try to encourage university inventions to get commercialized. A lot of the academic research has focused on the fact that in order for the very nascent stage at which academic ideas get disclosed in papers or patents to actually go out and make an impact in the world, it often requires people from the university to go out and work in that translational process. And there's a lot of concerns that maybe there's too few incentives for people to provide their human capital to go out and try to actually co-develop those technologies. And so in this paper, our focus is on a very simple question, which is whether academic discoveries that are otherwise the same but made at different universities have different propensities to spill out into having social benefits for society. There's a lot of variation across universities in whether there's how many patents there are, how many startups there are, et cetera. You could just think, well, some universities are more research active than others, and maybe that's what's going on. But it doesn't take a lot to look at the data and see that that doesn't seem like it really explains things. So if you look at Duke and Stanford, they have very similar research expenditures. They both have a medical school. They are roughly similar in a lot of dimensions of the faculty orientation of their research. Stanford has many more startups than Duke. And so you could say, well, maybe that's obvious. Maybe that's that we're in Silicon Valley. My example is going to suggest that it's not quite that simple. The way that we're going to get at this is looking at how faculty's propensity for their work to impact society changes when they move across universities, to try to get a sense of your research, some component of it stays the same, but whether it's spilling over in different ways to society might change as a function of where you work. And so the example that I wanted to talk about was an example from Stanford, which is Professor Carolyn Bertozzi. So this is one of the many discoveries that's come out of her lab. It's basically a way of doing better, cheaper, faster, more accurate tuberculosis tests. This was discovered in her lab together with a PhD student and a broader range of people. The PhD student was the first author on the paper. Bertozzi and her PhD student and another person from their lab were on the patent. And so oftentimes, especially in biomedical research, there's a very careful orchestration of disclosing in a patent at the same time you disclose in a paper, because academics want to have a publication but also need to have, intellectual property in order to have some incentive for people to come in and commercialize things. And it turns out you need to time those disclosures very carefully, because otherwise your publication invalidates your ability to get a patent. And so that idea of patent paper pairs is something you can measure in data. It's hard to do, but we're working on doing that. But this is a case where for a case study, it's very easy to come up with ways of finding those patent paper pairs. The idea that it was at the heart of that patent paper pair ended up getting embodied in a startup. The PhD student was named the founder of the company, together with Professor Bertozzi, who's also listed as a founder. The student was placed as the CEO. And again, this kind of illustrates this idea that the human capital of the people that actually do the invention is often seen as necessary in order for the idea to actually get developed. Bertozzi, in this case, was named chair of the scientific advisory board. Many people here are on scientific advisory boards. Sometimes that means more than it does others. From our perspective, it's, if your kind of lab is the one whose work is getting commercialized, you will often be on the scientific advisory board. Many other people will also be on the scientific advisory board, but it's kind of one marker of involvement of faculty in commercialization. So Bertozzi, before she moved to Stanford, was at Berkeley. And so you might think that moving between Berkeley and Stanford doesn't really matter. We're kind of in the same labor market. We're all exposed to the same kind of access to venture capital. We're very close to Silicon Valley. Bertozzi's kind of on record talking about how much her social spillovers of her work changed when she moved to Stanford. And so the way she characterizes her time at Berkeley is the graduate students were excellent, we were doing great science, but I found it hard to think about how to translate my ideas to the clinic. And then she talks about her move to Stanford, where she started 4 companies within 5 years of moving. And she kind of attributes a lot of this to, at Stanford, kind of students from different schools would come to her lab. She would talk with people at the medical school and get suggestions on different ways of thinking about the problems that she was working on. And that the work that she ended up choosing to do was kind of more closely interfacing with kind of the problems that are more in this translational area. So what do I want to illustrate with that example? Mostly it's just meant to say, I think where you work can impact the kind of work you do and whether it diffuses. I don't do qualitative studies, so this is not meant to be a compelling, example making a case for like any particular argument. It's just meant to be an example to motivate why where you work might matter. So we basically try to pull together data to systematically measure academic discoveries and whether they spill over into society, and to measure faculty that move across universities so we can test whether this seems like it matters kind of on a larger scale, not for a case study. So the academic discoveries we focus on are we take all of the data in the Web of Science data, which when I moved to Stanford, Stanford bought a license to the bulk Web of Science data. That's at the library. Everybody can use it. But it's basically all peer-reviewed publications along with some other things. We then track citations to those academic papers that appear in patents. If you are a patent nerd, you'll know that there's a difference between front-page citations, which are sometimes added by lawyers and patent examiners, and in-text citations, which are more often written by the scientists involved in the process. We can look at both of those because we figured out how to extract those both from the patent text directly. And then we can do things like linking academics to the startups that they make and their membership on things like scientific advisory boards to try to measure their direct involvement in the process. Okay. So next, we need to measure where faculty work, which should be easy, except that everybody has 30 affiliations that they list on their papers. So if you go to the Web of Science and you try to figure out where people work, it's pretty hard. Before I came to Stanford, I worked at MIT. I know Sangeeta Bhatia. She sat next to me at the MIT faculty meetings. I feel comfortable saying she works at MIT, but it would be hard to know that by looking at the affiliations list that you see on her papers. And so what we use as a proxy that's kind of assuming that faculty kind of reveal something when they post an email address on their paper, that you're kind of oftentimes listing the email address for your primary affiliation. So it's not that her primary affiliation is at Brigham and Women's Hospital, which in fact has a completely different technology transfer office and sort of different setup of incentives for faculty. Her main affiliation is at MIT, and her intellectual property goes through MIT. So you can go to this bulk Web of Science data, the XML data, extract the email addresses where they're available, which are mostly for the senior authors, kind of the final authors. That's fine. We're kind of interested in focusing on a sample of people that move that are research active. And this is a graph which basically says it turns out that method works quite well for determining when faculty move. So this is looking at among faculty that move once, by year, relative to the year that you move, what is the share of papers that are in your origin, your home university, relative to your destination? And so you could think email addresses are kind of all over the place, and there's legs in the paper publication process, and this is really messy. It's actually not that messy. So, when I moved from MIT, they canceled my email account. I started using my Stanford account. For a lot of places, that works pretty well. So it doesn't capture everything, but it captures a big sample of movers that we can analyze. Okay. So how many minutes do I have left? This is stuck at 9, so I just... 5? Great, perfect, good. Enough to talk about some results, great. So this is not a graph about the question of interest, but it is a graph that I think is really interesting and informative about what this kind of data can tell you. So this is measuring geographic locations of your citations to your work in patents. So again, the data is constructed by, let's take faculty that move and look at all of their papers that they publish in each year. And the outcome is your paper cited in a patent within 5 years of being published? And in particular, for this outcome, what we're looking at, is it cited by a patent in your origin location, kind of the geographic area where you came from, or your destination location, so where you moved to? So for me, moving from MIT to Stanford, citations from origin is citations to my work from people in Boston versus citations to my work from people in the Bay Area. And so this is nice in illustrating various aspects of the data. So this 5-year citation measure is important because most academic papers, if they get cited in a patent, get cited about 12 years after they're published. So legs are a really important part of the process. We choose this 5-year citation measure as kind of splitting the difference between we need some time for your ideas to diffuse, but if we waited around for 20-year citations, we wouldn't have any data to use. But what you can see with the blue line that's kind of declining, that decline is expected because for papers that were published the year before you move, 4 of the 5 years of your 5-year citations are actually in the place that you moved to. And so I'm gray shading the areas that are kind of contaminated years relative to the move, where those are years that are not cleanly like citations when you're in your origin location. And so what this shows is a variety of things, but one is, so you get more sites in the area where you live. That's not surprising. It doesn't look like there's a lot of concerns about matching. So, it could be my work is getting really heavily used by people in the Bay Area. So before I move there, they're really citing my work, and that's why I move. But in fact, this red line, citations from destination, doesn't tick up until after you move. And so it looks like the process through which knowledge diffusion happens at kind of a local level seems like it changes discretely when you move. The other thing that you can introspect on is that the blue dots after you move are higher than the red dots before you move. And that's kind of saying the people in Boston didn't really forget about me. They're citing me more than if I had never lived there. And so it's kind of giving you a sense that there's kind of a citation bump from moving because just more people know about you and your work, and that's kind of diffusing more in general. Like I said, this is kind of not the main purpose of our analysis, but I think it's useful for giving some mechanics of what happens when people move and how does knowledge diffusion actually happen. This is more along the lines of the actual analysis that we do. So the x-axis here is one parameterization of what's the difference between where you moved to and where you came from. And so when I talk to practitioners about this paper, sometimes they say, oh yes, it's like you're writing about the University of Chicago where good ideas go to die. So there's lots of great universities that are extremely research active that it turns out do not have a high propensity of their work spilling out into patents. And so what this is it's saying, let's parameterize different universities based on the average propensity of papers at that school to be cited in patents. And so if we take, as an example, I moved from Chicago to Stanford, that's a big move in the sense that I'm moving to a place where commercial spillovers on average happen much more. Whereas if I move from Stanford to Chicago, I'm moving to a place that on average commercializes things less. That's essentially what the x-axis is. And so the fact that this is upward sloping is saying, if I move to a place that on average commercializes more, my own work is more likely to spill over into patents as well. And if I move to a place that commercializes less on average, my own work also spills over into patents less. Okay? So that slope is about 30%, 0.3, which is telling you that about 30% of the geographic variation in whether academic papers are cited in patents looks like it's explained by where the discovery is made, where you work. Okay. So, of course, there's an 80-page paper, lots of other things going on. I would love to talk to anybody who's interested more about this work. But basically, it's just one way of saying, what inventions are we missing? I think this kind of result, to me, suggests universities have different propensities to kind of have the discoveries at their universities spill over into the economy. And so as we think about kind of what are the latent discoveries that are not realizing their social impact, these kinds of estimates about place-based factors I think can be really important as an input into that. So most of my previous work had been focused on what happens when the patent system is poorly designed and what happens when the NIH grants are kind of designed poorly. And all of those I think are also important. But I think this idea that where you work might really matter for whether your ideas have a social impact is important in a lot of dimensions. So thank you for the opportunity to present.
Thank you, Heidi. So our next speaker is Phil Marshall, who is a senior scientist at SLAC, a national accelerator laboratory. And he's going to tell us about scaling up astronomy at the Vera C. Rubin Observatory. Welcome, Phil.
All right, thanks very much. Nice to see you all. It's my first live talk in 2 years, so I'm actually feeling a bit nervous, so bear with me. Okay, so I'm Phil Marshall. I'm from the Kavli Institute for Particle Astrophysics and Cosmology. Some of you know it, some of you don't. It very helpfully connects the physicists and astronomers at the physics department on campus with high-energy physicists like me up at SLAC. And it's been really great for more than a decade now at doing that. Here are some of the names of the people I work with at KIPAC on a particular measurement we're trying to make in cosmology. I'd say we may not have the best questions, but we certainly have questions that are both fundamental and fun. And so I wanted to show you a little bit about what we're doing with in data science at KIPAC. So let me see. Button press. The big green button. Okay. Okay, so fundamental and fun problems. You may not have caught this from the news over the last few years, but the universe's expansion is accelerating. Nobody knows why. It's a bit odd. What goes up must come down, except when it comes to the whole universe. So one of the things we're trying to understand is dark energy. What is it that's accelerating the expansion? Another thing we're trying to figure out is what is our galaxy made of? Turns out 90% of the mass of the galaxy is in dark matter, and we have no idea what it is. So we're trying to take astronomical data and ask these hard questions, or rather make the measurements that will inform the theorists who are coming up with the ideas for what might be going on out there in the universe. So we are about making accurate measurements from large amounts of astronomical data. And at the moment up at SLAC, we're very much focused on Rubin Observatory as a source of data for us in the next decade. We've been busy building the world's biggest digital camera. There it is. 3.2 gigapixels is in the lab up at SLAC. It'll be shipped next year to an observatory on a mountaintop in Chile. That's the Rubin Observatory. What will we do with Rubin? Well, it's a wide field camera attached to a telescope with a very big mirror that can collect a lot of light. Makes it very fast at surveying the night sky. So for 10 years, 2024 to 2034, we'll repeatedly image the entire southern sky and build up an 800-frame movie of the sky in 6 optical and near-infrared filters. All that imaging, hundreds of petabytes of pixel data, every night and then once per year for annual releases, we'll run automated measurement pipelines on those images to make trillions of measurements of billions of objects, stars, galaxies, supernovae, everything. We'll see the things change with time. There'll be time series for everything. It's a huge database for everybody to mine. So people like me and the others at KIPAC, we're building data scopes to observe this database, essentially. Okay, to give you a flavor of the kind of data we'll get from Rubin, here's a small patch of sky. That brown stripe is supposed to represent a hair held at arm's length. Look at all those galaxies behind a hair. There's a zoom in there. You can see next to the hair there's a funny-looking object, some blue arcs arranged around some orange blobs. The orange blobs are massive galaxies. The blue arcs are distorted images of a background galaxy that's being gravitationally lensed. These are rare objects, but they turn out to be very useful for studying dark matter and dark energy. Okay, so here's a picture of gravitational lensing in action. On the right, there's an image of what you see in the sky, 4 images of the same background bright point source, an active galactic nucleus in this case. Those are interesting to us because they flicker, and the flickerings arrive at the telescope at slightly different times, maybe offset by a week or two. We can use those time delays to measure the distance to the massive galaxy that's doing the lensing. And that distance is what allows us to make accurate measurements of the expansion rate of the universe. So we're interested in measuring time series, measuring time delays, using them to measure distance. We can only do the distance measurement if we model the mass of the galaxy extremely accurately. Not just weigh it, one number, but map out where the mass is, how much dark matter there is, how much stellar mass there is, and do that very accurately. Another thing we can do with gravitational lenses, we can look at those blue arcs and look at tiny little perturbations in their brightness around the arc, across the arc. Those little perturbations we think are caused by clumps of dark matter. No one's ever seen any dark matter, but we see it gravitating, and we think it forms small clumps, smaller than galaxies, that make little differences to the arcs. And so one of the things we want to do is build up samples of lenses that we can use to probe this clumpy aspect of dark matter, and through that get a handle of what it might be. All right, so Rubin will give us large samples of lenses, maybe 10 to 100 times more than we have right now. And so that's our own big data problem. In fact, many astronomers will have the same big data problem coming from Rubin. The samples of objects that they're interested in will suddenly get very much bigger, and they'll have to change the way they do their data analysis. So that's their own big data problem. Why do I say their own big data problem? I think all big data problems are personal. If you've had to change your analysis approach because of the velocity or the variety or the volume of your data, you have a big data problem. Here we are in group therapy for our big data problems. Okay, so we're trying to analyze much bigger samples of lenses, but not compromise on the accuracy of the modeling. So can we use deep learning to do this? We think yes. So here's what we've been doing the last couple of years. We build training sets of synthetic gravitational lenses and train various deep learning networks to do the inference that would have taken a few days before, grinding through the forward modeling with MCMC. We now try and make neural posterior estimates in under a second, and then spend more time trying to make accurate predictions with those, so we don't get the huge speed up. But we're asking, can we get orders of magnitude in speed up, computation time, in order to approach these large samples? When we make the training set, we have to make some choices. We have to make a model of the galaxy population in the background and also the deflector population. And we'd like to not to have had to have made those choices, but since we did have to make them, we're going to have to live with them. And so a lot of what we do is try and tackle the problem of unrepresentative training sets, try and hierarchically infer the populations of galaxies at the same time as the cosmological parameters we're interested in. So here's a PGM sort of high-level probabilistic graphical model for what we're trying to do. We have cosmological parameters on the left. One of them is called H0. That's the current expansion rate of the universe. But we also have hyperparameters that describe these populations of galaxies. And then we're trying to work with image data, so high-resolution images of these gravitational lens systems, also measured time delays coming from the time series. Here's an example of one of the tests we've done. This is Ji-Won Park and Simon Bira. Simon's here in the audience somewhere. They made a little test set of 200 mock LSST lenses, as might be discovered by Rubin Observatory. We imagine that each of them has a measured time delay and some high-resolution imaging. And the question is, can we model them with Bayesian neural networks without introducing bias in H0? And in this test, the answer seems to be yes, that was good. Why do we phrase the question like that? Turns out there's some skepticism in astronomy about machine learning, and can it really be used to do principled scientific inference? And that turns out to be the same question we have. We want to do things right as well. And so a lot of what we've been doing lately is using these new methods and just checking that they really can give us the accuracy we want as well as the speed up we need. We've been using graph neural networks to try and understand the catalogs of galaxies in the vicinity of these strong lenses. It turns out all of those galaxies along the line of sight can perturb the gravitational lensing effect a little bit, and we have to take that into account. So we have to model the environments of lenses, and the question is, can we use graph neural networks to use more information from the catalog than just counting up the number of galaxies to see whether it's an overdense field or an underdense field? This seems promising as well, that we get some increase in precision from using those that extra information. And so far, we haven't introduced bias by doing the inference fast with deep learning. Here's Sebastian Wagner-Carreno, one of the SDS grad fellows. He's been working on the dark matter problem, and he sees it as a sort of extreme hierarchical inference problem. Imagine a gravitational lens system where just in this little postage stamp image, there may be 1,000 clumps of dark matter in the lens, and another 1,000 along the line of sight of the lens, and you can't see any of them. But they cause little perturbations to the rings, and we want to understand the statistical properties of that population of dark matter clumps. And so he's been trying to use, again, samples of 10, 50, 100 lenses, see whether we can back out the population of parameters or hyperparameters that describe the population of clumps without introducing bias. And so far, so good. there's a small amount of signal coming from each lens. The combination of 100 or so give you fairly tight constraints on the population. That's the bottom figure is some illustration of the population. Again, we're getting there without introducing bias, and so he'll keep investigating this. Encourage you to look at his poster later on today. Okay, so that was a whistle-stop tour just through the strong lensing work at KIPAC. Just some comments on what we're trying to do with Rubin. These inference problems in astronomy are generically hierarchical. Why is that? Well, we only get to see each galaxy at a single point in time from a particular orientation, so we have no choice but to try and understand fundamental astrophysics by building up large samples of galaxies that we see from different orientations at different points in their evolution. Then we're interested typically in a small number of hyperparameters that describe populations, whereas we have huge numbers of nuisance parameters that describe individual objects, which look pretty but aren't actually of intrinsic interest on their own. Strong gravitational lenses are interesting not just if you're trying to tackle the particular questions I'm interested in, but because they're hard to model. They have this non-linear lensing effect, so their careful modeling is needed. So our hope is that by solving the hard lensing problem, it will make it more straightforward to tackle easier problems around astronomy. And I guess our conclusion so far, after a couple of years of exploring deep learning, is that neural posterior estimation seems to be a very promising route to getting orders of magnitude speed up without introducing bias. Okay, so there are many others at KIPAC doing data science, trying to do science with data. Our data are typically sparse, blurry, low signal to noise, contaminated with artifacts and other systematic effects. I was pleased to see lots of these listed by other speakers this morning, so I'm not on my own here. But it is true that some of the techniques developed for higher fidelity data, so for example, natural images, look promising, but they may not be applicable. So some of our research is testing those methods in this different regime. You probably have had some of the same experience. If you do see some reflection of our work in yours, then it would be great to swap notes. I now have some business cards for you from 3 other people at KIPAC, just to show you what else is going on. Here's Tawiwa Sombom-Ponyakol. He's here. He works in the sort of extreme low signal to noise regime, X-ray astronomy, where every photon counts, trying to model galaxy clusters by their X-ray emission, and again in larger and larger samples. Here's Dominic Beck. He works on a particular inference where the likelihood depends on having done lots of expensive numerical simulations of the universe. He doesn't want to make very many of those simulations, but somehow has to cope with the fact that he doesn't have that many of them. And then here's Maria Elena Monzani, who works on the LZ experiment. This is an underground dark matter detection experiment, so another way of trying to understand dark matter. And they're trying to use machine learning for anomaly detection and uncertainty quantification. She puts it, the extreme needle in a haystack problem. So that went past fast. There's a lot of words on those slides that I didn't say. They're sort of designed for your future selves. If you find yourself interested in, what did that chap from KIPAC say? You can go back and look at these slides and read in a bit more detail. But I wanted to end with this picture. This is a representation of the strong lensing community at KIPAC, and I tried to draw people according to their shape, at least as I see them. So we have a couple of T-shaped faculty with their broad knowledge, providing some basic scaffolding. Then we have 3 gamma-shaped fellows. That is, we have long legs in our domain of strong lensing, but we've put some effort in over the years to understanding statistics, machine learning, and so on. But those legs don't really reach to the ground, so we have to lean on each other. And then at the top, what we've ended up doing is supporting graduate students who really are pie-shaped. So Sebastian and G1, and we hope Sydney, who did a rotation with us, are learning the machine learning, learning the strong lensing, and coming out skilled in both. G1 just got hired to Genentech, so a success story for other grad students in the crowd. Last thing to note, though, the one thing that we're really missing from this is someone with a long leg in statistics or machine learning. And so I put in this little crutch here called STS. That's what I'm hoping to get out of hanging out with all of you. Thanks very much.
think, Phil, on the question of what is dark matter, just put in a solid bid for the best research question. It's my pleasure to introduce our next speaker. This is Marc Hansen. Marc is the David and Helen Gurley Brown Professor of Journalism and Innovation, and also the director of the David and Helen Gurley Brown Institute of Media Innovation, Columbia University. And his title is How Things Really Are. Thank you.
Thank you. So I'm assuming the big green button is what I want, right? Yes. And I go back. There we go. All right. Thank you. Good afternoon, and thank you for inviting me to be part of this celebration of data science and the opportunities it holds across this and every campus. My talk today is about a quote within a quote from John Tukey, How Things Really Are. I chose it not because I know, but because the drive to find out is what motivates a careful data analyst. She's curious, she thinks beyond a single data set, she asks questions, she interviews people, she's an investigator. And for the purpose of this talk, I'd say in Tukey's vision, she's a reporter. 10 years ago, I joined the faculty at Columbia Journalism School. Prior to that, I had the good fortune of working with some amazingly talented artists creating installations that represented often complex data to the public. Here is one in the lobby of the New York Times, a grid of screens using machine learning techniques to create a portrait of the news of the day, word by word, sentence by sentence, article by article. This is my favorite image of the piece. It's a shameless photo bomber. Our artworks involve large and live data sets that we distilled through combinations, or that we distilled through sometimes playful, sometimes technical displays. I think that was what got me the job at Columbia. I had a background in statistics and had a sense of the narrative potential in data. It didn't take long for me to realize that this connection between data and narrative was hardly new for journalism. Even Joseph Pulitzer himself, founder of our school at Columbia, wrote in the North American Review in 1904 about his College of Journalism, my college, and what should be taught to promote the welfare of the Republic. In his essay, in addition to law and ethics and history, courses we offer today, he includes statistics or data. Everybody says that statistics should be taught, Pulitzer wrote, but how? You want statistics to tell you the truth? You can find truth there if you know how to get at it, and romance, human interest, humor, and fascinating revelations as well. Think of that. Romance, human interest, and humor. Pulitzer saw tremendous narrative power in data. All that said, as soon as I stepped into my first class, I realized that my training as a statistician didn't prepare me to deliver on Pulitzer's promise. One of the first student projects needed a feed of crime data from the NYPD. I was stunned to find out that while each week the department reported precinct-level incident counts, it did so by overriding the previous week's data. The department was in a perpetual now, and anyone who wanted to look back over recent history needed to be scraping it. Why? How could that be? One of the big lessons for me over the last decade has been how much we should know but don't, and how gap-filling is a first-order action in data journalism. For example, from the HHS, we have only sloppy voluntary counts of the number of healthcare workers at each facility who are vaccinated against COVID. We still don't have an accurate count of the number of people who are killed by police each year, but here news outlets like The Guardian and The Washington Post have stepped in using largely targeted Google searches to come up with better numbers than the FBI publishes. During the height of the COVID pandemic, the Atlantic's COVID tracking project provided data on testing that was not easily available elsewhere, and my own institute's documenting COVID-19 project used targeted FOIA requests to city, county, and state officials to understand how decisions were being made about the pandemic. Over 100 articles have appeared from this group, and recently they published data on coroner practices and undercounting of COVID deaths. In retrospect, I should have seen all of this coming, but from the perspective of the statistics classes that I took and the classes that I taught, data absence wasn't really discussed. The next hurdle for me was the basic act of reporting. This took me some time to fully appreciate. To describe what I mean, I'm going to refer to an article in the Columbia Journalism Review by Philip Isle. He's a freelancer from Rhode Island. The piece is called Ode to a Reporter's Notebooks. We've seen We've all seen portrayals of journalists on television shows and movies, notebooks in hand, scribbling furiously. For Isle, however, a reporter's notebook is more than paper and cardboard. It symbolizes the power and uniqueness of journalism as a profession. In his words, this object is a license to talk to interesting people and a ticket to interesting places. The key to bringing these people and places to life, he writes, is to capture and convey the details. And the reporter's notebook is how Isle captures the sights, smells, sounds, feelings, tastes, and other impressions of the world. To report, he writes, is to be alert and alive in a particular time and place. That's sort of worth repeating. To report is to be alert and alive in a particular time and place. When I arrived at the journalism school, I was told over and over that journalism is less an academic discipline than a habit of mind. We cultivate in our students a curiosity about the world, a restless questioning spirit that asks why things look as they do. And my role as a statistician in a journalism school is to add computational lines of inquiry to this habit of mind. If you take one thing from my talk this afternoon, it's that just as the reporter's notebook represents a call to be alert and alive in a particular time and place, understanding the computing systems we rely on daily opens our eyes to new aspects of the world, to see and interrogate the data and algorithms that increasingly govern how our society functions. And all this brings us, hopefully, to Tukey and the careful data analyst who knows how to be alert and alive and how to get at how things really are. All right, time for an example. Each spring, I teach a course in computational journalism. I'm going to present one of the data stories coming from my class. It's a couple years old, but it's a good example. Our reporter's notebooks have been replaced with the Jupyter and Colab notebooks, primarily in Python. Here's one of the notebooks. Here's the notebook. It's on bots. The bots are a great example because students can use bots both to report with as well as on. I'm going to take bots as a kind of case study for the rest of this talk because they have been particularly influential in spreading information and misinformation about voting and elections and vaccines and the war in Ukraine. As you all know, bots serve different purposes. There are bots that notify and bots that inform. Here's one that alerts you when a new word appears for the first time on the front page of the New York Times. And then there were pandemic-inspired bots. Recently, Twitter has tried to make bots like these a respectable part of their ecosystem. This is one that tweets out the location of jets owned by Russian oligarchs. It carries a new designation from Twitter, complete with a robot badge and mention of the author's Twitter account. The idea is to promote trust in these good bots. But then what about the bad bots, the bots that amplify? So what do I mean by that? Well, this is John Leguizamano. He's one of, here is one of his tweets. "I'm good, you?" he writes. Somehow this statement earned him 34 likes and 4 retweets. Who are the people who find this worthwhile to amplify? So here's Kim Hill. You have to wonder how she had time to pose for this image, given that she has 86,000 tweets in 2 years. That's about 10 tweets an hour for a 12-hour day every day of the year. And then Marquise Martinez. His account looks fairly respectable until you read that he's from Americus, a city in Georgia, and claims to be the dean of the Harvard Medical School. In my class, one of the issues we tackled was how we could be sure an account was in fact a bot. It's a dark art and offered an opportunity to teach the students about machine learning. There are services that can help, but they're noisy. Clearly, though, Marquise is a bot. Given all this, my class wondered what kind of influence we could have. So we opened up a Twitter account, and we did a Google search. How do we get more followers on Twitter? We turned up an answer. We could just simply buy them. So we found a company, Devumi, that seemed highly rated, which only later we realized was because the company's CEO was an SEO expert. It promised amazing growth, and the process was simple. Essentially, you pay them, and followers would come flocking. And so we did, and they did, and we bought 2,500 in total. I expected accounts like Kim Hill and Marquise Martinez. Instead, we had accounts like these. They look great. Biopics matched background images. Facebook and Instagram links pointed to accounts featuring the same people. These were real, but the economics didn't work out. We paid a couple of pennies for each follower. So why would anyone follow us just for so little money? It didn't make any sense. But then we noticed a tell. Every bot a clever bot maker had simply lifted people's data and created new accounts with a slightly altered name. Lowercase l's became i's and vice versa. O's became zeros. And underscores became doubled. The strategy works well because our actual login name appears only in small gray. Thank you. Works well because it appears in. Sorry, I've got to come back. I know, I don't know, because the actual login appears in small grade letters on the Twitter interface. The bot maker was indiscriminate, young, old, couples, adults and minors, all transformed into bots that went on to tweet statuses from Debumi's various clients in multiple languages, often political, often heavily pornographic. From our 2,500 purchased followers, we spidered the network and came up with 50,000 stolen identities, some stolen many times. After all this, we decided we had a story and we brought it to the Times. A year of computation later, this appeared. Buying influence from a shadowy market, and online it looks like this. So here's some examples, or an example, given that it's 3 minutes and 8 seconds. This is Chef Simon, an Iron Chef and then co-host of ABC's The Chew. He bought hundreds of thousands of followers from Devumi. In the plot, each blue dot is a follower. On the x-axis is the order they followed the chef, and the y-axis is the year they joined Twitter. For the first year or so, everything looks okay. This is what organic growth looks like, a slow hill, because as time goes on, people join Twitter and then follow the chef. But if you look at all of his followers, what you'll see is the stripes. The stripes indicate groups of accounts that follow the chef all at about the same time and join Twitter all at about the same time. This is a clear indication of bot accounts, as bot makers will often make their accounts in bulk after perhaps acquiring a list of stolen email addresses. The story behind the company itself is fascinating. It turns out they don't really make any of these bots themselves. Instead, it's a kind of arbitrage scheme with Devumi buying followers from a third party, places like Peeker. The fallout from our article was pretty intense. Hacker News said, basically, if a bunch of journalists could do this, why can't Twitter engineers? Which I took as slightly insulting, as the whole purpose of this class was to prepare journalists to do this. But anyway, a couple of people were embarrassed and threw their aides under the bus. Attorneys general at different states opened cases. The Senate directed the FCC to look at impersonation, and lots of bots on Twitter, millions of bots died on Twitter almost overnight. And then California, you're welcome, got a bot law, again referencing our piece. There is so much more to talk about in this example. How does a news outlet trust the work that you've done? How do you explain data science to your editor? What habits do you adopt to make these questions easy? I'm going to get this finished even before time, Chiara. But I'll leave all that discussion about trust to the next panel. That said, I hope with this example you see how Tukey's quote feels like a call to report. There's a dynamism in Tukey's description of exploratory analysis as investigation. It is similar to the call to be alert and alive. So far, I've emphasized what it means for the practice of journalism, how the introduction of technical tools helps journalists both report on as well as with computation. But there are lessons for data science as well. The call to be alert and alive in a particular time and place is the backbone of a potential public mission for data science. Look up, get involved, ask questions, talk to people. Philip Isle finishes his ode commenting that the reporter's notebook is one of the world's greatest mechanisms for accountability. Again, from the data science perspective, the reporter's mindset can be an entry point for an aspiring data scientist, an invitation to question the often invisible but undeniably powerful computing technologies that shape our daily lives. Thank you.
So I'm going to ask our speakers to join us up here at the front and take a chair, take a seat at the big long table. And while they're joining us, go ahead and think of what questions you all might want to ask. And there's And let's see, do we have any questions from the audience? Okay, we have a question up here. I don't know where our oh, and one back there. Go ahead.
Just thought I'd get started with Dr. Williams. So in looking at the sort of the positive assorted mating of scholars in Stanford, how did you account for the fact that the kinds of scholars who want to move here might be exactly the ones who are more interested in certain kinds of translation and team science? And I've seen that in my own discipline and many other disciplines, that there are people who are perfectly happy with the winters or whatever in their home institutions, and there are those who actually want to get patents and start businesses, and they have a different DNA even before they move.
Yeah, great question. These kinds of questions are places where I feel like theory and data are really complements in kind of trying to think about what are the different mechanisms by which this might matter. And so one thing is when you move to a new place, some of your work comes with you, right? Your past work. So how does citations to the work you did before you moved change versus, what's different about your work? Are you working in different directions? How do things change after you move? So when you're working with data like full text publication data, full text patent data, it's just a very rich setting to be able to talk a lot about, what happened to my work at my old institution? Was that converging to be more like the research that's done at my new institution before I moved? How is the work changing when I actually moved? And so those are all things that, we're still doing a lot of the text analysis to be able to do that. But I think just conceptually, I think there's like a lot of interesting experiments in the data that let you get at different mechanisms that I think shed light on different behavioral margins that might matter. So.
It's a question for Phil about sort of where the data scientists sit in physics. So you have this this real distinction between like the theorists and the experimentalists, right? And so I'm curious, have the data scientists emerged from one side or the other, and in part this is flavored by thinking about data science as an interdisciplinary sort of enterprise and the challenges that people who sit at that sort of nexus often have. So I'm curious where they're sitting, and have they been sort of, have people who do data science and physics been able to go on and get jobs in physics and be sort of, embraced by one side or the other?
Yeah, it's an interesting question. I'd say mostly it's more on the experimental side. People trying to make measurements have got interested in more and more sophisticated ways to do that, and ended up being drawn towards the data science communities that are forming. But it's not entirely true. We had one pair of postdocs who actually pioneered the machine learning work that we then picked up on. One of them came from the theory group, and the other came from the observational side of KaiPak. And they worked it all out together, and then have carried on in that way. So I think it's piqued the interest of people across astronomy, and it might be just because of, the nature of our field. It's hard to make measurements in astronomy, and the theorists see that as well as the experimentalists. The experimentalists feel it, but the theorists see it as well, and so it has some draw for everyone. In terms of where are people getting jobs. I think the postdocs who are applying for faculty are seeing a few more opportunities in more data science-oriented ways, joint positions, that kind of thing. But it's, I wouldn't say it was really taking off around the country. I think what they'll do is they'll take their short legs to their new departments and just continue the process of seeding data science initiatives there. And then it's nice to be able to. Well, it's nice to see the grad students and postdocs who really get into data science becoming really quite attractive to industry, especially around here, and that's been really good to see.
There's one behind you, so I'll take the one back first.
Hi, this is a question for Mark and for Brad. I've seen some really bad examples of computational journalism where some company will exploit cherry picking to make their product look really good and kind of pull the wool over the consumer's eyes. So my question is, what can reputable statisticians and journalists do to help these consumers out and mitigate this problem?
Would you please repeat?
question is, what can we do? Tell me if I get this right. What can we do to help people better understand the data that's being presented to them and from reports and studies that are coming out?
It's a question of how we can interpret things better, or...
No, I've seen some really bad examples of data journalism where they basically like exploit selection. Like they really pick out things, and the consumer gets really excited because it looks like there's statistics and there's data science when there really isn't. Yeah. And my question is, what can reputable statisticians and journalists do to combat that?
Yeah, so that I don't have a specific answer, but I do. It does bring up the question of covariates. The analysis I gave sort of lumped everything in the world together, which is what the Cochrane database does, but there's covariates. Like if you knew that this journal is a terrible journal and they just go out of their way to exaggerate, you'd feel differently. I feel differently when I read something in the New York Times than if I read it in the Daily Post or something like that. So the answer is I don't know how to do that. In some sense, it falls more into your
right. Yeah, so I think when I first started at the J School, there was one data-related class. It served 16 students a year, and that was it. As a course, like for a semester, and now about half of the cohort takes some kind of data training. So I think there's one thing is to simply up the overall literacy of even sort of the rank and file journalists who aren't going to go into sort of big heavy data work. There's also, I think, newsroom practices that help protect against sort of mistakes. Now, if an outlet's going to intentionally deceive, that's a different question. But to keep them from making sort of rookie mistakes is something that training can help with, and editorial process can help with, I think, too.
So I keep scorecards on data, the various journals and things I might read. So, for example, does you get a brochure from some place, maybe their newsletter. Does the newsletter ever have anything against their main point of view? That's a real good sign. Have they ever changed their mind on anything? That's another good sign. So, yeah, you can watch.
I love that idea of a report card. I think we can take one more question, David, and it looks like that's you.
So, this is a pretty simple question, but I guess it follows on is, if I understood, Brad, your talk, it wasn't totally symmetric, the Cochrane database. It seemed like the positive effects got shrunk differently than the negative effects. Did I see that right? And what's different about studies that are finding positive effects from studies that are looking at negative effects?
No, could you see?
So there was some asymmetry in the effects, the positive versus the negative, and he was just asking what.
Why
is it not symmetric?
Why is it not symmetric?
That's a very good question. It worried me about the Cochrane database as to why it's so symmetric. It worried Eric Van Zwedt also. You'd sort of think that it would be more positive, maybe if the z-values were always the treatment minus the control. You'd think that most of them would be positive, right? I tried to find out something about the Cochrane database and sort of failed. It's a really interesting, the amount of stuff I showed you is a very small amount of the things they have. And I did not succeed in really understanding why there was that symmetry.
So let's thank our speakers one more time.
I want to thank Kate for moderating that panel. So our final break of the day begins now. We're going to have a session at 3:30 that is entitled How to Increase Trust in Data Science, and that's moderated by Chiara Sabati. So have a good break. There should be stuff on the patio. There's drinks in the back, and we'll see you back here in a half an hour.
Hello.
for David. Someone must have his phone. Hello, hello. We're going to get started in just a moment. Welcome back from the break. We're in the home stretch. I hope you are looking forward to this panel as much as I am. This is people trickling in. Welcome back. So I am pleased to introduce Professor Chiara Sabati, who will be moderating this next panel on how to increase trust in data science. Chiara, as you saw earlier, is an associate director for Stanford Data Science. She's also the conference chair for this entire conference. So just a quick round of applause to Chiara. And welcome.
All right, so I think I'll sit here since we have. So thank you. I am, as you know, this panel, it's entitled How to Increase the Trust in Data Science. And I think the pandemic that came up already a number of times today has reminded us all the importance of having a healthy, trustworthy relationship between science and society. And really, it doesn't make sense to do any science if we cannot communicate it to society. It's not a solitary endeavor. And I'm very glad that we have 4 people here from the Stanford community who are going to help us think about this. I'm going to introduce them, and then I'm going to ask them to make some statement about what are their immediate reflections on the topic, of what in their work it's connected to the topic. And then I have some questions to start the conversation. But I really would like this very much to be an open floor type of discussion. So please think about your questions and do not be shy in asking them. So in the order here, we have Deborah Satz, who is the Vernon Elizabeth Warren Anderson Dean of the School of Humanities and Science. She's a philosopher. She's a member of the American Academy of Art and Science, and she's the author of several books. The only one I'm ashamed to say I've read is Why Some Things Should Not Be for Sale. I recommend it strongly. It was very clear and helpful to me as I was trying to think about fairness questions. She is a wonderful dean to have. Deans have this, I think, terrible, for my point of view, job of having to say something in millions of different occasions and having to send out letters with cheerleading intention or not. And whenever Deborah introduces or says things for no matter what occasion, her remarks are always very informative. They get me excited about the job. So it's really a delight. I'm very happy that she's here. Then we have Professor James Zhou. He is an assistant professor of biomedical data science and by courtesy of computer science and electrical engineering. He's a recipient of the NSF career and a 2 times Chan Zuckerberg investigator. He is also a person I look up to, even if generationally he's much younger than me. He has really published in a vast array of topics in biomedicine. He's a member of my department, and he has also a number of publications in topics very related to this panel. For example, he has a paper that's titled Sex and Gender Analysis Improve Science and Engineering, or Word Embeddings Quantify 100 Years of Gender and Ethnic Stereotypes. So much to say. Professor David Donahoe is the Anne T. Robert Bass Professor in the Humanities and Science. He's a MacArthur Fellow, a member of the American Academy of Science and National Academy of Science. He has an infinite amount of honorary degrees and prizes. And he has a very strong experience, both in research in academia, but also consulting and working with industry. He was quite literally one of my teachers, and without, I didn't love his lectures in the sense he wasn't the most structured teacher. We never knew if he was going to be there on a certain day or not. But with all respect to all the other wonderful teachers that I had during my first year here, I have to say David Donahoe's lectures and remarks are the ones that I find myself going back more often. So he really had a fundamental influence on what I think, and I'll tell you two things that are related to today. One, there has been some rumoring around, well, statisticians are abstract, do you do really data analysis or not? Our first assignment for David Donahoe class was go and find some data. And those were dark ages of the internet, so there was this new thing called Netscape that has appeared, and so we were shipped out on the internet to go find data sets. So he is a data scientist at core. He also had this remarkable expression that, I don't hold him responsible if it sounds a little bit arrogant, but got me totally energized, telling us that as statisticians, we were the ethical consciousness of science. So very much the data scientist and embedded with ethics. Sherry is an associate professor in health research and health policy at the Stanford School of Medicine. She is also a recipient of many awards, including the Gertrude Cox Award and the NIH Director's New Innovator Award. She has a very interesting background in that she has done some very strong methodological work on causal inference. Early during the day, we were asked, do you have the certification to work with observational data? And I think she definitely does. But she has also started thinking very strongly about policy implication of our data analysis. For example, one of the areas where she works is healthcare spending and insurance, and one of her latest papers is titled Fair Regression for Healthcare Spending. I have had less pleasure to interact with Sherry because she joined Stanford during the pandemic, so it's the first time that I get to meet her in person. But she has been very generous with her time, saying yes to a number of invitations that I had involved her with. So after all this talking, let me give them a chance to actually say some initial remarks about the topic of the panel and how they think about it. Debra, would you like to start?
Okay. All right. Well, thank you for having me, and I'm so excited and thrilled about this event and this bringing together data scientists, with social scientists, with humanists. I think the problems that we face are daunting, and we need many voices at the table. I was a math major, but I'm not as an undergrad, not as my field is philosophy, and I don't really work in the space of data science, but I'm gonna talk a little bit about trust in general and some lessons we know about what increases trust, and I think some of those will apply in the context of data science. So trust is a pretty complicated phenomenon. It's a relational phenomenon. It's not a one-way. For me to trust you, I actually make myself vulnerable to you. I take your word. I rely on you in my planning. When I trust institutions, I take their word, I rely on them, it influences my planning. So it's relational, and it's not always the case that trust is a good thing. It is very important, but if an actor is not trustworthy, right, it's rational not to trust them. So while lots of things go wrong when we don't have trust, sometimes it's appropriate not to have trust. Sometimes it's actually good for people to be skeptical because it makes them pay more attention. So I just want to point out it's not a singular good, but in lots of contexts, the absence of trust makes things go badly. And certainly the absence of actors that are trustworthy makes things go badly. And sometimes there's an interaction effect, because when people don't trust you, so imagine around issues about data, or they're not trustworthy. If they're not trustworthy, of course, they'll do things that make people don't trust them so much. And if people don't trust them, they may withhold data or game data or manipulate data, which then feeds back into researchers becoming less trustworthy. So what factors do we know are helpful in increasing trust and increasing the trustworthiness of actors? And I'll give a couple of factors that I think are pretty general. Some have to do with the input of what we're doing, some have to do with the output, and some have to do with the process. So on the input side, if you want trustworthy actors, they better be competent at what they're doing. You want people who actually are able to deliver. If you're, gathering data to help with some kind of problem, you want to make sure you're actually gathering the data correctly and the data that you need and figuring out what that is so the input matters, the competency of the people matter, the outputs really matter. And in particular, you want outputs that really deliver benefits to people. If your outputs are not helpful, if they're damaging or harmful to people, they're not going to trust you. Even if your intentions were very good, if you are not alert and not on board with thinking about the outcomes of what you're doing and the potential risks, right? People are going to not believe in you. You're not going to be a trustworthy actor. And sometimes in Silicon Valley, and our students and we say, like, move fast and break things, but if you break a lot of things and those things turned out to be really important to people, they're not going to be happy, and they're going to withhold their trust, whatever your motives were. On the process side, there are a couple of things we know work well. Transparency is important. Transparency about what you're doing and why you're doing it, and if you're collecting certain kinds of data, why, and being very open about that. I think accountability is really important, that you're making credible commitments, and if you don't follow through, that you're actually accountable, and that people see that people who who misuse, right, data or are bad actors are actually held accountable. And then there are concerns about fairness in the procedures. And here, in terms of fairness, there are many conceptions of fairness and many dimensions of fairness, but I'll just say I think it's really important to make sure, particularly when you're using data to address problems, like many of our social problems that have differential effects, that you consult widely and you make sure that there are all the relevant voices at the table, and you pay special attention to the people who are most disadvantaged or have the potential of being most disadvantaged by what you're doing. So I think maybe I'll stop there. There's more to say, but.
Thank you. Well, we are in this linear order, so.
Great, thank you. And if there's one takeaway from the panel is that if you get a chance to be introduced by Kiara, then it's definitely you should get her to introduce you. So I'm James. A lot of my work works on developing data science and algorithms, especially for healthcare applications. And especially when we're thinking about applying the data science insights and the methodologies and algorithms for dealing with patients and doctors, I think trust is especially important, or trust in the insights and also trust in the data. So I just want to give you one example to illustrate, right? So recently there's been a lot of interest in developing using basically computer vision to look at your skin and assess for skin cancer. Right? So there are a lot of companies that are doing this. And if this works, it could be very valuable because skin cancer is often underdiagnosed. Right? There are millions of people around the world who are, are not caught with skin cancer until it's too late. So it looks very promising. So we actually took 3 of the latest models, including ones developed by very large companies. I won't name the company, but they funded many parts of campus here. And we just evaluate them on Stanford patients, right? So these models, if you just look at their original publications from their paper or from their press reports, right? So they will get very high performance, AUC or accuracy about 0.9. When we test them on Stanford patients, the performance, much to our surprise, is just barely above random, right? So the AUC is about 0.6. So this led us to, and we were quite surprised because these are commercially available algorithms that are going through different parts of the FDA approval process. And we wanted to audit to see, okay, can we actually do a systematic audit to understand what are the factors that contributed to the algorithms doing so poorly on the real patients here at Stanford. And after the audit, what we learned is that most of these drop-offs, algorithms performance, most of the mistakes they were making can be attributed back to the training data that was used to train the algorithms. Right? So it actually turned out that the data that we used to report the very high 0.95 original AUC, they had a lot of mistakes in them, right? Just simply there are annotation mistakes in that data. And secondly, the original data basically had no images from dark-skinned individuals, right? So that the algorithm had very disparate performance when they were applied across different skin tones. So there are factors like those that I think are really important to understand, right? So the lesson that we learned from this is that oftentimes, the performance of a model or algorithm or data science model is really meaningless unless we really understand more deeply about what is actually the data and the data pipeline process that went into behind developing and evaluating this model. And this also highlights, I think, sort of maybe one limitation currently in a lot of our education and research. Right? In many of our classes or when we do research, oftentimes we're given a particular data set, right? The data set is given, and then we teach students how to build really good models on top of that data set. Right? That's how most of our classes are done. Right? But in practice, in industry, right, the biggest challenge is often how do you actually come up and create the data set in the first place? Right? And there are many challenges there, right? So for example, how do you decide what are the most informative data points to collect, right? So there are active learning questions there. Given some data sets, right, oftentimes now it's also unstructured data like images and text, how do you figure out how to efficiently annotate the data, right, to reduce these potential biases, right? So annotation can be challenging. And now, if you have a collected data set, oftentimes it's noisy, right? How do you systematically clean the data set? And after you have cleaned the data sets, what are the systematic approaches for even evaluating the data set for potential biases, like the ones that I mentioned? Right, so each step of this pipeline corresponds to and raises a set of really interesting technical challenges and also sociological challenges that I think requires a lot more research and a lot more emphasis in terms of the education that we do. So a lot of my work that my students work on are very much focused on looking at each of these sort of data-centric challenges. We're trying to come up with some combination of new methods, scalable algorithms, as well as collaborations with people like in history and in other departments for working on looking at these problems. And I think as we're thinking about how to build more trustworthy data sets, right, and more trustworthy data science applications, then I think it's really important to understand each of these components of the data creation pipeline.
Chiara, thank you for the introduction. The number one thing that occurs to me is how difficult it is to really reach a conclusion from data, and the struggle that many people have when they get started in the data analysis business with doing anything right. It's a long, long time between when you first, say, know a little bit about coding and you do something with the data set that really strikes you as having gotten to the heart of it and it must be right, and you think about it a lot afterwards and you realize, yes, I really got to it. In between those 2 points, there's generally a lot of personal development and struggle, which can last for years and years. I think that this may not be the first thing that we tell master's students in data science, but it's maybe the most essential lesson. And the development of data acumen, mastery, things like this are a big part of the journey towards understanding how you can learn something from a data set and how you can feel that you got it right. Now, there are many steps in this process, but I thought I would just share one set of tools that theorists have, and then one set of tools that non-theorists have. So as theorists, we generally develop generative models, and we say, okay, if the data were generated in such and such a way, would that produce what we're actually seeing in real data? And that has been around for, I'd say, 350 years as an approach, and it's been very successful. I think data science and statistics is basically that subject, but there are other subjects that definitely use that approach. Data science took a different route as an industrial job categorization, which is there is only data, there are no true models, there is no generative model, there is only the workflow, and we build workflows and we do stuff to data, and then we show you what we've done. The thing that generative models give you is an approach for academic discussion, because people can learn what the generative rules are, and they can understand whether the generative rules produce data with the particular structures and artifacts that you're seeing. The other approach, which is end-to-end workflows built, for example, in an industrial setting, they don't have anything underlying them other than the data set, which you often don't get to see. How can you develop any understanding of what the data are offering and what the message is in this second setting? So one thing that has helped me, and I've seen it help other people, for example, in consulting projects with the Wigler Lab at Cold Spring Harbor, is let's think of a three-way array: data sets across methods, across observables. And we're going to just endlessly make we're going to make essentially scatter plots across all three dimensions and see how any pattern we're interested in changes with the data set or with the method or with some particular way of coming up with an observable. And I think that is one of the most potent tools that people who are operating in this end-to-end workflow arena have. And perhaps this is obvious, but it brings up a point, which is depending on what it is, the underlying computation, let's say it's a deep learning model, there could be a great number of individual computations that have to be done underlying that. Many trainings of models, many variations of architectures, et cetera, et cetera. And so the only way to carry out this kind of comprehensive XYZ gridding of your understanding of how to tease apart everything that could affect the analysis is to have pretty massive resources. So the generative model approach that was prevalent because of the mathematical sciences, probability and statistics, you had to have IQ points. Now you need to have a dollar budget. And I think science funding hasn't really caught up to that. So I would say that we need a very extensive rethink of how science funding is being handled so that there are adequate resources. I was really happy to hear that there's interest on or work, I don't know the status of it, on building up a compute cluster or other compute resources associated with this center. I think national level facilities and totally new science funding has got to be thought through and developed. So once that's done, it'll be much easier for people to find the resources to do the kind of computations that are needed to pull things apart across multiple varying factors. If not, what happens is people become advocates for one model, or they become advocates for one data set or one particular observable, and it's actually that their hands are tied behind their back and they're just making a stab in the dark. So the trust that we can have on something that's been really exhaustively computed would be, I think, a big improvement in many people's ability to trust research. Of course, for us to trust other people's research, we have to be able to use this, which could be called a kind of recompute approach on other people's data. So they have to publish it. It has to be understandable to us. And then we have to have the resources. Beyond funding, there's also just the resources to make this kind of computing easy and almost irresistible. And I think there's been a lot of progress recently in the ML ops startup community, but that also is going to lead to voracious demand for funds on the part of researchers who want to use all those fancy new ML ops tools.
This is my first in-person conference in over 2 years, so I hope I remember how to do this. I'm a statistician by training. I think I'm not supposed to mention that I did my PhD at Berkeley, but Sandrina's here, so at least one person's happy about that. But I'm also equally a health services researcher, and so a lot of my comments will be related to the deep integration that I have with problems in health policy. So when we think about trust in data science, there are many things that I aim to incorporate in my work. One thing that we should be thinking about is who is doing the work, who has access to the data and the resources, who has the power or political capital to be making decisions about the types of questions that we ask and answer. Another one is who is being cited and who is not being cited. We've seen examples where certain fields of work within data science are less valued and have been led by people of color and women. And over time, as those areas become more and more valued, that foundational work is not cited and recognized. And so there are initiatives like Cite Black Women, led by Kristen Stewart, to draw attention to many of these issues. Another question is, what is the goal of the work? I mentioned that I'm equally a statistician and a health policy researcher. The goal of the work that I'm doing is to try and develop methodology that solves real problems. And I think one of the things we need to think about with trust in data science is being good stewards of the data. So if the goal of the work is to solve a real problem, that would not involve treating the data like a toy problem, which is also related to another point of mine, which is genuine integration in the application area. So when you start chasing things like my goal is an 8-page NeurIPS paper, my goal is a 6-page JAMA paper, that's not the same goal as trying to solve a real problem in healthcare, which is the area that I work in, and it's not necessarily being a good steward of the data, although it could be. Another thing that dovetails nicely with a number of the other comments on the panel is more comprehensive evaluation of the work that we do, broader sets of metrics, not just things beyond AUC and overall fit metrics, but metrics for marginalized groups. And then also thinking deeply about generalizability. So much of the work that we do might be in a single data set or a single year of data in a particular medical center, and making any broad claims about this algorithm or tool should be used in practice could be pretty dicey, especially if we haven't looked at external samples. And some of this leads to us having minimum standards for this type of work, especially in healthcare, and we've seen a number of papers and guidelines that have come out. I myself have worked on some, including a recent paper led by Irene Chen, who's a PhD student at MIT, where we developed an ethical pipeline for machine learning in healthcare. There's also a recent paper by Judy Gachoya at Emory about operationalizing fairness, and these are all important endeavors. But I think one of the places we need to go to as far as trust in data science in the health space is enforcement and having some enforcement mechanism that comes down from funders or journals. We've seen how this has been really useful in the past, especially for things like pre-registration of primary outcomes in clinical trials, because right now the uptake and the engagement with a lot of these guidelines and recommendations is pretty weak. And so I would love to see us move in that direction. And I'll stop there.
Well, thank you all. So I do want to do you have questions? I have some questions prepared, but I don't want to. I've already spent a lot of time introducing the panelists. So if you have questions, raise your hand so I know that you have questions and I don't ask useless ones. But I wanted to go back to the issue of privacy and sharing of data, sharing of methods that a couple of you mentioned, but also it was mentioned during the rest of the conference today. And, you know, it seems that for the point of view of who does the data analysis, the more data, the better. But, you know, the data belongs originally to somebody, or it's relative to one person, and there are sort of then concerns about privacy. Do we really want to know everything about everybody? So there might be a trade-off between privacy and large data sets available that would make easier to extract knowledge from them. And I wonder if you have any thoughts about this trade-off, if there's a way of mitigating the trade-off. I don't know, James, do you want to start?
Sure, happy to take a first stab at it. I think this is definitely a very important topic. It's like one example that comes to mind is that you know, many of us here have been using this resource called the UK Biobank, right, which is a place where 500,000 people in the UK have actually consented to have their data being used for all sorts of medical applications. But once in a while, like maybe every couple of weeks, I'll get an email from the UK Biobank that says, person X has decided to withdraw their data from the biobank. If that happens, then you have to delete their data and also delete their data from any models that's been used, trained on that data. So this actually raises a really interesting perspective that's different from privacy, but I think it's perhaps even broader, which is that these individuals, and like many individuals like us, we have consented for our data to be used for certain applications, right, when we over some time period. But the individuals also like to have control and some sort of governance, right, ownership even, that says that if they, at a later time, they can decide to flip off the switch and say, my data can no longer be used for these applications, right? So here it's interesting because the people have certainly given away their privacy because these are genetics data, medical records, but they still want to retain this level of control over when and how the data can be used for specific applications, right? And this, I think it's worth maybe even taking the discussion beyond this traditional notion of privacy and going to this more question about data governance, right? So how do we enable individuals more options or control over when and how the data can be used? And this leads to a lot of really interesting, I think, open challenges, right? For example, like even if when you decide to delete your Facebook account or delete your Twitter account, the algorithms that are used by these companies actually still retains a lot of information from your data, right? So it's actually not obvious how do you really remove your data from these large models after the models have been trained on this data, right? So that again goes back to the question about how do we really give individuals more ownership and more agency over how their data is being used.
Can I? So I think that's really important, and I'm with you, and I think the questions you're identifying are really interesting. I wouldn't want the default to be that every individual owns their own data, because there are also problems with that assumption. We have some strong reasons, like I give the example of COVID. We don't want people to be able to remove data about how many people have been infected in an area. So if you think of it as it's the individual's right, then the individual can pull that out. And so I think there's a governance question and there's a democratic question for us together to think about what kinds of data should be private, and there clearly are reasons to hold some data at the individual level, and what kinds of data actually you don't have a private property right over, because there are important public goals that couldn't be met if you held that data back.
Just from the statistical perspective, self-selected data is very problematic. Yes. And maybe self-selected erasure is also problematic in some ways, so that it might jeopardize the whole project if there were a wave of people who, due to herding, all had certain characteristics and took themselves out of the data set.
Question, but maybe we can take it a step further, which is, most data sets probably have some kind of selection bias, right? And we know that selection bias can really screw up any type of causal inference you want to make from a data set. So how do we, I don't know, maybe James, since you've thought about, these issues about sort of distributional shift and stuff like that, or Sherry, you may have thought about this as well. I don't know if, are there ways to think about, particularly about selection bias in the context of fairness and trust?
I can start. So the representativeness of the data and the selection bias involved in which data that we see and who's part of the data is a really important question with many facets, and I'll just touch on a couple. But for example, I've worked with both randomized trial data and observational data. We know that randomized trials are often held up as a gold standard, but they have many of these same selection issues. For example, if we have a randomized trial for a particular type of cancer, and 20% of the population that has this cancer is Black or African American, and we see that the randomized trial, only 2% of enrollees in that trial are Black or African American, we know that we have a substantial issue. And in our observational data, James also brought this up, we rely on who's in our observational data sets. And the data that I work with is many of these data sets, who has an encounter with the healthcare system. And many individuals, including people from low SES backgrounds, for example, are not going to have an encounter with the healthcare system, or individuals who do not currently have health insurance. So many marginalized individuals will not be included. And so I do work in generalizability and transportability methods. Some of these are complex, machine learning, double robust, all that jazz, but they can't really take the place of a deep understanding of the exclusion of marginalized groups, and as well as remedies to this systematic exclusion. So a lot of these tools just really, it has to be both, not or.
And maybe just to, I really like that point, and just to follow up on Sherry's points a bit more, is that, yeah, so I think exactly a lot of the clinical, even the randomized studies, even though that's sort of the gold standard from the causal inference perspective, there's an even stronger selection bias for them. Like a lot of the clinical trials are really looking for the Olympic athletes of the patients, right? And it's actually now well appreciated that the causal effects identified from the clinical trials often do not translate when the drugs come on the market for the average non-Olympic athletes. And there, I think some of the most exciting efforts are being like really large efforts to curate much larger, more representative data sets. Like for example, the Flatiron Health Network, it's one example where they're actually going around to over 280 community cancer clinics to actually get more data from those community clinics to get more representative populations, which are very different from the ones that are participating in the clinical trials. And there, that runs into all sorts of these, the data creation questions, like how do you harmonize data from all these different clinics? How do you fill in the missing data? And how do you extract the data from the medical records? But I think that's sort of where a lot of the most exciting work is happening.
I wanted to ask, sort of take off from where Dr. Satz made a really important observation right at the start, which is trust is relational. There's no such thing really as a data set that you trust. People, there's a person who is trusted, who's making statements on the basis of their research, and there's people who are doing the trusting. So I think to answer this question, we have to be really, really careful about how we define both. So for example, with what example Sherry was making about the conclusions from a clinical trial that's not representative, if the person who is publishing that says, this is not generalizable because my population did not include these minority groups, that's a perfectly reasonable statement. The issue is, how do we trust the statements that are made on the basis of the analysis, and who are we trying to convince? If we're trying to convince a fellow scientist, a lot of the conversation had to do with, how could I convince a fellow scientist that it was true? It was substituting truth for trust. There are lots of things that are true that people don't trust, and a lot of things that are untrue that people do trust, like the effect of ivermectin and hydrochloroquine for COVID, even though they don't trust the actual RCT findings. So I think we have to be very, very precise about who these two agents are. If we're trying to convince a doctor and we're a data scientist or whatever, that's a certain set of tools to get a doctor to be convinced enough to treat a patient. And we have a whole set of norms, some of which are not very good at that. I do think transparency has a lot to do with that, and there's lots of things about how consensus is formed. If we're trying to get the general public to trust the science establishment, then we have a whole different set of tools and a whole different set of answers of issues, which do get to issues of transparency and democracy and who's participating and who are other people who can see the data. So I think this is a very layered and nuanced issue of who are making the statements on the basis of the data, and how are those statements processed, and who do we want to be trusting them. And it can be a completely different answer if we're saying a physicist trusting a fellow physicist, or a person who's driving a car trusting the engineers, the doctor trusting the authors of the paper, or the general public trusting. So I think we need to address each of them, and in this community of scientists, we often think that if it's more likely to be true, it's that trustworthy is more likely to be true. But I think if we're talking about trust, we're going to have to enlarge the conversation to include all the complexities that Dr. Satz, I think, started this with. Thank you.
Thank you.
Somebody over there.
Oh, hi. My question, I think this is a really fascinating discussion kind of about privacy and trust. I think a growing body of research is around the use of simulated data that might have different privacy guarantees. And I think it follows the previous question about kind of who the trusting body is, because I think, privacy guarantees can help the trust of people who might be opting into the study, or, for example, in the US Census, this current one kind of has differential privacy guarantees in terms of kind of simulating the census data set. But on the other hand, you might have less trust in downstream findings, given that we might not know the generating function for, the simulated data set. Like, how do you think we as scientists should balance, the privacy and trust, especially, when we don't have the full information of maybe how data is generated?
If I might join your two comments and question, we talked about data because at the basis of data science there is data, and we try to describe some characteristic of data that might play a role in this trusting. But if we think about the general public trusting data scientists, we have many settings where the general public trusts people. They trust the doctors, they trust the engineers, and generally these professions that need to be trusted by the public, often they have an accreditation protocol. They have people in this profession pledge to follow certain norms. So maybe we can phrase the question in terms of, are there some ethical conducts for data scientists, something that we should pledge to follow so that we can be, and are there some accreditation criteria that could facilitate the public trusting what we do?
You're looking at me.
Anybody.
I'll just say, I think it's a great question. Professional norms do seem to make some difference both in behavior. They're not not merely symbolic. I think we have an educational responsibility in the way we're training the next generation of our data scientists. This goes back to what you were saying about, we want to think about the construction of the data sets that we're working on. I actually think we want to think about the outcomes that we're aiming at. We want to think about trade-offs. We want to think about the different values. I think there's also a huge issue around uncertainty and how we communicate about uncertainty, because that's a very important factor in trust. But we need to say when we don't know and when things are uncertain, but there's also a tendency when you indicate a lot of uncertainty for the public to feel less trust. And so there's some, but we've got to get a new generation thinking about these issues in the very training of what it means to be a data scientist.
Anybody else? Otherwise, I think we are out of time already, no? Are you keeping track?
I have a question.
Please.
Yeah. So in terms of data science training, I find that actually there is a tension between some traditional method, especially respect to basic chemical or physical principles, and also some new data science method, like machine learning method. And when talk about a specific task, let's give a concrete example. For example, to predict air pollution levels at Stanford campus, I can use chemical transport models or a machine learning model from satellite data. And the two groups of people won't trust each other's results in terms of, for example, machine learning models have higher R-square evaluation measures, but the chemical transport models have a clear physical principles behind that. And especially, for example, in these chemistry groups, they actually trust other chemistry or physicists more than data scientists. So I would see in terms of training how this thing can be harmonized in the future.
Anyone?
So any idea on training? I think, there's two trainings. There's training of the data scientist, and then there's the training of everybody. Like if data science has such a big say, if it's in what in the journals tells or not, we all have to be able to interpret data to some level. Do we have a responsibility toward data literacy for everybody? So I don't know if.
So bilingualism helps. If you know how to do the scientifically motivated generative model of the phenomenon and understand how that affects your workflow, and if you also know how to take a given workflow and tweak its parameters and understand how those sort of data science operations affect your workflow, you're speaking both languages.
And in the examples that you were mentioning, what we're trying to push towards is more about using more rigorous evaluation and monitoring, because oftentimes it's hard to decide what model to trust more from first principles. So then that's why it's important to do more rigorous evaluations and also evaluation over time, monitoring of these systems.
Any concluding thoughts?
No.
No.
Can you hear me now?
Yeah.
Okay. I'm going to ask a question that's coming from a different perspective. I know the title of this panel had trust in the word. Trust to me makes me feel concerned. I think trust is important. I like the terms like accountability and standards of practice, because I think we should not just trust people, we should also hold them accountable and be critical about what's going on, self-critical, but also critical of others. But I'm going to ask a different question. Data science and the whole frontier that it's building is not being built in a vacuum. We live in a research culture that has been going on for a while. So can you give me your perspective on the current norms, the current accountability, the current practices that are going on in the research institution now that you would be concerned that might reproduce bad outcomes in the data science age? And what would you prioritize to try to change or keep the same to make data science more accountable and more transparent?
Well, I could say one thing, which is came up with, the reproducibility of data, like going and trying to reproduce data. I think we disincentivize that. It's actually why would you take somebody else's finding and redo it? You're not going to make your name for doing that. But I actually think that's a very important thing we should be doing more of. And null findings, which are also tend people not to care about, they're really important. And so somehow changing the recognition for the value of the reproducibility and the null findings, I think would be important.
Yeah, just to build on that, I think we disincentivize a lot of the things that we would say would support robust, accountable, high standards in data science. We reward many quickly published short papers. We don't reward open science in the way that we could, although that's slowly improving. We don't reward reproducibility. We don't reward the generalizability. So why get an external data set when you can publish it with just 1 year of data in a single medical center? And so I think there are a lot of things that we could do to improve this. I mean, it would be some of it would be pretty radical shifts, but I think starting with minimum standards for the type of work that we publish. And I work in healthcare, so I focus on minimum standards for data science and healthcare. I mean, there's so much work that is published that wouldn't be if we had some of these minimum standards.
So I just want to mention in the context of these comments, Stanford is actually part of a group that was just announced this last week called Helios, the Higher Education Leadership Initiative on Open Scholarship. Mark and Persis signed on to Stanford becoming part of this, and I'm kind of sitting in for them as their representative. And the goal of that group is exactly what you're talking about, of basically working, there's 50-something universities and colleges working together to basically figure out how can we build incentives for people to do the kind of science that we want them to do and that they need to do, realizing that in many ways those incentives are not aligned. It's a group that's being run by the National Academy of Science and Engineering and Medicine. So there's certainly hope that some of these things will be moving. And if anybody's interested in sort of hearing more about that, feel free to reach out to me.
Okay, and I thank you all very much, but it was an interesting discussion, but I think we are 18 more minutes. Okay, so very good. No, we can have, well.
I see a bunch of hands.
Yes, there's plenty of hands here, so.
I just wanted to say, speaking to this issue, the group we have in the School of Medicine working on increasing reproducibility has a working group on creating a CV, a new CV for Stanford that makes more reproducible research and open practices more visible. Because we actually think, see if this is on, actually think that we're the ones who promote each other. So if we as a community value these things, if they're visible in the CV, they will be rewarded. we say that they're not, that we don't reward them, but it's because they're invisible. So the goal of this project, and maybe it will be subsumed under other things that are going on with Helios, is to be able to have the faculty show what they're doing in this area, so it can be valued in promotions committees. So this is particularly for Dr. Satz. So hopefully that will have some salutary effects, but it may also, we'll see what's going on with this consortium. Maybe they're doing the same thing. And anybody who wants to contribute to that, please contact me, Steve Goodman.
Yeah, I just had a quick question about like a different kind of trust. So all of you do interesting like interdisciplinary data science work. So on teams, when you do research, as we talk about drawing in experts from different disciplines, how do you build trust in the team when people speak different languages? Especially in contexts where you might be interacting with an expert who you really value their expertise, but they're skeptical of an approach to science that focuses on quantification, which is an experience I've had a lot meeting people who work on qualitative research who have really valuable things, but I think are skeptical of data scientists who are interested sometimes for that reason. How do you build trust on teams in that?
Great question. I'll say one thing which we've found pretty successful in terms of an ethics initiative that's been going on partly around artificial intelligence, but where we're embedding ethicists in groups. So it's not like somebody coming from outside and speaking a language and pronouncing from on high, like we've got the answer here, but actually working together over a long period of time in order to learn more about each other's languages and then be able to contribute in more positive and helpful ways.
Yeah, and I think these long-term collaborations, like you mentioned, are really important. I think one of the best ways to build trust over a diverse team is to really bring them in from the very beginning, right? From the, not just at the very end in the paper writing and the validation stage, but think about even in the question formation stage, right? So some of the most fruitful and fun projects that I've had the pleasure to work on involve collaboration with historians and linguists here at Stanford, and we started this project from the very beginning, and even in conceptualizing what to do was, what to do, what questions to ask.
Hello. Hey, just had a question for, I guess as everyone could, and feel free to answer. So I had a question about, so could you describe a scenario or example where getting comprehensive, trustworthy data is really, really hard, but really, really important? And could you also describe like how do you address that problem?
Well, so I work in genetics, and it's hard to get good genetic information for people with different ethnic backgrounds. And not only it's difficult to get good genetic information, it's difficult to get access to phenotypic medical information. It's much easier, you can imagine, to get information for people in the United States that it's to get from people in Central Africa. The medical resources that are available there are just not comparable. So to say, I want to design a study that has population from all over the globe, it's very challenging. At the same time, it's very important because the environmental factors that people are exposed across the globe are diverse. Our fundamental biology is the same, but there are differences in our makeup, in our genetics, just due to evolution over time, the randomness of how some genes get transmitted or not, some mutations arises or not, and those ones might have implications on how well you respond to a treatment or not. So a big challenge, for example, in the studies of genetics is how do you get data on a diverse set of people? And you can collect some diverse individuals in the United States, but really that doesn't represent the geographical diversity, the different type of exposures and culture that people have all over the globe. And it's challenging, and it's a clear challenge in terms of resources, but still quite important.
Hello. Yes, it works. Hi. Thank you so much for this panel. A question that I have that I would like to hear your thoughts on is sort of the promises of data science have been sort of the scalability and the efficiency, which at the same time is also maybe part of the reason why it's seen as sort of the fast, sloppy, superficial way of doing things. I recently attended a conference about learning analytics where there is like lots of fine-grained data. And at the same time, people were identifying the problem that this type of research doesn't really happen in communities. So there's lots of data, but people aren't really within communities of learners to understand where their problems might arise. And I wonder to what extent the issue of trust is because there is a lot of unknowns for the people that data are sort of extracted from. And so I wonder how you feel about sort of the approach of there might be more room for mixed methods, because I feel like there's this really hard part where it's really hard to combine sort of the promises of data science with that exact issue of that you're so far removed if you're just simply working with data from the population that you care about.
I absolutely agree that we need to, for example, involve in data science, impacted communities and incorporate qualitative information and community-based participatory research to understand, to make sure that the work that we do in data science, especially when we're thinking about having more complete data sets, is particularly not extractive. And we also need to be open to the idea that there are some questions that we shouldn't ask and answer, because if you're going to engage in this process, that you need to be open to that. And that there's some information that maybe you might want to collect, and you have to be open to the idea that maybe we don't collect this information because it can be stigmatizing or harmful or perceived that way, and that would lead to individuals not wanting to share their data. So I think there's a great need and a lot of promise for having mixed methods and bringing together these fields with data science, for sure.
So I want to bring back a concept that was touched upon before, that is the role of uncertainty and variability. So, we have said multiple times now that trust is a relational quality, so you need to have two agents talking to each other. And I think that people cannot trust each other if they cannot understand each other. And when we think about scientists trying to communicate their results to the general public, I think we have a longer, more serious effort to make than when we are communicating to other scientists. So, how do we communicate the nuance and the complexity of our finding? Because science often doesn't have a yes-no answer. Whatever effect we might have comes with lots of cautions. We have, things like confidence intervals or prediction intervals in statistics. But what strategies have you found are maybe more important to pursue, more successful in communicating the complexity of the scientific finding to the public?
Yeah, I think that's a really good question. One technique strategy we found to be very useful is to have more interactive interfaces between the data science and the models built from the data and the end users, which could be public or could be domain experts, right? So, for example, we try to build these interactive interfaces where the user, maybe just on their web browser, right, they can just say, they can change the data. They can say, what happens if I remove this part of the data, right? And then see in real time, how does that actually affect the predictions and also the uncertainty that the model makes on the data, right? Oftentimes, it's hard to describe those, hard to get those just from reading a paper, right? So if you can actually interact directly with the data and then tinker with it, oftentimes you get the users get much more better sense of what is going on with the model and with the data, and they can develop more trust.
I have one. I actually think, maybe I'll be speaking to the choir here, we should be teaching statistics earlier. It shouldn't be that you have to wait to college to get statistics. We actually should be teaching it like in junior high school and high school. We should be helping kids understand concepts like risk and uncertainty. We've got to do a lot more. I don't think we can just do it alone. We've got to have a national movement to really raise the literacy and the comfort of people with things like uncertainty and risk. And
I would endorse that and also stress that I think the AP statistics needs to be very heavily revamped. I dropped AP statistics and ultimately went on to major in it. That's how non-engaging AP statistics is, and so I think it, with this eye towards understanding uncertainty, et cetera, rather than reading tables in the back of a book and looking up z-scores.
Here.
Hello, is it on?
Yes.
Okay. I was wondering if the panel had reflections on the impact of the COVID-19 pandemic and the pandemic response on public trust in data science, especially as it relates to healthcare, since we have a number of experts on the panel.
Do you want to take?
Sure, I'll take a first stab at this one. I think the reaction to this is mixed. I think the pandemic has shown some people how advantageous collecting data and analyzing data in real time, how useful that can be for public health. I think because we saw some bad projections and predictions and some bad data science in COVID, it's also decreased trust among others. And so we're dealing with this bifurcation of how people are viewing data science, and we really do have a problem where some people think, oh, you can just make anything up with data. And we do need to surmount that.
Yeah, and I agree with that. And also I think it really highlights a lot of the challenges with doing good data science, right? And brought to the forefront that these are very difficult problems to make sense of the data, and different people can reach very different conclusions and different projections on the same data set.
Are there lessons to take in going forward? Maybe it's too early to tell.
Well, I think, rephrasing somewhat all the questions, how does this compare with, how does this relate to another topic that emerged before of do we make every data public? How quickly do we publicize our results? Do we have to put some control on when is some information ready for spreading or not? Some of the controversy around the pandemic was entirely political, and I think that as data scientists, there's nothing you can do if you have a divided audience that is going to fight about anything. They're going to fight. But we had some problems with preprints, research work that is not peer-reviewed, is not really a product of science entirely, but in a context of the pandemic, you want to shortcuts. You don't want to say, oh, there's important information there, and I sit around and wait for everybody to review or not. And then, we also discovered the peer review is not perfect, but it's useful because things that are not peer-reviewed are not peer-reviewed. And at the same time, you can put out data and people can torture it to make it say whatever they want. And so does the panel have any idea about what control steps should we or shouldn't not put in place in terms of data sharing and also research results sharing?
I think one important takeaway that, even really well-intentioned analyses during the pandemic were sometimes not very transparent, and people were trying to back calculate the assumptions that were made in the model to try to understand why they got such disparate results. And that's something that we can really take towards minimum standards. We've seen machine learning-based papers published in high-profile clinical journals where the algorithm is not transparently included, not in the appendix, there's no code shared, and part of that is because they might want to spin off a startup company. But how can we allow something that's going into some of our top clinical journals that they want to influence practice and have uptake and not be transparent about the algorithm? So I think that's just one example of something that we've learned is incredibly important, and I hope we can bring it to our minimum standards, that we transparently share the different features of what the model is.
I read a paper, I think it was by John Ioannidis and co-authors. There was a huge flood of papers due to COVID-19, like an incredible flourishing of scientific endeavor. 1 million papers, 2 million papers, I don't remember the number. And I don't know that the fraction of doubtful claims is any different in that flood of papers than what came before. Maybe it's higher because people are rushing, but it's just a huge volume of things. But people's anxiety about scientific mistakes was much greater because it seemed that the stakes were so high. And so definitely it was received into a different world, and also because of the emergence of medRxiv and rapid publication. That literally started just before the pandemic. So we were like utterly in a new world for clinical science publishing. And maybe we perceive that it's a world with flaws, but it might be quite continuous with what came before. I'm not sure.
This is not completely on this, but it goes back to your question about should there be like a code of conduct, or we're talking about, it does seem to me, so we have conflict of interest rules. We also have in the sciences where you've got a list all the people who are supporting your work. I don't know if there's any norm like that for data science, but that might be like a good norm, is if your research is being funded by, X and Y group, at least that people know that. And I definitely think we should make, when we can, the data we're using and the hypotheses, we should put them out before we do our work so that they're then available for people to replicate.
Yeah, and I think that's really important. And there's some recent efforts along those lines to make it more standardized in terms of reporting the entire life cycle of the data. So not just what's the final data that's being used, but also how the data is pre-processed and curated and cleaned even before that usage. And those are all really important.
And, to bring this back to uncertainty and to what Professor Donovan was saying, maybe we made some mistakes during the pandemic, but maybe they are just the normal amount of mistakes that the scientific process entails. It's not that every paper is right out all the time. We always have contradictions. So we have to find a way of going from scientific community to public consumption that I think needs to be rethought a little bit. We have to have the people comfortable with the fact that not everything is going to be perfectly spot on from the very beginning. There is last question. Do you have your mic?
I'll just make one. To be fair, I do believe there are people who make money off of playing against science and who have podcasts with millions of listeners and promote anti-science skepticism. And that also didn't exist 2 years ago. So that creates a whole nother layer of issue that we might not have had in the past.
And maybe they buy a lot of bots.
I'm afraid to make this the last question, but coming back to different versions of trust, there's the competence version of trust, but there's also the question of whether people are harmed, and underrepresented groups often aren't getting too much of a say in some of the questions that are being asked, and there are very diverse groups that might look differently at different questions, and we've talked about the COVID example. It's exciting that data science is moving into the policy and social sciences realm. Those of us who were in this business a generation ago would be very excited to see this, and it wasn't so much the way it was taught. What questions do the panel feel should not be asked? Sherry suggested earlier that certain questions, are not necessarily exactly pro-social. Mm-hmm. Do we have any clarity on what is science that should not be done, and how do we reconcile that, with our desire to sort of live in a world free of bias, mm-hmm. that we're going to just not ask certain questions? So, do people have thoughts about where data science shouldn't play?
Anyone?
So I think you've highlighted a really interesting trade-off, which is that there are certain types of data where it's relatively hard for us to collect, especially data related to sensitive attributes, right? And there are kinds of analysis that relates to sensitive attributes that are usually people would like not rather to do that, right? But on the other hand, if we want to evaluate equality or the performance of a given model across, to make sure that it actually works well across diverse populations, then we do need to have some of these sensitive attributes collected, or these proxies of those attributes, in order to actually assess how well does the model work across these different populations. Right? So that's actually, I think, a really hard trade-off. There are different approaches for trying to address that, maybe by using proxies, but I think that's sort of a fundamental trade-off.
I interpreted your question differently. In terms of which scientific question we should ask and which scientific question we should not. And I think, and there is a trade-off between what you want to do, scientists to be as creative as possible and think about problems that we have not thought about yet, versus, is this a worthy questions for us to spend money on as a society? So I think, maybe scientists are free to run wild and ask any questions. But I would think strongly, if I were a funding agency, which research projects I fund versus not. And I think it's a real question. In genetics, for example, we often do the genetics. There's many studies that look at, can I find the genetic basis of educational attainment? Or can I find the genetic basis of sexual orientation? And I think you have to ask yourself, why are you doing this? There's certainly something to learn, but what are the repercussions of you just putting out a paper that says there are genetic bases for how well you do it in school or not? So I think if you ask some difficult questions or some questions that can have repercussions that are not what you intended to, you should spend a little bit more time. And you should do that in a context of a very carefully curated study. So I think these questions are particularly dangerously taken on when you use some recycled data, saying, oh, by the way, I have all of this data set, and I can also address this. And maybe it's not the best data set, but then you have these conclusions out there. But I don't know which questions we should ask or not, but I think it's a democracy type. It's a public discourse of what do we find, what do we support versus what we don't.
A related topic to this is there's been a lot more work now in trying to fix algorithms that have disparate impacts. And I think it's also important for us to, when we think about questions that are that we should be asking or shouldn't be asking, there's also that we should take a step back and say, instead of trying to fix this algorithm, should this algorithm exist? And that it's always valid to ask that. And sometimes the algorithm not having it will cause more harm than having it, but that's a question that's often not asked. It's really about, okay, can we add some variables or change the loss function, or how can we fix the algorithm? And there isn't that bigger picture of stepping back and saying, why does this exist, and should this exist, and is there another way to accomplish the goals that this algorithm was trying to achieve in a way that's more equitable?
All right, and on that, let's thank this panelist and
Thank you all. Thank the panelists. Thank you, Professor Sabati, for that engaging conversation. Before we wrap up, I just want to take a moment to thank a few people who made today possible. Lynn Keel and Charlene Zelnis, who probably are not in the room because they've been working for weeks, if not months, taking care of all the logistics, getting great help from Stanford Events, Stanford Video, Stanford Catering, and the Huang facilities team. So thank you to them. Also, thank you to the volunteers who helped pitch in today, Heather and Joanna for the mic running, Janice, Pauline, and Judy, and Cassandra for the poster session, which is coming up. And of course, our data science scholars for the wonderful posters, their thoughtful work and design, and all the speakers who shared their vision for how data science is driving new discoveries. And so to help close the program, I'm excited to introduce David Studdard. David Studdard is the acting vice provost for research and professor of health, policy, and law. He also leads an important initiative aimed at bringing the next generation of data resources to campus. So please join me in welcoming David Studdard.
Thanks, Chris. It's kind of intimidating to see my name up on the screen like that. It's great to be here, and I'm even more delighted that this is happening, the inaugural conference of Stanford Data Science. Long time in the planning, Chris. I was able to attend the last half hour of that session just now on trust, and I regret not being here for the whole day. It was fascinating. The reports I've been hearing are that the day has gone very well, and it's been highly successful, so congratulations to the organizers, to the speakers, and to all of you for participating. Emmanuel and Chris asked me to close by just situating data science at Stanford in the broader university landscape. From my different jobs in the Vice Provost and Dean of Research over the last couple of years, I've had a sort of vantage point on that. Let me start with, I think, the most important one, and I suspect I might be echoing here what the President said in opening earlier today. Data science is a major priority around here, and the university is committed to it. From where I sit, I've seen a pretty clear recognition of two things around data science from the leadership. First of all, harnessing the power of this ever-expanding body of data around us is really essential to improving public policy, to addressing disparities and racial injustice, to protecting the environment, to advancing our understanding of the world. In other words, it's a critical part of Stanford's ability to make an impact in the world. Secondly, I think there's pretty good recognition out there that we're good at this. Stanford, across computer science, mathematics and statistics, the physical sciences and the social sciences, is as good or better than, I would say, any other institution in the world. But continuing on our individual paths without being strategic and purposeful about how we do this is not going to get us there. It's not going to keep us at the forefront. It's not going to get us to where we want to go. So we can't be complacent. We have to invest time and resources to make this happen. So what are those investments? What is the university actually doing? Well, I think the most visible thing is right here around us today, and that is the Stanford Data Science Initiative being led by Emmanuel and his wonderful team. I think it's off to a terrific start. As many of you know, the initiative has a range of activities underway with trainees. They include the data science scholars, the data science fellows program for postdocs, and a new undergraduate major about to arrive. The initiative has also established, as many of you know, theme-based centers on causal inference, open science, sustainability data science, and health. And possibly with more to come. And 4 to 5 faculty recruits, joint between Stanford Data Science and different schools, are also on the way. I think they're on the way, right, Emmanuel? Yeah. They're on the way.
I think committees make decisions as we speak.
Good to know, good to know. More generally, I would say Stanford Data Science, maybe its most important role, has been as a focal point for convening people and groups and communities. It's linking data scientists in some domains with data scientists in other domains, and these are people who've never spoken before. It's linking subject matter experts with methodological experts across multiple disciplines. That was always part of the original vision, and I think it's happening. So I would say that today is testimony to that convening force that Stanford Data Science is becoming, and we're off to a really promising start. Another way in which the university is investing in data science is by improving the tools and the infrastructure that we all rely on to do first-rate work in this field. There will soon be a formal announcement that in the coming fiscal year, the Provost and President have committed to investing more than $5 million of new money towards shared data resources. Those investments will support improvements in equipment and staffing at the Stanford Research Computing Center, which is our main shared computing facility here on campus. There'll be a new data resources facilitation service. This will help researchers, especially new faculty, develop computational solutions for their project needs. And a dataset acquisition fund will be established. Its purpose will be to provide these multi-use, high-demand datasets for the research community so that individual research groups don't have to bear those costs or compete with each other for these datasets. The libraries already do some of this, but the fund will focus on larger acquisitions. We have a pretty good signal that this year's investments will be the first tranche in an ongoing multiple years of investments, perhaps over the next 4 to 6 years. I should also add here that there's a parallel program of investments approved for upgrading our scientific instruments. And that's relevant to some of you because those instruments are producing the data that we all work with. There's one other investment I want to mention. One of the most frequent concerns I've heard during 2 years of going around campus and talking to colleagues is that the process of bringing data sets onto campus is just too hard. It takes too long, there's too much legal and bureaucratic maneuvering involved, and the risks are often poorly understood, sometimes exaggerated by the people handling these agreements. The Provost has recently committed to funding a new unit that spans all of our sponsored research and contracting offices. The unit's sole focus is data use agreements, negotiating them efficiently in close collaboration with faculty and other researchers. 3 of the 4 staff positions in this unit have been filled. We expect the 4th to be filled shortly, and for the team, the DOA Tiger team as we're calling it, to be fully up and running by the summer. I'm hopeful that that's going to make a difference to our day-to-day experiences with data acquisition, but I look forward to hearing from you next year as to whether that's proving to be true. So in sum, I'm really excited by the continuing growth of the Stanford Data Science Initiative and by these new investments of the university. I see them really as concrete statements that the university gets it, that leadership places weight and value on data science. And I think they're also indications that data science is recognized as integral to the university's future. So congratulations on holding the conference. I look forward to coming to many more of these, and I really applaud your efforts in this area. Thank you.
Thank you, David. After 2 years in isolation, not complete isolation, I feel completely reborn today. I had a great day. I heard some terrific talks in many different areas of science. I feel refreshed. I feel reborn. I feel energized. I feel I want to do more. And so I want to thank all the speakers for making this possible, for sharing this day with us, for all the attendees. And so I just want to have a big round of applause to our speakers and all the panelists who've made this day, as far as I can tell, such a great success. I also want to thank the people. Chris did already some of it, but he forgot some people. So Chris, thank you very much for helping us with Stanford Data Science and for helping us organize this event. And also I want to thank Chiara for being our conference chair. She's worked tirelessly on the organization of this conference. She has put her most beautiful colors, her Ukrainian colors, for today, and I can see, because at home I could see how long she worked on preparing for this conference. So I want to thank both Chris and Chiara. I want to thank people from the Dean of Research who have helped us organize this conference, and from development. I'm very glad that we had the last word by David, because with development, we're working on trying to up the capabilities for big data computing on campus. You'll hear from us soon about this. And so I want to thank both the Dean of Research and the development. The last thing I want to say is the day is not over. I think you should go all to the reception. We prepared refreshments for you. But more importantly, a big item at the reception will be that you'll be exposed to the work of our data science scholars. And they're absolutely wonderful people, and they say they embody the spirit of Stanford Data Science, which is collaborations, which we've heard about all day long, and multidisciplinarity. So please, please go to the reception, meet our data science scholars, and if you're a faculty member on campus, please encourage students in your units to apply for this data science scholarship and join us. Again, as I mentioned earlier this morning, we are listening to you. The point of Stanford Data Science, as I said a few times during the conference, is a lot of people do data science on campus. This is not going to change. But how can we be a bit greater than the sum of our parts? And that's what we're trying to achieve here, through new collaborations, through resources that we're trying to build, through graduate educations and fellowships. And so with this, and with the renewed spirit, I'm going to go to the reception, hope to meet a lot of you, and thank you very much for coming and for making this day such a great success. And please engage with us. Thank you.
Thanks for everyone online. We'll see you next year. For people here, go all the way down to the basement level. The amphitheater is right out there.